There's some noise.
Hi, Nicholas.
Good morning.
Yeah, morning.
Hi, good morning.
Okay.
We have already, Dr. Nicholas Rubin is already there.
So I.
Hello.
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 Yeah. So it must be around 9 p.m. or something like that there.
Yes, around 9:30 p.m.
Okay, sorry to bother you at late night.
It's fine. I prefer this versus early morning.
So we'll start shortly. We have to wait for a couple of minutes.
Okay.
So let other people join. So Bimalenda. Bimalenda.
Yes, I can hear you.
Yeah, you can just request the speaker to share the screen and then you take care of the rest.
Okay.
Okay, so I should introduce the chair,
Yeah,
right?
you have to do that person.
Okay, okay, sure.
Can you see the screen?
Yes.
Excellent.
Hello.
Yeah, hello.
Good morning.
I
request Dr. Nicholas Rubin to share your screen.
yes, he's sharing a screen currently.
He's sharing. Okay.
Yes.
Prasanna, I think we can start. Maybe
We can start, right? Okay. Okay, so very good morning to one and all present here. Today we have very exciting talks on quantum information and quantum computing, light matter interactions, as well as electronic structure. So before I go ahead and introduce the chair, excuse me, Professor Bimalendude, I'll just add a quick note that those of you who have questions during a talk, I request you to either type it on the Zoom chat window or on YouTube comment section. And the questions will be sent to the chair and he will ask the questions on behalf of those who type their queries after each talk ends. So having said this, I take great pleasure in introducing the chair for the upcoming two sessions, Professor Bimalendude. He's a professor of physics in the Indian Association for the Cultivation of Science, Kolkata, India. He works on a wide array of topics, including quantum optics, quantum information, cold collisions, superfluidity, superconductivity, orbital angular momentum of light, and the list just goes on. So who better than Professor Dev to chair the upcoming two sessions? So Professor Dev, I request you to take over. Thank you.
Thank you, Prasanna. So welcome to the first session of the day. So we had 5 speakers in this session, 2 keynote talks and 3 invited talks. So before I introduce our first speaker, Dr. Nicholas Rubin, I would like to wish 65th happy birth anniversary to Professor Bhanu Pratap Das, whom I call Bhanuda. I don't see Bhanu. Okay. So now let me introduce our first speaker, Dr. Nicholas Rubin from Google Research, California, USA. So he has been working at Google Research since January 2019. He had obtained his PhD in theoretical chemistry from University of Chicago about 4 years ago. His research interests include optimization theory to solve complex real-world problems, strongly correlated materials such as high-temperature superconductors, and robust computational modeling of the electronic structure of molecules and materials, quantum computing, and quantum programming. So his title of the talk is First Step in Intermediate Scale Quantum Chemistry on Superconducting Quantum Computers. So with this brief introduction, may I invite Dr. Nicholas Rubin to present your talk. Thank you.
Thank you very much for the introduction. It's wonderful to be able to give this talk, especially for the anniversary and birthday of Professor Das. He invited me to Tokyo last year, about almost a year ago, to present on work that was slightly prior to this. And so this is kind of what I've been doing, and it's nice to be able to at least talk about it for this special event. So I'm going to be talking about an experiment that we ran on the Sycamore quantum processor. That is the quantum processor that Google has built. It's the processor that we achieved quantum supremacy on. For those of you who don't know, quantum supremacy was the first time where we showed a quantum computer outperforming a classical computer at some contrived task. And so my background is in quantum chemistry, and so the very first thing that I wanted to do with this device was run a chemistry experiment on it, and that is what I did. And so I'll tell you about this and the background about what led us to this experiment. So first, a little bit about the group. I come from an industry group, so it's a little bit different in terms of the structure than an academic group, and so I wanted to kind of highlight that right away. This is actually about a year old, this picture. The group is a little bit bigger than this now, but we're at about 80 people. It's a collection of superconducting qubit physicists and microwave engineers, software engineers, and then algorithm theorists such as myself. And this is us in Venice, California. The hardware effort is actually located in Santa Barbara, which is actually just up the coast of Los Angeles. And we have some other efforts. Theory is actually in Los Angeles, and then also in Mountain View, where I'm working. And then there's some software efforts that are up in Seattle. So all along the West Coast of the United States. Okay, so a little bit about the processor before I get into the theory of the experiment. The superconducting qubit platform that we're using is the Sycamore quantum processor. It has 54 transmon qubits, and it's laid out in a square array, and there's tunable coupling between each of the qubits. And so this is kind of this picture here is what it would look like after we flip the chip on top of it. So actually the qubits are on the top side of this chip, and the bottom chip is actually just for wiring. And we bump bond the top chip to the bottom chip with niobium bumps for superconductivity connections. Here is a nice picture of the CEO of Google, Sundar Pichai, right next to our dill fridge, which is dilution refrigerator holding the chip. There's nothing in it. You can actually see all of these microwave lines are empty. But it's a pretty big system. There's about 200 control lines for these 54 transmon qubits. And if you just look at the performance from a theory perspective, so I'm not a superconducting qubit physicist, and so I don't worry as much about the specifics of leakage to the third level and how much anharmonicity is there in my qubit. I usually look at metrics like what is the single qubit and 2 qubit performance per maybe cycle of gates across the entire chip. And if you were to use the device, you'd expect to see something like this, namely single qubit gates are around 3 nines, 2 qubit gates around 2.5 nines, or 2 nines, and then the readout is actually around, we have the highest amount of error in that. It's around 96-97% in terms of reading out single photons from each of these transmon qubits. At the highest level, if a external party was to interact with the system, they'd be using one of which is the language that we use to write quantum algorithms and then send them to the chip to be executed, and then open for work for translating quantum chemistry and other fermionic simulation problems into quantum circuits and the primitives that one might need to use there. So I'm not going to talk about kind of all of the background theory on how you take an electronic structure problem or a material simulation problem and port that onto a quantum computer. But I will start by saying that we intend to build a fault-tolerant quantum computer. And what I mean by that is we're going to build a large enough quantum computer such that the error rates per qubit are sufficiently low that we can run algorithms that would require very, very long circuits. The most common example that we talk about is for physical simulation, like simulating a chemical system with the phase estimation algorithm. So we expect to do this with about 100,000 to 1 million superconducting qubits in a planar array running the surface code. So running some type of quantum error correction to suppress errors. And we expect to be able to push our physical error rates. So those things that I showed on the previous slide about the single qubit and 2 qubit error rates that we'd pull off the device down to about 10 to the minus 3 for across the chip. And we expect to be able to do state distillation, and this is actually a kind of a bottleneck in fault-tolerant quantum computation, doing state distillation. And we expect to be able to do that around 200 to 100 microseconds per round. And so if you kind of use all of that information looking forward and assume that we're going to build something, the next question is, well, why do we focus on simulating chemistry? Well, the nice thing about it is that we have a known exponential separation in terms of algorithmic complexity for getting eigenstates of particular systems. And there's been a lot of progress since kind of when this was first put forward in 2005, where there were kind of unknown runtimes to present day where we actually have better scaling than this for large systems. An example I have here on the right side is the FOMOCO enzyme center for the nitrogenase enzyme. And the improvements that we've seen here are actually largely due to tricks that we import from quantum chemistry. So things that maybe some people in the audience are very familiar with, like density fitting or low rank factorizations, and then even using better basis sets or basis sets that are more tailored to the algorithms that we're going to be running on the quantum computer. So there's been immense progress in fault-tolerant algorithms, bringing down the cost to something that is more reasonable. And it would be very nice to be able to do a full CI type calculation on something of this size. I mean, today that's kind of unheard of. But this is approximately 10 years away, but it's something we have to look forward to. So what do we do in the meantime? This slide I like to put up just because it's always good to look at a logarithmic scale and the resources required to do something interesting with a quantum computer. Order 1 qubits, you might be able to get some, or order 1 to order 10 qubits, you might be able to start getting publications on interesting physics in your system and understanding that device. But then getting up to the million qubit range where you need to run an error correcting code to do fault-tolerant quantum computation, there's this large gap in the middle. And the question is, of course, what do you do there? And we already know one application in around 50 qubits is supremacy demonstration. So simulating, doing some type of computation much faster than a classical computer could. But then in this intermediate regime, it's a wonderful test bed for simulating error correcting codes and studying their performance as we scale the system size. And these would be the largest quantum systems that humans have ever built and controlled. And so this is kind of a new feat in engineering that we're looking forward to new science happening there. But there is a question of whether you can use these devices to do physics or find undiscovered applications of quantum computers, treating it more like an analog device. And so that's what I'm going to be talking about now, because I'm actually very concerned about what we're going to do in this gap. Like I said in the previous slide, we know we have a very good idea of what we're going to do with quantum computers, at least for simulating chemistry in this era, but we are not so sure about this time. And so I think it's a good thing to study. So what do I mean about when I say NISQ era, near-term intermediate scale quantum era, and what are the problems? So many of the algorithms that have been developed for this area use the quantum computer much more like machine learning black box, namely some state that you hope is actually difficult to prepare. And would be difficult to prepare classically, and you perform some measurements to evaluate some functional that you're encoding in a Hamiltonian or some linear combination of permission operators, and then you change your probability distribution with a classical optimizer such that some functional is decreasing in energy. And you can actually cast almost all optimization theory like this, so optimization over parameters of a probability distribution. In fact, there's lots of things in classical electronic structure that effectively do this. So anytime you're trying to solve the Schrodinger equation, reduced representation like with reduced density matrices, except you're not making approximations, you're actually preparing the entire state with a quantum computer. So in describing that process, the main challenges are actually pretty clear. The first question is, well, what distribution do I prepare on my quantum computer? Namely, what can I do with a fairly limited number of gates? Namely, I can do things from SU2 and SU4, and with that computation, I can show that I have universal computation. But the question is how to use that to leverage the device to do some interesting chemistry. The next is this step right here, in between your quantum and classical processor, and that's the measurement step. Namely, have information out from our device very quickly and useful information. And I'm going to use a lot of the infrastructure in RDM theory. They're very nice observables to look at because it really captures almost everything you need for chemical system. Noisy black box system because there's no error correction, right? And so this is still suffering from decoherence as we're executing one of these circuits. And then how do we use optimization such that we can minimize those errors? So one slide that I actually recently made when talking about this was why bother going through all of that trouble? I mean, everything that I talked about on the slide, this sounds a lot more complicated than either improving existing coupled cluster methods or any of the perturbative type methods, methods. So why bother going to do this? Well, first is that variational freedom can help mitigate coherent errors on our device. So I'm very worried that our quantum computer is noisy and we're not going to be able to execute very long circuits. But with variational freedom, you are allowed some error robustness. For example, if I'm doing a Rabi oscillation on my quantum device and I have a miscalibrated gate, namely, I'm not actually performing an RY rotation, I'm performing an RY rotation with some error coherently. Well, with variational freedom, if I asked you for where the minimum of this objective function on the y-axis is, then I would still find the right answer. It would just shift over the theta by some amount that is with respect to the gate. And so if you actually don't care about the theta parameters, then that's okay. And particular scenario in chemistry, very rarely do we actually ask about what the amplitudes of the wave function are. We mostly observe things in terms of correlation function, condensed matter physics. So The other component is that we have access to states that are potentially exponentially expensive to prepare. So a nice example of this is doing arbitrary time evolution for interesting Hamiltonians. So this circuit on the left here, it's just this trotterized form of this Hubbard Hamiltonian. And so here we can imagine this is the one-body hopping term of the Hubbard Hamiltonian, the fermionic Hubbard Hamiltonian. This is the charge-charge interaction, and then this would be another subset of the hopping terms. And it might get compiled into something like this. If you were to do this for a good trotterization for long time periods, then you would get interesting dynamics out of this. And of course, you can have other ansatz. Namely, this goes back to the problem of how do you pick an ansatz such that you're performing something interesting. Okay, so the rest of the talk is going to be broken up into kind of 3 sections. One is going to be the chemistry experiments to date, at least in the field, and how I think this guides some of our thinking. This particular experiment, and then what I see as going forward for error mitigation. So one thing that is always in the back of our mind is answering the question, if we are on a path to quantum chemistry simulation advantage, even using these NISQ quantum computers. And so this is the start of a larger research program, and one that's much longer, where we like to be able to draw a fairly clear line from the number of qubits that we have today. So 10 to the, 10 to the 2, all the way up to the million qubits we'll need to run fault-tolerant quantum algorithms. So on the bottom here, I've plotted a handful of experiments that have been performed since around 2016, when quantum computers started to get good enough actually to be able to perform fairly small simulations. And you can see there's a lot of binding curves because, well, chemists, electronic structure theorists specifically, kind of influenced the field at the beginning. And all of these experiments that I'd like to point out are fewer than 6 qubits, and they barely reach the accuracies that you would need to be able to decipher chemistry using a simulation, or condensed matter for that matter, for example. And this isn't a criticism of these experiments. It's more of an observation that getting these to work, these algorithms to work on NISQ devices, is extremely difficult. And so with this knowledge, it informs our perspective on how to scale up studies and algorithmic studies in the NISQ era. Namely, what I want to do, or what I'm proposing that we should be doing, is scale up important algorithmic primitives that we'll need for NISQ and then into the fault-tolerant era. And I'll explain more what that means in the context of this experiment. So some things that are maybe obvious to other people, but I like to write them down because I think it's important to say at least, is that NISQ will be a long period. We have to go from 10 to the 2 to 10 to the 6 qubits, and that's not a trivial amount of time in terms of engineering. And the goal is to be able to use some of the things that we learn along the way to improve our quantum error-corrected algorithms, and maybe even bring that timeline closer than a decade. Going along with this, we need to learn which strategies will work best in terms of error mitigation. So when you run a quantum chemistry calculation on a classical computer, the level of precision that you're working at is 15 bits of precision almost always. You can ask software like Mathematica or Maple to go even higher and do arbitrary precision if you'd like. But generally, floating point precision is sufficient. And that's kind of what you get for all levels of the theory. So when you select a basis to project your Schrodinger equation onto, you're already getting all of that information. And then when you do operations, you're already working at this ridiculously accurate regime. So we don't necessarily have that, and we need to understand how that will limit and influence simulations. And then ultimately, how far are we from something that's classically intractable? And really, that's an important question for the broader field in terms of building a quantum computer. So keeping this in mind, the thing that I had proposed and what I think is a reasonable stepping stone is actually starting with a bedrock of electronic structure, and that is doing mean field Hartree-Fock theory on a quantum computer. So we study this in the context of a variational algorithm because if you study a basis rotation, and that's how we formulate Hartree-Fock on a quantum computer, a unitary variant of it, and you couple that with energy minimization, then you get Hartree-Fock theory back. So if you just are interested in preparing basis rotations on a quantum computer plus energy minimization, you are doing exactly the Hartree-Fock procedure. And the basis rotation that I'm talking about is a coordinate transform on the single particle space. And so let's say I start with some collection of orthogonal orbitals, and these are not necessarily these necessarily don't look orthogonal right away, but if you've worked within a molecular basis set, if you integrate overall space, these will give you nice orthogonal functions. And then the coordinate transform, or the basis rotation that I'm talking about, is simply taking linear combinations of these. So it turns out that when you project this onto a basis and you represent this in second quantization, this particular transformation can be encoded as a unitary that is quadratic in many body order. And so we're working with Gaussian states, specifically Gaussian states that are particle conserving, because of course in chemistry, we don't want to be losing electrons. Of course, unless we're working with a superconductor, then we'll be working with something that's non-particle conserving. Of course, like I said, if you couple this with energy minimization, you get mean field theory back. So if this is tractable, and I hope we all remember that doing Hartree-Fock, at least the iteration complexity is cubic, but actually solving Hartree-Fock is still an NP-hard problem. We do it all the time, so it's generally perceived as classically tractable. So why bother? Well, the basis rotation is actually a circuit primitive that we're going to need all the time when we want to simulate something more interesting, like a unitary coupled cluster. We have an optimal compilation. Namely, if you were to look at this unitary right here, say, well, it doesn't exactly look like all of these terms in the exponent here commute, and so you might have some trotterization error. We can borrow theory from electronic structure and do a QR decomposition and effectively generate a circuit without trotter error. And from a qubit perspective, simulating fermions is still a very entangled wave function. And so if you were to look at what this wave function is from a qubit perspective by maybe doing a Jordan-Wigner transform, you still have the qubit marginals are still high in rank. Okay, so what's up with my obsession with basis rotations? Maybe you don't necessarily believe that these are interesting primitives if it just comes from Hartree-Fock. But let's say that under a two-body operator that looks something like this. And this is fairly generic. These P and Q R S indices indicate which orbital I'm referencing, and then the alpha and beta are the spins for the spin variable for my electron. And if I wanted to implement, you might imagine performing some type of shown in each term. But it actually turns out that we can import structure and perform a low rank decomposition on this particular tensor, this V tensor here, and write this as a sum of squares operator. And then diagonalize this again, this one body term again, and we get some linear combination of diagonal terms. Now, diagonal terms are actually quite easy to implement on a quantum computer. And so this is a nice kind of structure to have, the form of the operator. But where's the basis rotation? Well, if you were to implement this particular trotter form, you have a basis rotation here and a basis rotation here, and then you have an evolution under a charge-charge type interaction. And so every one of these orange boxes is that basis rotation primitive that I'll need. So if I want to do something like unitary coupled cluster and implement the doubles term, that might be this V operator or something like that, or Hamiltonian or time evolution of a interacting Hamiltonian, this is an interesting strategy, and it uses the basis rotation primitive. Another, of course, is measuring my Hamiltonian. We sometimes take for granted that you can just pull a reduced density matrix. Maybe you can get a reduced density matrix approximation from some amplitudes in your system, or maybe you can get approximations to the Green's function, or specifically the 0 times Green's function, to get observables that you care about. But in NISQ algorithms, we have to measure those with Monte Carlo sampling. And so the most efficient way that we know how to do that is actually rotating our Hamiltonian into a series of bases using the low rank factorization that I described on the previous slide, such that you can express your Hamiltonian like this. Namely, you would write each of the two-body terms as this summation over L different bases. So you represent L different bases. And then you can measure each of these terms in that basis. So if you were to go do that measurement, you need to actually implement this basis rotation circuit. And so thus showing again that we need this particular primitive, even for doing the most optimal measurements that we have for NIST. So this might be a little bit hard to see, but we actually studied this, how much savings you get. And the lines down here, the 3 points down here are just how many measurements you would need using this particular strategy in comparison to some other strategies like just performing a Jordan-Wigner Hamilton or transformation and then measuring each of the terms individually, or finding the commuting cliques and measuring each of those simultaneously. This particular partitioning into these separate fermionic bases works the best by far. And the last is actually a slight departure from using the last example before I move on to other things, is something that is a little bit, it's not actually using the basis rotation primitive, but it uses a circuit that's very close to it. And so if our device can actually perform this basis rotation primitive very well, then we expect it to perform this other circuit that is not a Gaussian circuit. Namely, it doesn't come from Gaussian interactions to be able to simulate that very well. And so on the right here, I have actually a Trotter step for a interacting Hamiltonian with just a diagonal Coulomb operator. So if you represent something in the plane wave basis, you might get something like this. Or the plane wave dual basis, you'll get a charge-charge interaction term, but then your Hamiltonian for kinetic energy might still be non-diagonal. And you can implement this particular gate through Trotterization by doing an RY rotation on the odd subspace of this particular SU4, and then implementing the 1-1 evolution here, followed by a swap. And so this is a primitive, an algorithmic primitive that one might want to use when going beyond something that is efficiently simulable. Namely, every single one of these gates has a Schmidt rank of 4, and therefore we know it's maximally difficult to simulate. Okay, so on to why. We've covered why we might want to actually simulate something efficient like basis rotation circuit or perform Hartree-Fock on a quantum computer. So how do we get that actually onto our device, the Sycamore quantum processor? So the gate that we have access to is actually something like this, where all of these parameters are actually tunable. We can control this theta angle by how long we actually turn on the coupling between two qubits, and all of these other local phases are dictated by pulses on either side of that coupling. And this algorithm for implementing that basis rotation unitary actually only requires linear connectivity. And so I just need to pick out a line on the Sycamore chip and implement my algorithm on that. So this is, for example, a line that I picked for the 12-qubit experiment. So what is the actual compilation? So I have that depicted over here on the left. On the far left, I have some initial basis functions for 12 hydrogens. This is actually just a plot of the core orbitals. So just the kinetic energy and the electron nuclear attraction integrals. And if you just diagonalize that one body Hamiltonian, you would get this set of orbitals, which clearly kind of don't look correct in terms of the node structure, or they look correct in terms of the node structure, but their distributions look a little bit weird. And then, of course, the goal is to implement this particular unitary, a basis rotation, such that we're finding an optimal basis. Namely, we're doing Hartree-Fock. We're effectively applying the Toulouse transform or theorem, or the first Brillouin conditions is another way to look at it, which it feels weird to talk about because Professor Mukherjee is in the audience. So what we can do to implement this particular unitary is actually perform a QR decomposition, where we decompose via Givens rotations the exponentiation of this kappa matrix. And what that gives back is this sequence of gates, this theta 1 through theta 36, where each of those is a Givens rotation. Namely, it's a two-local fermionic gate. And what we choose to do is implement this with a square root I swap, two square root I swaps, and local RZ gates. Now, I could have chosen other compilations of this particular unitary. You can write this with other more standard gates like CZ or C0. But the interesting thing about this particular compilation is that you can look at each of one of these I-swap gates, and I haven't actually specifically drawn it here, but you can think of it as a fermionic Fourier transform on just 2 qubits. So what we're doing is we're Fourier transforming this pair of qubits into its eigenbasis. We're evolving in the eigenbasis, namely this 0-1 subspace, and then we're going back. And that's what these 2 pi z gates are actually doing on either side. And so there's actually no microwave control in this circuit, which lowers the error that we have. So namely, we don't have to pump in microwaves. We can just do these gates by voltage offsets for each of our qubits. And that's actually a very nice thing to have. So that's the compilation of the circuit. At measuring at the end, we can apply other error mitigation techniques such as post-selection. Like I said, we don't want to lose particles. And then other techniques like purification, which I'll talk about in a moment. So the last thing about VQE algorithm is that you need to have some observable to measure. Namely, you need to evaluate your objective function. And so in electronic structure, we can evaluate the energy of our system by measuring the 1 particle and 2 particle density matrices, the 0 times Green's functions, or whatever you'd like to call them, the quantum marginals of our system. I'll try to be fast. And when we're working on Gaussian states, we can actually just focus on simulate or measuring the 1 RDM. Namely, we just measure all of these pairwise correlators because we know for Gaussian states, the 2 RDM is exactly reconstructible. Now, this isn't a general property, but we can use that property, namely the geometry of 1 RDMs, to do error mitigation. So we actually do this with McMeany purification. And of course, we could have just diagonalized the 1 RDM and then projected our eigenvalues to 0 or 1. But we can prove sampling bounds using this particular procedure. And so it's a nicer way to do that. We actually have a more general strategy for doing this. So when you have states that aren't fermionic Gaussian states, we can actually, we have other n representability conditions that we can apply for error mitigation. Of course, these are ensemble pure state constraints. And so that's actually a new kind of direction to go in. Okay, I'm going to skip in terms of time the specifics of how we measure the 1 RDM. And I'll just skip to the performance. So the first thing that we do is actually, well, the most classic electronic structure simulation, which is hydrogen chains after the hydrogen molecule. And so in this experiment, what we did is we picked 4 systems for 6 qubit or 6 hydrogens up to 12 hydrogens. And we dilate the distance between each of those hydrogens and we simulate the basis rotation, namely we perform Hartree-Fock. And we just simulate this on one of the spin sectors. And so the number of qubits directly relates to the number of atoms in a minimal basis. And you can see that we get pretty good agreement with the correct values. The different colors are various forms of error mitigation. So the yellow is no error mitigation, and the red is performing various forms of error mitigation. Okay, so in the last couple of minutes, I wanted to touch on how we do that. And then I'll conclude. So this is just a zoom out of those pictures on the previous slide. If we were just going to simulate if we just simulate the circuit with no error mitigation, we get these fidelities. And that's another nice property of Gaussian states is that you can extract the fidelity without performing exponential number of measurements. And this box here is actually what we expect from the supremacy type error model. And so it has fairly good agreement. But what you can do is actually post-select, namely preserve the correct number of electrons, and we get the right answer. And this is correcting for T1 errors. Purification, you can actually show in a couple of lines. This actually corrects for T2 errors in this particular system, boosting us up to, in the largest systems, 94% fidelity. And then with variational relaxation, namely that thing I touched on in the beginning, if you have coherent errors, you can further mitigate that with variational relaxation. Get to about 3 nines for the smallest system. Nothing really changes for the largest system. This is on 12 qubits, and it's a pretty impressive improvement in terms of fidelity. And I'll end here just on the performance of Diazene. So I picked this particular experiment because we know that, well, we know that for Diazene isomerization, Hartree-Fock, it's the wrong ordering of these 2 transition states. This gap is obviously too large. But it does show the accuracy of the quantum computer here. Namely, we are able to, at least within the two mechanisms that we're simulating. So this is a pretty big step forward. This is about twice as large in terms of the number of qubits as previous experiments, and about 10 times the number of 2-qubit gates. And I'll leave that here and conclude, and I'm happy to take any questions. And thank you.
Thank you very much for the excellent talk. Now the talk is open for discussions and questions. So I see a few questions. So I will take the question from Sumit. So he asks, does not the circuit become very expensive using so many swap gates during basis rotation? So many 2-qubit gates. How do you plan to reduce the cost? So this is the question.
So eventually, I hope to actually be able to implement the unitary for the Givens rotation explicitly without having to actually do a compilation here, which would certainly save me a couple of 2-qubit gates. And that will require a new level of hardware control. But outside of performing something like a non-orthogonal LU decomposition to do the rotation, this is, as far as I know, the most compact representation of a basis rotation. Namely, this can be cast as a parallel swap sorting network from computer science, which we know is an optimal depth circuit for doing sorting. And so we're not going to save so much on doing a basis rotation circuit like this moving into the future.
So does that answer, Sumit? Okay, so the next question I see from YouTube. This is from Sandeep Dubey. So he says it's a beginner question. How do we apply quantum logic gates in lab on a system in some initial known state?
Sorry, could you say the end of that question again? How do we apply logic gates in some known initial state?
Okay, in lab.
So the logic gates, I guess maybe I'll try to answer what I interpret this question is about. So in classical computers, when you're doing logic, you're sending information through a digital circuit that does the transformation, namely turning off a particular voltage setting somewhere. Here, you're actually operating directly on the memory, which is the qubits. And so we can initialize the qubits into, well, they cool down, they relax, they're 2-level quantum systems. And so they all start in the 0 state initially, and then I can perform a pi pulse to initialize it to a 1 state on some subset of the system. In this case, it's like half filling, for example. And then after that, these are coupling gates. So these I swaps are coupling gates between 2 qubits. And then these are just voltage offsets. And we do that by applying, well, these are all in the rotating flame, and so we can just change the frequency of the qubit a little bit, and it will apply this gate.
Okay, thank you. So we have still some time left. We have another 7 to 8 minutes. So I'm waiting for more questions.
Professor Dev, there is one more question from Srinivasan Prasanna. It's in the chat box.
Okay.
May I help you, Professor Dev? Yeah, maybe let me read it out. When do you think or speculate one can see quantum supremacy for quantum chemistry using quantum computers? Do get a feel for numbers, since I am not so familiar. How much of an improvement over other platforms will a 200 microseconds magic state distillation be?
Yeah, that's a good question. The kind of jargon associated with how to actually time fault-tolerant algorithms always depends on what code you implement, namely what error correction code you implement. So in the far future, you have to pay attention to, for example, the Schroederization scheme in your particular algorithm to implement time evolution, to do phase estimation, and then the accuracy at which you might want to represent all these rotations. Because in error correction, what we do is actually we go back to a digital picture. We digitize all of these rotations, and we have to synthesize all of those digital rotations with a T-gate, which is in a Z of pi/4. Now, in a NISC setting, like, for example, in the supremacy experiment, those circuits in total, to take about a couple million bit strings of data, we only needed a couple hundred seconds. And so there's a difference in terms of counting time for error correcting codes versus counting time for NISC. Whether we see, I think the jury is still out on whether we'll see a quantum advantage in the NISC era, but I certainly know that once we get to a large enough fault-tolerant computer, we should be able to simulate fairly large systems and see chemical simulation advantage. So worst case, 10 years.
Okay, so we have still 2-3 minutes left. So I don't see any more question coming. Okay, I see another question from Bindia. What is the reason for choosing square root swap instead of swap gates?
Yeah, this was a fun one, actually. So those of you who've read the supremacy paper might remember that we used a different gate in that particular experiment. We had something that was called the Sycamore gate, which was an I swap followed by a C phase of pi/6, or approximately pi/6. Now, if you want to synthesize one of these Givens rotations with that gate, it actually requires 3 Sycamore gates. The reason that we chose I swap is because this gate is actually a Fourier transform on 2 of these fermionic modes. So each line here is a fermionic mode, and the I swap gate you can think of as just doing a Fourier transform, so a twiddle operation in the fast Fourier transform at the lowest level between these 2 modes. This rotates it into an this pair of qubits eigenbasis that we can then just do the evolution in that eigenbasis with 2 RZ gates and then go back. So that's actually what we advocated for to the experimental team. We said, they asked us what gate we needed for interesting chemistry simulations. And we said, well, generically, I would like to have an FSIM gate, a fermionic simulation gate like this. But in absence of arbitrary control, why don't you calibrate a particular value for this theta such that it's a useful thing for fermionic computation? And so that's actually where that came from. It was actually a theory hardware collaboration.
Okay, thank you very much. As I see, there is no more question. So let us thank the speaker for exciting and quite interesting talk. I hope all of you have enjoyed this talk. So with this, we come to the end of the first talk. Now we will move to the next talk. So our next speaker is Professor Arun Kumar Poti. He is from Harishchandra Research Institute, Allahabad, in India. He is a professor of physics. So before joining HRI, he was a scientist at Theoretical Physics Division, BRC, that is Bhabha Atomic Research Center, Mumbai, from 1989 to 2010. His research interests include quantum information and quantum computation, theory of geometric phases and their applications, mathematical and fundamental aspects of quantum physics. Among various awards he received, he is a fellow of Indian Academy of Sciences, Bangalore, Academy of Science, Allahabad. So the title of his talk is Non-Commutativity, Superposition, and Coherence. Dr. Poti, you have 35 minutes for the talk, okay, and 10 minutes for the discussion. Thank you. Okay. So with this, I invite Dr. Poti to present your talk.
Okay, thanks, Professor Dev. And so, good morning, everyone. So, let me thank the organizers for inviting me for this auspicious day to celebrate Professor Bhanu Das, birthday. So, this is very nice to be here. So, let me start sharing my slides. Okay, are you able to see my slide? Hello?
Yes, yes, yes.
Yes, I can see.
Is it full screen or?
No, it's not full screen.
Okay. Okay.
Yes, now it is.
Okay, so as you see, my title today is non-commutativity, superposition, and coherence. So what I'm going to talk today is how this coherence that all of we know plays a very important role in even in quantum computing, quantum information, and how this coherence arises, how to quantify it, and how that this coherence changes under noisy channel and things like that. So which will be very useful in quantum communication, quantum information processing, and things like that. So why not going next slide? So once I make full screen, I'm not able to go to next slide. I don't know why.
Maybe you have to click on that PowerPoint slide. I see, below there are, two arrows, front and back.
Okay, okay. Yes, yes. Okay, thank you. Yeah, so all of we know that in quantum world, superposition principle is something very basic, and that is at the heart of quantum mechanics. So what it means is that if you have a physical system, if it has two admissible states like psi1 and psi2, it is also possible for you to have a state which is a linear superposition of alpha 1 psi1 and plus alpha 2 psi2. And this historically, this notion arises from the so-called wave particle duality, that in quantum world, every entity, every particle behaves in a wave-like fashion and also like a particle-like fashion. So this is a cartoon which tells you this wave particle duality in a very nice way, that photon doesn't know whether itself is a particle or a wave. And if you recall your graduate level, graduate days lecture, you notice that if you deal with this Young's double slit setup and you send so-called particles one by one through the double slit, and you wait long enough, you do see an interference. So even though at any point of time through the setup, you are sending particles one by one, but on the screen, you can observe an interference as long as both the slits are open. And this is a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which is in it the heart of quantum mechanics. In reality, it contains the only mystery. So the way you explain interference is well known to all of you. And why do you see interference, or how does the particle happens to move through both the slit, still continues to be a mystery. So we don't know how it happens, but it happens. And this mystery still continues. We don't yet know in reality what a quantum entity is. Is it really a particle or really a wave, or both particle and both wave, or neither wave nor particle? Because there is a recent article by this group where they try to prove actually the theoretical proposition inequality, and as well as they do an experiment where they rule out, they design an experiment where they argue that to explain that observation, neither wave aspect nor particle aspect is sufficient. Maybe something more is there. We don't know what that is. But this, I'm not going to tell in more detail about this mystery, but we will go about more practical applications of this notion. So how do you obtain coherence in a quantum state? The very basic thing is that it is the non-commuting nature of observables that plays a very major role in quantum theory. And the way you create superposition is you need at least two non-commuting observables. So how do you see? This is very easy to realize. That is, you prepare your initial state in one of the eigenstate of some observable that is of your choice, and apply unitary operator that you generate by some observable B, where this A and B don't commute. So if you apply this unitary to this initial state, which could be one of the eigenstate of this observable A, then as you know, you can create a superposition of all the eigenbases of A. Okay. So essentially, initially at time 0, you had one of the eigenstate in which you have prepared a system, but at some time t, you have a superposition of all the eigenbases of this observable A. So this is a very simple way to illustrate how do you create coherence. And just to give an example for students, who are interested, you prepare initial state of a qubit in state 0, which is eigenbasis of say sigma z, and apply an unitary, which is created by something like exponential minus ix theta, or could be ix y, exponential I times sigma y theta. And if you apply this, you will create a state which is a superposition of 0 and 1. This is very obvious to everyone. And this is the this so-called the quantum bit that you actually use in your quantum computer to store and process information. So non-commuting nature of A and B creates a state which is, as I said, is superposition of eigenbases of all all eigenbases of this observable A. And quantum coherence is a notion that arises from this coherent superposition of different amplitudes. And as you can see, this quantum coherence is a basis dependent notion. So if you recall your textbook level, like if you look at the Cohen-Tanoji textbook, there they do talk about coherence and population of a density matrix. So essentially the diagonal elements of a density matrix are populations, and off-diagonal elements are actually representing coherence. But if you want to actually quantify how much coherence is there in such a simple quantum state, the answer was not known. So this is quite surprising, quite strange. It may appear very strange to you, but so last 80-90 years, we have been dealing with quantum mechanics, but this there is no way to quantify how much coherence is there in a quantum state. So this question was actually answered very recently in 2014 by Plenio group. So what they do is they formally quantify how much coherence you can say given a quantum state. So to do that, what you have to build up your your theory. That is, you have to identify so-called set of free states. And what are those free states? If you have a quantum state, either a pure state or a mixed state, and if we diagonal in a given basis, that those are called free states. And any operation that you would like to do on a quantum state, if that will map those free state to free states, those you will call as incoherent operations. That means those class of operations, either unitary or completely positive map or noisy map, anything you want to act on a quantum state, if that will map to a diagonal state to diagonal state, those operations you will call free states. So this is very simple. Intuitively very easy to appreciate, but mathematically it is more complicated. But anyway, I'm not going to tell too much of mathematics here. So basically, I will try to explain the main results. So, so using this kind of framework, they try to quantify rigorously how much coherence you can actually identify given a quantum system or quantum state. So if you are interested, you can look at that paper. Essentially, they laid down which would be required, to tell, okay, whether this is a valid measure of coherence or not. So that measure of coherence should be 0 if it is in coherent state. That means if you are given a qubit, and if you identify your basis as 0, 1, which is eigenbasis of sigma z, then in that basis, if your state is like say p1 times 0, 0 plus p2 times 1, 1, the projector, then that state you will call as an incoherent state, because that is essentially density matrix diagonal in 0, 1 basis. Okay, and under this incoherent operation, this coherence should never increase. That means this should be satisfied. And there is something called strong monotonicity under incoherent operation. That means if you do the selective quantum operation on this quantum state, and you obtain the state sigma I, on an average, you should not be able to increase this coherence. And the last property is something called convexity. This is not desired, but sometimes it is, this is not necessary, but sometimes desired property, that if you have a density matrix, which is a convex combination of all these components, then CF rho should be less than this quantity. So as I said, you have to identify a set of orthogonal bases to define your coherence, and the probabilistic mixture of orthogonal bases you say is incoherent state. So quantum states that don't belong to the class of incoherent state will have some non-zero coherence, and this may be quantified in several ways, one of which is to accumulate the off-diagonal terms in the density matrix in a that we express in a preferred basis. Okay, so there are two simple measures of coherence. People have largely exploited, that is something called L1 norm of coherence and relative entropy of coherence. So essentially, this measure is sum of all the off-diagonal elements and modulus of these off-diagonal elements. And this quantity, which is called relative entropy of coherence, is essentially the entropy of the diagonal density matrix minus the entropy of the original density matrix. So what I mean here by diagonal density matrix, you have the initial density matrix, you write down the density matrix in a given basis, and you delete the off-diagonal elements and construct the diagonal operator only from that density matrix. You find out the entropy of that, von Neumann entropy of that state, and that will tell you this quantity. So over the last couple of years, several groups have been trying to give physical meaning to this as well as this quantity. So like in 2015, we tried to give an operational meaning to this L1 norm of coherence, because if it is a coherence and if it attributes really the wave nature of quantum entity, that should satisfy some kind of duality with path information when you deal with quantum interference. And indeed, we tried to prove a rigorous complementarity relation between this this coherence and path information, and that generalizes the notion of so-called this angular duality, the very famous angular duality in quantum interference. And also this quantity, the so-called relative entropy of coherence, also has an operational meaning. That is, if you subject your quantum system to a noisy channel, and the channel will try to inject some disorder to your system, and the minimum entropy that you will inject to your quantum system to make it incoherent is actually this quantity. So this has a beautiful meaning also from thermodynamic sense. Okay. So as it is quite clear now, this quantum coherence depends on the choice of basis. That means for any quantum system, there are actually infinite number of choice of basis you can think of, and this means the least to infinite number of different coherence measures. So if coherence captures wave aspect, then for a quantum entity, there is not just one wave. There are infinite variety of waves, which I call as myriad of waves. Okay, so unlike what you have learned in your graduate level textbook, that to a given entity there is a wave, there is a particle, that notion is actually very rough sense. Okay, so actually for a quantum system, you can associate myriad of waves actually. So similarly, if you carry out this duality nature, for each wave there is a particle you can associate. That means there should be myriad of particles as well for a given quantum entity. So carrying out this notion, actually you try to quantify what do we mean by particle when you think of a quantum system. This may look very innocent, but this is highly non-trivial, and this is the first approach that we have taken in this paper, where we try to quantify in a resource theoretic sense that what do actually we mean by particle in quantum world. Okay, so this is not very clear yet. Okay, so coming to the next slide, as we see that coherence is actually a basis dependent notion. That means if I capture the coherence of a quantum system in one basis, and if I capture the coherence in another basis, where these two bases are mutually incompatible, that means this basis say I and this basis A, they don't commute. Is there any trade-off? The answer is yes. We can show that this coherence in basis I and the coherence in basis A, they satisfy so-called an inequality, which is actually nothing but the entropic version of the on-site interrelation that some of you may be familiar. Okay, and the C is quantity which is the maximum of this overlap of I and A, which captures the so-called this incompatibility of these two observable whose eigenbases are this I and A. Okay, so what she's trying to tell you is that this coherence of a quantum system in two or more incompatible bases actually are not independent. That means if in one basis you see less coherence, in another basis you may see more coherence. Okay, and there are a lot of activity going on in this direction. And as I said in the beginning, coherence is the prime resource in your quantum computation, because when you initially you set your register in 000 and you apply Hadamard gate on this computational basis, you create an equal superposition of 0 and 1. Okay? And this kind of states actually contain, if you use this measure of coherence, they contain one unit of coherence. That means if you have n qubit register, you are dealing with n amount of quantum coherence. So coherence is a resource for quantum computation, which will lead to this so-called massive parallelism, whether you talk of source algorithm or Grover's algorithm or any algorithm you think of. So for example, sometimes back we try to figure out how do this coherence measure plays any role in quantum algorithm. For example, we try to find out that in quantum search algorithm, this coherence is actually connected to the success probability in this fashion. So if some of you are familiar, in Grover's algorithm, what happens is you prepare initial state in all equal superposition, and that contains n amount of coherence, and you apply the Grover operator, and in the end, you find your target state. So this coherence initially was maximum, then it gets consumed during computation, and finally, when you reach your target state, that is essentially the product state, and that has no coherence. So that is one of the computational basis state, and that is no coherence. So coherence actually getting consumed during your quantum computation. Okay, so next thing I want to tell you is how does you estimate the coherence of a quantum state, okay, given a quantum system. So obviously, if you have a quantum state, you can of course do quantum state tomography, which will, you have to determine the state completely. From there, you can of course identify, or you can calculate how much coherence is there by looking at the modulus of the off-diagonal element of the density matrix. But is there any better way? Is there any easy way to estimate coherence in a quantum state? The answer is yes. So what you do is you choose a basis I and choose any observable that is convenient to you. Okay, and your quantum state you write in that basis like this, and then split into diagonal and off-diagonal element. And similarly, given any observable A, you write the observable in that basis and split this into diagonal part and off-diagonal part. And then you can verify that the trace of row A diagonal is same as trace of row diagonal A. This identity, and you can show that the average of the commutator of A with the diagonal part, notice the following. Why this is non-zero? Because this diagonal part is having a spectral decomposition in the basis I. Okay, so whereas this observable A may have a different eigenspectral decomposition. So in general, this I and this eigenbasis of A may not commute. Okay, so that is the reason that this quantity is non-zero. And the simple, relation tells you that if you find this commutator of A and its diagonal part and have this average of this commutator, that will give a lower bound to coherence of any quantum state. Of course, in this case, we deal with pure state, but we have generalized to mixed state. So given any quantum state, you can always estimate by looking by this average of this commutator. So this is quite universal result in the sense that you don't have to worry about estimating or doing tomography or doing state estimation and things like that. You can actually find out how much coherence is there in any given state. And this is an interesting application because this mu bound try to connect quantum coherence of an arbitrary quantum state, not only pure but also can be mixed, in quantum system of arbitrary dimension, and the incompatibility of estimator of any arbitrary variable of that system. And along with being potentially a fundamental use, it also provides a ready estimate, precisely gives lower bound on the quantum coherence of an arbitrary quantum state without resource to quantum state tomography. As a byproduct, it provides a direct method of creating witness for quantum coherence, which is not related to existing witness operator till now. So now the last part of my slide is something to do with how does this quantum resource behaves under noisy channel. Okay, so till now we have been talking about quantum coherence of a system by choosing suitable basis, but in general, when we want to do quantum communication or quantum information processing protocol, you may have to deal with noisy channel. And the next task is how does this quantum resource, which is very precious, how do they trade off with in the presence of noise? Okay, so for example, the noise could be due to measurement, could be due to open system dynamics, could be due to anything that is extraneous to your quantum system. And whenever a quantum system undergoes a measurement or a noise map, then it is subject to some kind of disturbance. Okay, so the measurement process not only disturbs the state but also leads to loss of coherence. This is quite familiar to all of you, because once you do a complete measurement on a quantum state, this process diminishes the off-diagonal element of the necessary matrix, and that leads to loss of superposition or loss of coherence. And if there is no disturbance, that is, if there is no measurement or no noisy channel acting on a quantum system, obviously your system will maintain whatever coherence it was there before. Okay, that will have some non-zero coherence in suitable fusion basis. So it is natural to ask if there is a trade-off between disturbance caused to a quantum system and the coherence content it has before it was subject to quantum noise. So let us see how do you get this trade-off. So before that, let me try to tell you, qualitatively, what do we mean by disturbance? Typically, disturbance is an irreversible change in the quantum state that is caused by a completely positive trace reserving map. So if you are familiar with this notion, it is fine. If you're not, then essentially what it means is that, the simple way to realize is you have a system and you have some ancilla, which is your external world. And once you evolve the system and ancilla by some unitary process and you trace out the ancilla, then the transformation that will happen on the system part is actually a completely positive trace preserving map. Okay, so those who are familiar with unitary dynamics, they can be happy with the notion that any such completely positive trace preserving map, so-called CPTP map, are actually nothing but unitary transformation on a bigger Hilbert space plus tracing out the external world or ancilla part of the bigger system. Okay, so any disturbance measure should satisfy some salient features. Those are essentially the following: that this disturbance should be a function of the initial state rho and this CPTP map that you are applying on a quantum system, and this should be null. This should be zero if the CPTP map is reversible, invertible on the initial state, because in that case, what can happen is the system can be reversed back to the original state, and obviously will not be causing any disturbance to the quantum state. And moreover, this should be monotonically non-decreasing under successive application of noise map. That means if I apply one channel once, I apply some channel once and apply again the same channel repeatedly, or maybe different channel also, this disturbance should be non-decreasing. Okay, and it should be continuous for physical map and initial state. We don't differ too much. Okay, so these notions in literature, you will find several definitions have been proposed, like using fidelity measure and Burr's distance and so on. But the difficulty is most of these measures do not satisfy all the requirement. For example, some of the measures don't satisfy so-called irreversibility condition. For example, if you use the fidelity measure definition of the disturbance, this is non-zero even for unitary transformation, which are obviously reversible. And this definition can be null for non-invertible maps, and they are not monotonically non-decreasing under successive application of CPTP map. Therefore, they fail to satisfy the condition 2 and 3 also. So one beautiful measure was introduced by Lorenzo Mecone in this paper. So what he said the following. So given a quantum state, we define the disturbance as the entropy of the state rho minus this quantity, which is the so-called this coherent information of a quantum state under a noisy channel. So what this is trying to tell you is that this quantity is the following, that you have the density matrix rho, and we know that any density matrix can be a part of a pure entangled state, which you think of like this. That means if you trace out one side, you will get the density matrix rho, and this noise is acting on only on the system. Okay, so you look at the entropy of the final state after you apply the channel E, and you look at the entropy of the combined state after you apply the channel E. Okay, so what this quantity is essentially, I mean, in a simple notation, this is telling you that this is the entropy of the system after you apply the channel minus entropy of the joint state. So if you think of the system as A and initial as B, this is like entropy of AB, and this is entropy of the B. Okay, this is essentially negative of the conditional entropy. So this is called, sometimes called coherent information, because this is a very interesting quantity. It was first, I think, studied in quite detail by Shoemaker and Michael Nielsen when they wanted to quantify how much entanglement you can preserve when you send a quantum state through a noisy channel. So essentially, this quantity, this coherent information is trying to tell you how much distinct quantum information you can send through a noisy channel. So once you send the entanglement through a noisy channel, obviously the entanglement will undergo degradation, but how much can we preserve? So that quantity, I mean, that question is answered by this quantity, okay, this coherent information. So the beautiful thing about this quantity is that this does not increase under successive application of the noisy channel. This also is, this under reversible CPTP map, this quantity is same as this SF rho, and hence this quantity vanishes. And this is very, very nice, appealing, definition for disturbance. So with this definition, you can show that this obeys this, bound. And what we do is the following. So we want to quantify how much coherence can be there when you subject the system to a noisy channel, and as a result, your system undergoes some disturbance. Okay, so consider a density matrix rho. As I said, you can always think of that as a part of a pure entangled state like this, and the result that you can show is the following: that whenever a system undergoes a noisy channel, okay, then the trade-off relation is this. So coherence, I mean, twice of coherence per disturbance is bounded by twice of log D. So you see, if there is more disturbance, system will have less coherence, and if it is more coherence, this will have less disturbance. So this is kind of trade-off that you obtain. Similarly, you can obtain even a tight version of this trade-off if it is a measurement channel, that is, if it's not arbitrary noisy channel, but measurement process channel, then you can prove that this coherence plus disturbance is actually less than log of D. Okay. You can also try to ask similar question when you think of a bipartite or multipartite quantum state, because in that case, the quantum resource is not just coherence. You have to also deal with entanglement. You have to deal with quantum coherence, quantum correlations like quantum discord or many other, non-classical quantities. So you can ask, how do you, establish so-called the trade-off between coherence, entanglement, and disturbance, or maybe you can establish something between coherence, quantum discord, or quantum correlation and disturbance, and so on. Is it possible really? The answer is yes, you can do that. So before telling the main result, I should tell you that it was already known that for any pure bipartite state, there is already complementarity between this coherence and bipartite entanglement. That is, given any state like this, which is an entangled state, you can show that the local coherence plus this global coherence between A and B is actually bounded by log of D, where D dimension of the subsystem of the this part. So what we want to prove is you can show indeed there is a complementarity for coherence and relative entropy of entanglement and disturbance caused by measurement or by a CPTP map on this bipartite state. That looks like this. So suppose you have a state rho AB. So I just say you can purify any state. So you can purify rho AB by bringing another third system, which you call as R, and you have an entangled state psi of ABR, such that if you trace out this part, you get this density matrix. And the relative entropy of entanglement is essentially the S of rho AB and sigma AB, and minimize overall separable state. And the disturbance you can also define for bipartite state in the same fashion that you did for single particle. So you define the disturbance as S of rho AB minus the coherent information of bipartite state, and this quantity is essentially entropy of this final state rho AB minus entropy of the global state psi of ABR. Okay, and this disturbance looks like this. The relative entropy of coherence also you can define not only for single system but also for bipartite system by choosing different suitable bases in joint Hilbert space. So if you choose the basis I tensor mu, you can define the coherence like this. And the next step is using these definitions of coherence and entanglement and disturbance, we can actually find a very nice complementarity relation like this. That is, coherence plus entanglement plus disturbance is actually bounded by twice log D of AB. So this is telling you that if you want to maintain this joint quantity, entanglement and coherence both, then disturbance should be less. Okay. So whenever you deal with noisy channel, if your goal is to preserve these non-classical features, then you have to maintain, you have to design a noisy channel such a way that disturbance is less to the quantum system. So our results capture the intuition that coherence, entanglement, and quantum discord for a quantum system should respect a trade-off relation with disturbance. And these results will find interesting applications where we send singular composite quantum system on a noisy channel and that tend to lose this coherence and entanglement. So as I said, if you wish to maintain coherence and entanglement or both, or for that matter, if you want to maintain coherence and quantum correlation, then you need to send the quantum states through a channel that does not disturb too much. And it will be interesting to see if other measure of coherence and entanglement does respect the complementarity between coherence and disturbance. Okay, so let me try to summarize. So what I try to say is that coherence, the very basic feature of quantum mechanics, which has been there for last 100 years or last more than 90 years, has been a subject of great research over the last 4 or 5 years because there is no way to quantify coherence of a given quantum state. Only in 2014, this group Plenio group had tried to capture this coherence in a very rigorous way, and a lot of things are happening in quantum information community. And the notion of coherence actually comes from non-commuting nature of observables, which plays a very important role in creating superposition of different basis states, and that leads to non-zero coherence. And in one of the main results, we tried to show that the average commutator of arbitrary observable and its incoherent part can actually provide a lower bound for the coherence for pure as well as for mixed states. And in subsequent slide, I tried to show that if you want to deal with the noisy channel, obviously you will deal with disturbance to system, and any disturbance that is caused to system by measurement or by noisy channel, you have to deal with this kind of trade-off between coherence and disturbance. And also, you can show that for bipartite state, coherence, entanglement, and disturbance, they do respect the trade-off relation. So these findings will be very useful when you deal with quantum states and quantum communication channels, because finally your goal is to send quantum state and quantum coherence or quantum entanglement and distribute over network or over quantum channel so that you can do some useful task. Okay, so with this, I think I should stop now. So thanks for your attention.
Thank you very much, Professor Pothi. And now the talk is open for discussion. I don't see any question coming.
So there is a question, so let me read it out. In your slide, where you relate the probability of Grover's search with coherence,
Yes.
does zero coherence mean that the Grover's algorithm will work with 100% success, or I missed something? Can you explain a bit more? So this is by Dr. Bindya Arora.
So in the standard Grover's algorithm, what happens is you you prepare your initial state in an equal superposition of all the I mean all the n qubit register is in a state which is 0 plus 1, 0 plus 1, and so on. Okay, so a state which was something like 0 plus 1, in our notion, that has maximal amount of coherence. Okay, so any qubit which is alpha 0 plus beta 1 has some intermediate amount of coherence. Okay, which is less than 1. But this state has maximum coherence. So you start your quantum computer with maximal coherent state, and when you keep applying this Grover operator, it try to consume this coherence and then produces an answer in square root of n number of steps. And when you get the answer, the coherence actually drops to 0. Because why it drops to 0? Because when you put target state, the target state is designed to be one of the orthonormal basis, from the computational basis state. Okay, it could be 1, 1, 1, all 1. Obviously, that has 0 coherence in 0 and 1 basis, right?
Okay, so there is one more question in YouTube by Ms. Nikita Chaudhary. So she is asking, is coherence like a resistance in quantum computer? And then she asked further that if it is not, then who does the work of resistance in quantum computer?
No, it is not resistance, it is facilitator. You see, if it is not there, you cannot gain any advantage or any speed up. Because I mean, even though this question is quite open, I mean, what is the power that quantum computer exploits, whether it is coherence or entanglement or correlation or something else, it is still, I mean, people are trying to figure out, but it is quite clear that in these class of algorithms that we know, starting from Shor and Grover and Joja, in all these algorithms, coherence and entanglement do play a very major role. So they are like fuel, they are not resistance, they are fuel to your quantum computer. So coming to your next question, that what is the resistance in quantum computing is the noise. Okay, if your system is not ideal, if there is some external noise acting on the quantum computer or quantum register, then your pure qubit will undergo decoherence. Okay, so you will not be able to maintain all your register in a perfect superposition of all these basis states. Okay, in that case, you have to deal with open system, and that is kind of resistance. Okay, so noise is actually a resistance your your ability to do quantum computing. Okay.
Yeah, I think these two are the questions.
Yes.
So, is there any other question? I don't see any other question in the chat box. So,
Dr. Bindya has one more question. She asks if it's possible to have absolute zero coherence.
Yeah. You prepare your system in all the qubit in 0, 0, 0, 0. That is zero coherence. Okay, by definition. Okay, because if you choose a basis, okay, and in that basis, if you prepare your system, that has zero coherence, because you say that in that basis system will display no coherence. Okay, right? Yes, the answer is yes. Yeah.
okay. Though we have a few minutes left, but since there is no other question, so let us thank the speaker for the excellent talk. And now we will break for about 20 minutes because we have saved 5 minutes here. So we'll assemble again at 11:45.
Okay, thank you. Yeah.
Okay, so then we go offline. Okay.
Hi, Bimlendu.
Hi, how are you?
Fine. So, how is life in Kolkata?
Oh, okay. You look slightly different.
Yeah, haircut and yeah,
Is it the effect of lockdown?
yeah, lockdown. Yeah, you don't go to saloon.
Okay. So we have 2-3 minutes left.
We have 1 minute left. Just 11:44. It's now. Yeah.
Are you able to hear me, Atiji?
Yes. Prasanji, I can hear you very well.
Hi, hi. So you look fine to me. Good, good. Nice to see you.
Thank you, thank you.
Yeah.
I don't know. My talk is very out of the topic in the conference. Out of the completely different like topic. Nobody
So you can.
unnecessarily he has put.
No, this is fine. This is.
How are things going?
Things are fine.
Fine, yeah.
Shall we start now?
Yes, please.
Yeah, thank you. Thank you, RP and Professor Panigrahi. Yeah, Bimlenda, you can start now.
Okay. Okay. So, welcome back to the first session. In this remaining session, we have 3 invited talks. The first talk will be given by Dr. Kenji Sujisaki from Department of Chemistry and Molecular Materials Science, Graduate School of Science, Osaka City University, Japan. He obtained his PhD from Osaka City University in 2006. His research interests include the molecular and electronic structures of open-shell organic inorganic molecules, theoretical methods for the study of open-shell molecules carrying unpaired electrons, quantum chemical calculations, quantum computing, electron spin science, and technology. He received 2019 Young Investigator Award from the Society of Electron Spin Science and Technology. The title of his talk is Toward Spin Symmetry Adapted Quantum Chemical Calculations on Quantum Computers. So with this brief introduction, I invite Dr. Sujisaki to present his talk. Thank you.
Okay, thank you very much. Can you hear me?
Yes, we can hear.
Okay, so let me share my slide. So thank you very much for kind introduction. I'm very happy to share my recent study on the quantum chemical calculation on quantum computers. And today I'm going to talk about how to utilize spin symmetry on the quantum chemical calculation on quantum computers. And this slide summarizes content of my talk. Because some introduction of the quantum chemical calculation on quantum computing are already given by Dr. Rubin in the first talk, in today's first talk. Anyway, so I would like to start some introduction on the quantum chemical calculation on quantum computers. And today I'm going to talk about mainly two topics shown here. First topic is how to determine the spin quantum number S on quantum computers. And second topic is how to purify the spin state on quantum computers. As you can see, this is a Schrödinger equation. Schrödinger equation is one of solving Schrödinger equation is one of the ultimate goal in quantum chemistry. But as last stated in 1929, the structure of Schrödinger equation is very simple, but in order to solve this Schrödinger equation, the equation becomes too complicated to be solved. So we have to introduce some practical, approximate practical method to solve. But in 1982, Richard Feynman stated that such kind of quantum mechanical element can be efficiently simulated by using quantum computers. And there are several types of calculation, but mainly two approaches have been investigated very well. One is quantum phase estimation approach, which uses time evolution wave function and obtain full energy. And second one is VQE, which is a quantum classical hybrid algorithm. And today, my talk is focused on this first approach, quantum phase estimation approach. And the basic idea of quantum phase estimation is based on the time evolution wave function. If we have a wave function which is an eigenfunction on Hamiltonian age, the time evolution causes phase shift depending on the energy. So if we can determine the phase caused by a time evolution, we can determine the energy by using quantum computer. This is a basic idea. This is a quantum circuit for quantum phase estimation. In this quantum circuit, first we have to generate superposition on 0 and 1 state, and then apply control unitary operation. Here, unitary operation is a time evolution operator, and then perform inverse quantum Fourier transformation. By measuring the qubit, we can obtain some binary digits here, which correspond to the phase related to eigenenergy. In order to apply this approach, we have to map the wave function onto the qubit. There are several approaches for the wave function mapping, but I'm using direct mapping. In direct mapping, each qubit stores an occupation number of particular spin orbitals. So it means if the spin orbital is occupied, the quantum state should be 1 state. If the spin orbital is unoccupied, the qubit state should be 0. In this representation, the Hartree-Fock configuration or single determinant configuration is represented by this kind of single quantum state. And CI type wave function can be represented by a linear combination quantum states. So this is a kind of entangled state. And the CI coefficient is corresponding to the coefficient on each quantum state. And in order to perform quantum chemical calculation on quantum computer, we have to transform the quantum Hamiltonian to qubit Hamiltonian, which is written by a string of pi operators. Because in direct mapping, we use the 1 and 0 states to be occupied and unoccupied. So it means we can transform the question and answer operator to something like this one, 0 to 1 and 1 to 0. But this question and anticipation operator should satisfy these anti-comic this relationship. If we define this operator like this equation, this question and initiation operator doesn't satisfy this relationship. So we have to apply this kind of Jordan-Wegener transformation, which consists of cubic transformation from 0 to 1 state and the probability arrays. And if we perform the quantum phase expansion based FSQT, there are two, basically, there consist of two parts on the classical computers and quantum computers. First, we have to generate initial gateway function. Usually, the Hartree-Fock wave function is used as the initial gateway function. And then calculate the 1 and 2 electron integral and transform the molecular Hamiltonian to cubic Hamiltonians. And then on quantum computers, the quantum state should be, wave function should be mapped onto the quantum bits, and then simulate the time evolution wave function and execute inverse QFT, quantum Fourier transformation, to regular Fourier energy. So in quantum phase expansion based FSQT, there are mainly two assumptions. One is Hartree-Fock wave function is available, and another is Hartree-Fock wave function is a good approximation of the ground state wave function. However, for large molecules like proteins, sometimes Hartree-Fock calculation doesn't converge. So application of quantum chemical calculation of quantum for such system is still an open question. And also the Hartree-Fock wave function is not always a good wave function, approximate wave function. Actually, in option molecule carrying ampere electron or spin beta, the overlap of the Hartree-Fock wave function and Fourier wave function becomes smaller. I will show you later. So spin symmetry adaptive approach is very important to solve such systems. And this is the potential surface of the hydrogen molecule. As you can see, this is a FSQT curve, and this is a restricted Hartree-Fock curve. And this is the overlap with the Hartree-Fock wave function and the FSQT wave function, square overlap. And as you can see, Hartree-Fock wave function is a good approximation of the ground state wave function when the system is close to the equilibrium geometry. But if we bond dissociate, the Hartree-Fock wave function, the overlap becomes smaller, and Hartree-Fock method is not able to describe bond dissociation very correctly. So this kind of optional system is not not just a reactor intermediate or an unusual molecule, but fundamental in chemistry species. As I said, the molecule under covariant dissociation generates the radicals, and there are many examples in material science and biosciences. So application of spin symmetry adaptive wave function is very important. And previously we reported how to generate the configuration state function, which is an eigenfunction or S-square operator. I mean the spin eigenfunction on quantum computers. By applying this approach, we can generate good initial gateway function having large overlap with the FSQT wave function. And also we reported another quantum algorithm to generate the much configuration wave function without performing post-Hartree-Fock calculation. Usually we have to perform post-Hartree-Fock calculations such as CAC-HF or CI to generate much configuration wave function. But in this study, I use the diagonal character, which can be computed from the occupation number of natural orbital from the Hartree-Fock wave function. By using such approach, we can generate good integer wave function having large overlap with the Fourier wave function along all bond lengths. And why spin symmetrical approach is very important in chemistry? Let me show you a very simple example. If you can see, oxygen molecule. Oxygen molecule is classic oxygen molecule is spin triplet, and spin triplet oxygen is necessary for life. But spin singlet oxygen, which is the first acidic stage, spin singlet with oxygen is one of the rare oxygen species and can be the cause of various species. So different spin state exhibit different molecular properties. So determining the correct spin state is very important for application of spin chemistry. So there are two fundamental questions arises. So first one is how to determine the quantum state obtained from quantum simulations. I mean, how to determine the spin state and how to purify the spin state obtained from quantum simulation is another question. So in quantum chemical calculation on classical computer, we usually calculate x-square value, expression value or x-square operator to determine the spin state. So how to extend such approach to quantum computers? So because the quantum phase estimation can calculate the eigenvalue of Hamiltonian, if we use the x-square operator instead of Hamiltonian and then apply quantum phase estimation approach, we can calculate the eigenvalue of x-square operator, which is x times x plus 1. And this is the best idea. So in order to apply such approach, we have to first we have to define the x-square operator in terms of pi operators. And first we have to write down the x-square operator in the standard form, and which can be defined as this one, which is the number operator of spin orbitals, and then this is the two electron acceleration operators. But in this one, we use another definition of the x-square operator, which is shown here, which consists of the NP spin, which is the number operator spin acting on the p molecular orbitals. So this means that if the p molecular orbital is open shell, it gives 1 as the eigenvalue. And this PQ is a permutation operator, which interchanges the spin between two molecular orbitals. So it means if the P and Q orbital has spin alpha electron, it doesn't change. And also beta case, it doesn't change the quantum state. But if the state is alpha beta state, it returns beta alpha state. In this definition, the number of the spin this permutation operator commutes. Only we have to uncommute operators pairs PPQ and PPR or something like this. So in this case, the time evolution operator of x-square operator becomes like this. And this part is somewhat complicated, but it can write down like this one. So in order to apply this approach, we developed another wave function mapping approach, which named as generalized spin coordinate mapping. In Jordan-Wegener, in conventional approach in Jordan-Wegener, the qubits represent occupation numbers. But in generalized spin coordinate mapping, the first qubit represents open shell or not. Whether the molecular orbital is open shell or not. And second qubit represents the occupation number of spin beta orbitals. Because in this square definition of square operator, we need the number operator of spin. So this mapping is very easy to handle such number operator of spin. In fact, the time evolution operator of the square operator can be written like this. And if we write down the quantum status for this operator like this, and this quantum status consists of 5 steps. And first, it transforms to direct mapping to general spin quantum mapping. And these 2 terms correspond to a number operator of 2 spin operators. And this part is the permutation operation, guys. And importantly, total, because these operators, number operators commute to other number operators and permutation operators, total decomposition is required only for these permutation operators. So I performed some numerical simulation for this time evolution operators using the spin eigenfunction and spin mixed wave function, using the Python program using OpenFrame and Circle libraries. And result is shown here. If we start from the spin single wave function, because spin single wave function, the eigenvalue of square operator is 0, so it doesn't evolve. But if we change the sign of this real combination to plus, it generates spin triple states, and this is a real imaginary part of the question. As you can see, the real imaginary part question oscillates, which corresponds to the phase shift caused by time evolution. If we start the spin mixed wave function, starting from alpha beta corresponds to the spin up and spin down configurations. If we start from alpha beta stage, and if we apply time evolution, we obtain beta alpha stage population, and then go back to the alpha beta stage. So it's kind of a Rabi oscillations. We also analyze the total decomposition errors by using 6 in 12 spin orbital models with randomly generated initial states with evolution time t equals 10. And this is the result. If we apply a Jordan-Wigner conventional Jordan-Wigner approach, the total error is very large. And also, this is the deviation from the exact square value. As you can see, if we apply a Jordan-Wigner transformation, the square value oscillates. But if we apply our approach, I mean the general spin quantum mapping, the overlap with the exact time evolution is very large, and square value doesn't oscillate. If we apply the standard order total decompositions, the error becomes smaller, but still, if we use the Jordan-Wigner transformation, the square value still oscillates a bit. So using general spin quantum mapping is very important to simulate this kind of operator, square operators. So let me move to the spin state determination using quantum phase estimation. And this is a quantum studies. First, generate the Agamal transformation to generate the superposition, and then apply control time evolution operation and Agamal operation and measurement. And there are additional terms. I will discuss later why this additional term is included. And this is the result of 2 spin systems. By changing the quantum circuit with changing the evolution time t. As you can see, if the second wave function is spin single stage, the measurement gives always 0 state. And this is the probability to obtain the 1 state in the measurements. And spin triple stage, the measurement outcome probability to obtain 1 state is changing by a time evolution time. And if we use t equal pi over 2, we can discriminate spin single and triple state by means of 1 qubit quantum phase estimations. This is a 3 spin system which consists of spin doublet or spin quintet case. In this case, the no such if the one spin state gives always the state and another spin state gives one state, we can discriminate two states deterministically. But in this case, no such good evolution time can be found. So we include another quantum gate, which corresponds to use the x12 minus xd plus xd plus 1 instead of the x12 operator in the time evolution. In this case, xd equals spin doublet. So xd equals 1/2. In this case, the time evolution of spin doublet state is cancelled out by using this key rotation operations. So spin doublet state always gives 0 states in the measurement. And spin quartet state gives 1 state or 0 states, depending on the evolution time. And if we use this evolution time, we can discriminate 2 states deterministic manner. So if we use these conditions, the x equals 3/2 state always gives 1 state, and x equals 1/2 state gives always 0 states. So we can discriminate 2 spin states by carefully choosing the time evolution time t and rotation angle eta in the above quantum search. So this can be used as a spin initiation operators. And this idea is shown here. If the initial wave function is concatenated by a other spin state, we assume spin concatenation is x plus 1 component. In this case, if we choose these parameters, the quantum state before measurement becomes like this one. And if we measure the one state, the quantum state is projected onto this quantum state, so we can annihilate spin concatenation. If we apply this approach to this kind of a function, which is concatenated, the target state is x equals 0 state, and which is concatenated spin triple and spin quintet states. In this case, if we choose these parameters, the quantum state before measuring becomes like this one. So it means if we measure the 0 state, we can annihilate not only spin triple and spin, but also spin quintet states simultaneously. This is one of the power of probabilistic spin annihilation on quantum groups. And in spin annihilation on classical computers, the spin annihilation operator x plus 1 is usually used. But if we apply this operator to this concatenation function, the result state is become like this one. So only the selective spin component can be annihilated, and regular rate of the x equals x plus 2 state will increase by this spin annihilation operators on classical computers, which causes some peculiar behavior, which the application of spin annihilation operator will increase the x square value. It's shown here. N nitrogen incorporated carbon 20, the x square value of the ground state, double ground state is 4.26 before the annihilation, but annihilation operation results in x square value become 13.14 or something. So, but if we use this spin annihilation operation on quantum groups, the quantum state before measurement is generally written like this one. So the relative rate of the x equals x plus 1, x plus 2 state will always decrease. And this is a numerical simulation. We apply the spin annihilation operation to the alpha beta state, which is a new composition of spin singlet and triple and quintet states. If we apply spin annihilation operators on classical computers, the x square value increase. But if we apply our spin annihilation operation on quantum computers, the resultant X-well value is 0.0045. So, and overall, with the spin single wave function very large. This small deviation from the spin single wave function is arising from the total errors. If we apply a total size, if we increase the total size, the X-well value decreases. And also, we apply this approach to 5 spin seconds. Again, the application of the spin isolation operation increase the X-well value, but if we apply a probabilistic spin isolation operation on the quantum computers, the quantum state becomes, the X-well value becomes smaller. In this case, the spin statistic is not isolated completely by single spin isolations. If we apply another spin isolation operation with x equals 3/2, the remaining x equals 5/2 component can be eliminated. And this is summary of my talk. And these results are already published in PCCP. Both of two papers are open access, so please refer these papers. Let me first, finally, I would like to thank all the collaborators and funding folks, and thank you very much for your kind attention.
Thank you very much, Dr. Sujisaki. And now the talk is open for discussion. I see there is a question from Sunik K. How do you take care of fermionic antisymmetry in direct mapping?
Okay, so let me move to the slide. Yes, so if we define the equation and anticipation operator by this equation, the fermionic relationship doesn't satisfy. Instead, in the Jordan-Wegener transformation, we use this kind of operation, which consists of this xp minus iyp correspond to the 1p 0p. And the additional power operator in C, power C operators, which is introduced to satisfy the fermionic antisymmetry.
Thank you. Is there any other question? I don't see any more question in the chat box. We have still 2-3 minutes left. So,
Linda, your watch is a little late.
oh, okay. Thank you.
It's already time.
So let us thank the speaker, Dr. Kenji Sujisaki, for the wonderful talk. Thank you. So now we move to the next talk. Our next speaker is Professor Prasanto Panigrahi from the Department of Physical Sciences, Indian Institute of Science, Education and Research, Kolkata. So he has been working at this institute since 2007. So before moving to this institute, he was at Physical Research Laboratory, Ahmedabad. He obtained his PhD from University of Rochester 1988. So before moving to IISER-K, he was at PRL for 5 years. His research interests include theoretical physics, quantum optics, quantum information, Bose-Einstein condensates, and nonlinear dynamics. So please note that his title of the talk has changed from that announced in the program booklet. So the new title is Exact Solutions for Quantum Droplets and Supersolid Phase in Quantum Gases. With this, I invite Dr. Panigrahi to present his talk.
I hope I'm audible, Vimanandu.
Yes.
Okay. So I'll be talking about exact solutions for quantum droplets and super solid phase in quantum gases. So this will be one space basically on a line, one space on one time. So I'm talking about a cigar-shaped kind of BC, and Bose-Einstein condensate has been routinely brought from 3 dimension to 2 dimension to 1 dimension through appropriate trap configuration. But as you realize, this quantum droplet, which was first proposed by Petro, the behavior, it is basically self-trapping. You know, the matter, this dipolar BC, where it has been seen experimentally, it is a self-trapping situation. There is no trap. So, and the behavior is very different in 3 dimension, 2 dimension, and 1 dimension. I'll be concentrating on 1 dimension. And as you know, the super solid phase has been, much sought after for quite some time. And the first paper was by, it was around 54, 55, if I remember correctly. I'll give you the reference. Since then, including liquid helium and many other systems, optical lattice, it has been seen experimentally. But here, I will point out that in this quantum droplet, in the self-trapping condition, it is possible to realize it. So, and let me tell you very strictly from the very beginning that, as we know, long range order in 1 dimension is not viable because of quantum fluctuation. So I'll be giving you a mean field solution, which will be strictly valid in a finite system. As you know, for example, these gases, quantum droplets, or these traps, where they have initially started, they have finite dimension. So when you really go to thermodynamic limit, the quantum fluctuations will destabilize it. So keep that in mind. Now, there are participants of all kinds. So therefore, let me start with super states of matter. So super fluid, we are all familiar. Then superconductivity, which leads to supercurrent. Now finding a lot of technological use. And then this was Gross, the same Gross-Pitavsky in 1957, pointing out the super solid possibility of a super solid. Okay. So then, his paper is just a 3-page paper, very readable, and using this Fourier transform property of the potential, he predicted that there could be in a super fluid phase a long range of diagonal order, and hence possibility of a super solid. So as a solid, as you know, for example, in a solid, we have a regular arrangement of atoms. So here one talks about similar kind of things in a super fluid phase, but please keep in mind that super fluid has a off-diagonal long-range order, and super solid is over and above that. And there are technical issues. I will give you the references that you can't, if you confine the atoms strictly to, like, in case of a lattice, super solid phase will not be realized, because that was the thing which led to a no-go theorem later, and which people pointed out that this kind of restrictions, if you remove, then there's a possibility. And so now in case of super solid, as you saw, and historically it has been studied starting from Landau, who actually brought in really these new concepts of two fluids model, and it was in the context of liquid helium, this lambda point. And so there was a superfluid component and a normal component coming because of the heat. And there was, the region the superfluid phase forms is breaking of a global U1 symmetry, where here the mean field equation or the original Hamiltonian, which essentially has two-body interaction, the kind of thing what you see in BC, is invariant under a global phase transformation. So there are two different phases where the ground state is invariant under this, which is the symmetric phase, but there could be a possibility that where the ground state is not invariant, typical double well type of potential, where the symmetry breaks. So below critical temperature, this U1 symmetry is spontaneously broken, and you have the supersolid behavior. And you can also look at, for example, density matrix, talk about top diagonal long-range order, which Yang introduced. Those are more complicated things. In a very simplistic language, in a double well potential, you have below a critical temperature, you are the particle is confined to one of the systems for a simple hypo theory, or lying on a circle in case of an object having U1 symmetry with the non-vanishing amplitude. that is your broken symmetry phase. Now, when you talk about super solid, then you have solid order, long range order. But this kind of order, one has to be very careful that if you're really talking about like point particle kind of confinement and delta function kind of thing, what we see in regular atoms, then you will find out that this will not be allowed. Okay. So, and that was the objection which I given reference here, Penrose and Onsager. They pointed out that if you have particle like a delta function kind of thing what we see in irregular solids, then this super solid behavior will not be tenable. So these results of Penrose and Onsager really led to suspicion of Gross idea, and for quite a while people are not persuaded. But then after that, the region was found out. And so again, Gross in 57 looked at both these things in a very unified way, very simplistic, simple-minded picture, looked at the property of this potential, and then pointed out the possibility of that. Now, people then investigated beyond mean field interactions. The one which people are in Petrov used is the so-called Li-Huang-Yang perturbative corrections, which is beyond mean field correction. So 60s saw a lot more results in this kind of thing, many of which people are familiar. So this was like the beginning. And very interestingly, I just found out that this Li-Huang-Yang, this beyond mean field correction, apparently was not really the due to them. This was already, the calculation was already existing in a classical 1885 result of a capacitor, where the mean field energy is the capacitor's real potential energy, and the boundary correction is this Li-Huang-Yang correction. It's quite amazing how physics gets unified. So now, okay, then later on, Lipschitz pointed out that the defects can form quantum crystals. And this is there's a very beautiful small book where all these things are described very nicely. Now, after Lipschitz's result, Chester demonstrated that you need a diffused matter wave density, namely not delta function kind of thing. And that diffused matter wave density rules out this objection of Penrose and Onsager. And therefore, people started really looking at it more carefully. This was a very nice result. Lipschitz's thing was JETP, 1969. Chester was physical review, 1970. And since then, a lot of results have come. Leggett is one of them. Okay, he pointed out the idea about this, rotational inertia, which experimentally, led to investigation of liquid helium. And for a while, it was observed that is some anomalous part. So people believed that liquid helium will see this kind of behavior. And but unfortunately, it has not been fully confirmed. But it has been, a lot of experiments have been done. Now, this rotational inertia really showed unusual kind of behavior, below 0.1 Kelvin, reviving the hope of seeing a super solid there. And this, there's a very nice review article by Kim in 2004. And okay, so now let me go to this first self-trapped fluid. So as we know that in case of Bose-Einstein and condensate, we have this short-range interaction, delta function interaction, which is the so-called mean field energy, psi dagger psi whole square kind of thing, which is positive. When it is positive, then there is BC. And if it is attractive, if you go to lower dimension, like on a one-dimensional thing, you can still have soliton kind of configurations, which themselves are condensate. But typically, we are talking about repulsive short-range interaction. Now, this Li-Huang-Yang correction is is negative in one dimension. It is negative. So this short-range interaction is repulsive, and this one is attractive. And only when they are present, as Petrov pointed out, you can actually have this self-trapped liquid. So, okay, now, and it was interesting. It is interesting because you can really go to ultra dilute lower dimensional liquids, which much more dilute as compared to physical liquids. And more interestingly, it has been seen experimentally in dipolar systems in very recently, 1819 kind of thing. So Petrov and later on Petrov and Strasik looked at it carefully. It's a PRL paper, 2015. So they took a dipolar BC, two-component BC, and tried to show under what kind of effective, the theory coming from this two-component thing can give rise to self-trapped quantum droplet. So please note that it is not that in the experiment you are actually using this beyond mean field correction. You are actually looking at a two-component BC and finding out the condition under which a similar kind of effect could be observed. So indeed, they showed that there is a window. So he showed initially, and later on shown more carefully with explicit results, which is given here, that there is a parameter domain when this system can mimic this beyond mean field correction with the mean field repulsive energy. So now you can see people who are familiar with BC, this looks like a soliton. Okay, this is the chemical potential, and but only thing is that this is a flat top. If you really plot it, the change comes around mu is equal to mu0, otherwise it's a flat top. So they emphasize on this flat top droplet nature, and it is 1A. Okay, so this spectromasterships, this is the second paper which does careful job and exactly finds out what is the chemical potential. And amazingly, this is a very simple thing. The people who are doing soliton physics, they are familiar with it, but people didn't look at it more carefully. So here the change occurs only around mu is equal to mu0. So anyway, how was it seen? You can actually see the experiment I will give you, 2016, which indicated the possibility of these things, that when you expand, normal cases, the gas spreads, and here it was not spreading. So, this pointed out that there is an attractive component of this cubic nonlinearity, confirming the calculations of Petro. Okay, so then later on, experimentally, people realize this phase and also the supersolid phase, not in this system, but in a dipolar system. So you people are more familiar, this. And how was it seen? This is BC, and this is this coherent supersolid phase where you see diffused matter but localized, and there is a superfluid component in between. Okay, and here you will find out that there is no superfluid component, but it is a droplet, individual droplets. There is no coherence. So this is like our ordinary. If you say so, it is like our ordinary solid, and here is the supersolid, and here is the Bose-Einstein condensate, and these are all realized by tuning the repulsive interaction. Okay, so it's a two-component BC. Now, okay, so in fact, 3 to 5 of the things are same. So more precisely, these are there is no atoms here. The whole thing is inside a trap. So this is the flat top thing I'm talking about, and this is the this is the superfluid phase. So super solid, there is matter in superfluid matter in between. These are actually ones where atoms are localized but no superfluid component in between. So these 3 distinct phases by tuning the scattering length. Okay. And so it is the repulsive interaction through which, and this is the experiment of both this group in Europe. And okay, and there are observations. There are 3 important experiments, and all of them on this dipolar kind of systems. So, the technique of probing it, one was direct, just like I have shown, probing the superfluid presence of superfluid here, no superfluid here, disjoint droplets. The other one was through collective modes. So there are these two systems in which it was seen, and this very beautifully, this Higgs and Boson modes were the ones which were seen experimentally, and that is how they confirmed it. So these are really clear signatures of collective modes. Higgs is our amplitude mode, Boson is the phase mode. So these are the modes. And it is quite interesting that you observe this, super sound. So this paper is a very beautiful paper who talks about this super sound, that we have this Bogoliov spectrum over and above these so-called phonons, which are the ones which confirmed the presence of supersolid. quite a beautiful experiment. So now we basically looked at the same theory as Petrov has given, pointed out that there you can have analytic solutions of the mean field equation. That is what I'm just briefly show you. So here, in case of Petrov, here is the repulsive term. We are all familiar with it. Repulsive is NLSE. So the psi mod psi is the one which is the beyond mean field correction. Attractive, repulsive. Now we are looking at propagating waves. In principle, k could be 0, chemical potential, because it is propagating x minus vt, and we are looking for a real function without loss of generality because the phase is here. So then, if you can, this velocity is related to momentum. Now, I would leave the mathematical calculations to to somebody who is interested to read from the papers. But first, if you see if there is instability or not, if there is a plane wave solution which is allowed, then supersolid will not form. So one analyzes something called modulation and instability to check that. So once it is done, we identify the parameter regime where this instability occurs. Then you look for the exact solutions. So since we are interested in the background, superfluid background, you start with the general solutions of this kind. So these Sn functions are generalization of sine, cosine kind of functions. So they interpolate this Sn, Cn, Dn. People who are familiar with nonlinear equations, they will recall these are called conoidal functions. They have been experimentally seen, for example, 95-96 atomic gases, where they were the excitations in the nonlinear media. Many, many nonlinear systems like ocean waves, you can actually create them. But there is a parameter called m is equal to 0. This flow is sine function. M is equal to 1. This tan hyperbolic. So these are amazing functions which relate between this tan hyperbolic, sec hyperbolic functions to cosine and sine harmonic functions. So if you substitute in that thing, you can check that indeed there is a exact solution where the background density is 1/3 of the uniform background, and amplitude is also related to a. So now healing length depends on both the complex delta G and G and also modulus parameter. Okay. So explicitly when you plot, you can see that there is a background density, and following their experimental thing, we plotted them in a box kind of configuration. So here are the density peaks diffused with a superfluid background in between coming from the background A. Okay. So, and then you change the so-called modulus parameter, try to see how the wave behaves. In fact, this modulus parameter determines the periodicity. So the supersolid phase has a period because Sn is much like sine, cosine functions where the periodicity is 2 pi. Here the periodicity depends on some integral called k. For tan sec, period becomes infinity. So the period changes. So you can actually check who controls that period. Now, okay. So compute the dispersion energy, dispersion relation to see how are we doing in terms of other phases. So indeed you find that the dispersion is somewhat close to this Bogoliubov kind of dispersion, but you can actually compute it analytically. Now, okay. So now this paper was communicated. There were some referee reports. So more fighting. So this thing is in progress, not completely accepted yet. But I can strictly tell you that in thermodynamic limit, truly one-dimensional system, quantum fluctuations will destabilize it, as is well known. So the result is strictly true in in case of a finite system. We have actually I will refer to my paper. We have more general solutions with chemical potential which is lower than that of the self-trapped Petrov solution. So now I'll go to another system where a similar kind of equation, as you know, nonlinear Schrodinger equation describes a variety of systems, and so that will be useful for describing dynamical phase transitions of photons. And this is a driven Kerr nonlinear system. So the same repulsive interaction in case of optics is called Kerr nonlinearity. So this again, a superfluid phase has been observed for photons in experiment. I'll show you, in the reference. So there we are trying to probe, since superfluid has been observed, what are the conditions under which supersolid can be seen. Okay. Now, familiar NLSC again? Okay, I have a few more minutes. So this is familiar, repulsive, chemical potential. Now here there is a source. Now, that is what, for example, if you see the experiment, they actually drive the system where they saw it. So we have put a source type of term. So so it will be strictly an out of equilibrium, close to equilibrium kind of system. I'll show you that there are two things possible. If you have a two-component thing, just like they have done, and which was seen also in the experiment, which showed photon condensation. Two polarization are like the two components, and you can actually have a equilibrium configuration where one dominant polarization will be driving the others. So it can have both interpretations. Okay, so now again you have to check modulation stability to see under what condition you can have a condensation. So indeed there are parameter domains. Okay, I will not get into details of here. So we can have this thing. So as I pointed earlier, let us look for some explicit solutions. So our paper will be shown in the archive where we have more general solutions, but I'm just giving you a sample one. So you, when you substitute the kind of transformations which I have used there, they are called fractional linear transform. In condensed matter, in nonlinear physics, they are routinely used. This SL2R, SL2Z kind of transformations. So they, in fact, they connect the nonlinear equations to the so-called conoidal waves, the Cn Sn functions. Previously, one I used is Sn, now I'm using Cn. Cn, m is equal to 0 is cosine, m is equal to 1 is sec hyperbolic. So you find the consistency conditions and you can exactly solve them. So when you solve it, you find very interesting thing that modulus parameter greater than half and half below half at two different phases. M is equal to half, you have the D which is 0. So it needs special attention. In fact, you find M is equal to half, there is a phase transition which we studied carefully. But here, you have to look at the density waves. And lo and behold, as compared to before, you can have waves where photon density is localized here with a background. Now, the experiment of Claire et al. Had seen it without a background. So we are proposing that if you look at driving as a function of driving, or you component the two polarizations, there's a possibility of realizing these kind of systems. Now we call it photon crystallization in the scale nonlinear systems. So okay, now this is more general solution, and one case there is no background, one case there is background, and there are interesting solutions where there is a bigger peak and a smaller peak, namely different kind of structures. So whole lot of explicit solutions which you can found. Okay, now I will not get into this rotor modes. So if you read the papers which we looked at formation of supersolid, they found out the rotor mode has a deep connection with the supersolid. Only when near the parameter domain there is instability involving rotor modes, you find formation of supersolid. So we are actually trying to check analytically. In certain cases, if we can identify, as you know, numerically rotor modes we can compute, but analytically we are trying to see. So it seems that the cubic quintic system where it may be possible. So I'll just show you some results, but there is, I will not get into details. But a power law kind of soliton which shows rotor mode type of behavior dispersion may be possible to look at it explicitly. So as I see, this is the one as I mentioned to you earlier. The 2018 paper clearly points out that only when there is a roton instability, a supersolid phase forms around this domain. So that was the reason. So this paper saw the experimental roton mode. Now here we do observe a similar kind of things. Okay, so I hope that this model also will give rise to this kind of supersolid what appeared in in case of bipolar DC. So main point is that nonlinear equation, which have been studied quite extensively, with modifications of other kind of nonlinearity and source, can describe a host of physics which are being seen in lower dimensional systems, cold atoms, and amazingly, in case of light, where it was seen by Claire at room temperature. So hopefully that will drive a lot of technology in future and new physics also, particularly collective modes. So I think I'll stop here. Thank you for your kind attention.
Thank you, Prashant, for the excellent talk. Now we can take one or two questions. So there is a question from India. It is, what is the order of nonlinearity in your system?
Order of?
What is the order of nonlinearity in your system?
See, chord nonlinearity is same. Psi star psi in the in the Hamiltonian, it is the same. Psi star psi whole square, just like in BC. And for the two component BC, one starts with this self phase cross phase modulation, just like optical fiber. But in a certain parameter domain, there is a expansion which allows you to come up with that psi mod psi kind of thing. So, but you start with cross phase and self phase modulation, namely psi star psi whole square kind of thing for both the components. So it is standard BC type nonlinearity.
So she has a specific question also. What were the blue and the red curves for psi mod square in your slide 30/3?
Okay. Slide.
If you can go 30.
30 or 31?
30 or 31. 30 or 31.
Okay. Okay. This one, no? Yeah.
29 she says.
29, right. This is the one, I think. 29, yeah. Okay. Now, in case of intensity, this is the intensity of photon. This electric field mod square. So in this experiment, they started with Maxwell equation, basically Helmholtz equation, and it was seen in some liquid observer, molecular observers. So I am talking about electric field. Psi here stands for electric field. So intensity here you see, here we are emphasizing a small peak which is coming here, which is getting enlarged. How this intensity peaks, you see both the things are lying here. One of them does not have a background. So that is like normal solid. Another of them, there's a background which is building up. That's the super solid. So goal was to see how the background builds up and how the relative intensity here changes. So that is the thing. One of them is a super, as a functional modulus parameter. One of them, therefore, is a super solid pole phase, which we call crystallization of light. And because here it is regular Maxwell equation in the paraxial approximation, which gives rise to a chemical potential. So you can't really call it quantum, but it is coherent. Amazingly, the coherence of light has been seen experimentally in various experiments. A lot more experiments have been done, including that of Phillips group very recently, 2018, showing that it is indeed condensation. And good thing is that it is almost at room temperature. Bindia, I hope you are okay.
Yeah, she says she got it.
Yes, got it.
And there is one more question. Yeah. Even on the YouTube, can you see that?
YouTube,
so maybe
no, I can't.
For you, how can we say that Li Huang Yang LHY term will be attractive only in 1D system, and on which factor the sign of LHY term depend?
Yeah, in fact, I am actually learning. I saw with the clarification in that I was mentioning of the capacitor calculation. Apparently, it was done by Lord Rayleigh. In context of capacitor, standard capacitor, the bulk energy is the mean field energy, psi star psi square. The boundary thing which takes away is negative. Capacitor, you can imagine, because of the symmetry, can be thought of as a one-dimensional system. And now in 3D, it is actually the things change, the sign changes. So I would really refer you to original paper of Petrov and Astrasik, very readable. And Mahomet also has a paper, very clearly pointing out what is the physical origin of the sign. But 1D thing, I am giving you a very heuristic argument, and the derivation, in fact, was taken from there. If you read Mahomet's paper, he points out it is neither Li Huang or Yang, it was done or much earlier. If somebody is interested, send me an email, I'll give you that reference.
Okay, this question was by Maitri.
Any more question?
No, this question, last question was by Maitri Pathak. I just wanted to mention.
Okay.
Okay, from Hartree Pratap. Okay, thank you very much, Prashant, for the excellent talk.
Thank
So
you.
now,
Thank you, Bhanu. Thanks. Yeah.
okay, thanks a lot. So we move to the next talk. The speaker is Professor Ravindra Pratap Singh, who is fondly known as RP among his friends and colleagues. He is at Physical Research Laboratory. He is a professor of physics. So his research interests include quantum entanglement, quantum space communication, multidimensional entanglement using optical vortices, using imaging and quantum cryptography, optical vortices and their properties, light scattering, nonlinear optics, etc. He obtained his PhD from Jawaharlal Nehru University in 1994. The title of his talk is Satellite-Based Quantum Communication, an extension of free space quantum communication. So with this brief introduction, may I invite you to give your talk. Thank you.
Thank you, Bimlendu, for the introduction. And let me start by thanking Vijaya Sahu for inviting me to give a talk in this conference, and congratulating Professor Bhanu Das for completing 65 years of very active and fruitful life. So I will start with acknowledgement in the beginning itself. So the work I am going to present, it's mainly by Ayan Biswas, PhD student, final year PhD student. Anindya Banerjee is a postdoc. Nizil Lal, he has also completed his PhD, now doing postdoc. Pooja Chandravanshi, she is engineer, BTech Electronics and Communication. And faculty, our colleague, GK Samanta, Gautam Samanta. And Yamvi Jabir, who has finished his PhD, now doing postdoc at NIST USA, and myself. So with this acknowledgement, I will do some advertising, because I see this is very off the track topic for the conference, and it's 12:30, more than 12:30 now, and orienting towards a new topic. Everybody, it's not. I don't think it's very prudent or advisable at this hour, lunchtime. Anyway, so let's go for some advertising. And Milindu, you can stop me after 25 minutes. I will stop there. Don't. So at PRL, we have started Quantum Science and Technology program approved by our council. So this is the, hope it works. So this is the website, recently developed website of our Quantum Science and Technology program. And here you can see our convener of the conference, Vijaya Sahu. Okay, so he's part of that program. And so they are, and this is an India I have talked about. This is Gautam Samanta. And this is Ayan, you can see, who have contributed to this work. Nijil is here, Uza is here. So you can see all those guys who have contributed to the work I'm going to present. And then one can go to research activities involving this program. So basically we have 5 groups here. You can see that. This is atomic physics theory. Vijay is leading. He is supposed to develop atomic physics codes for quantum computers now. He has to change his code, classical codes, for quantum computers. And that's what he's working on. And I hope that very soon with Sugisaki-san, he will have very good papers in the field. And then this is group. This is the lab where my students are working along with PDFs. And we are working on single photon sources, entangled photon sources, all sorts of entangled photons, hybrid entangled, hyper entangled, all those things. And this is Photonic Science Laboratory. This works on nonlinear optics, optical parametric oscillators, along with entangled photon sources and single photon sources. This is very resourceful lab, a lot of equipment, 3 to 4 femtosecond lasers, along with many other lasers. This is attosecond physics laboratory, unique in India, and they are working on ultra-fast process in atoms and molecules. and they are supposed to control the wave packet dynamics. So the kind of work you are listening under quantum chemistry, this is the group which can do experiment, that they can realize that kind of calculation or simulation in the lab. And atomic physics theory, you know Vijaya, and you have been listening the kind of work he does. And luminescence laboratory that works on defect centers in crystals. And as we know, defect centers are very important for quantum sensing and metrology. So these are the 4 groups. And now we can go to the talk. So this is the motivation. Basically, as you see the title, satellite-based quantum communication. It all started in 2015 when we put up a proposal to Principal Scientific Advisor to the Government of India in 2015. But alas, this is still not an officially approved project of Government of India. It's more than 5 years now. Anyway. So as you see this satellite here, and this can be LEO, low Earth orbit satellite, or MEO, medium Earth orbit satellite. It can be GEO. And from there, you receive photons at the optical ground stations at Earth. And you can see that this is basically a long distance free space communication. That is the title. So if you want to go for satellite based quantum communication, first you have to work on long distance free space quantum communication. So how one go for this quantum communication? You need a single photon source or entangled photons. You can use physical variables like polarization, momentum, time being. There are many other variables you can use, path and other variables you can use to encode your photon as a quantum state. And these, then you can make a key using these quantum states or photons or qubits. And once you have key, you can encrypt your information and you can do the secure communication. And single photon source are single photons or entangled photons. They can be communicated through free space or optical fiber. Both is possible. We'll be talking about free space mainly. However, with optical fiber and photon detector technology currently available, you can't have a very long distance quantum communication because fibers have like very good fibers. They have 0.2 dB per kilometer loss, and beyond few hundred kilometers, you can't do point-to-point quantum communication using fibers. So you have to go to overcome this limitation. One has to go for satellite-based quantum communication, free space quantum communication using satellites. So that is the motive to go for satellite-based quantum communication. This first demonstration happened in 2015. Okay, and this was in Matera Laser Ranging Observatory. So as I say, laser ranging observatory, this is the prerequisite for satellite-based quantum communication. You should have laser ranging observatory or optical ground station, one can call, to receive this quantum signals from the satellite. So that's what they did in this Matera Laser Ranging Observatory or Italian group. They had a retroreflector in the satellite, and they sent pulses, qubit pulses. You can see here, you have satellite laser ranging pulses for pointing and tracking. Then you have qubit pulses. Okay, qubit pulses are there, and they sent from ground to the satellite, which has retroreflector. And while reflected, when it was reflected from the satellite, it has on average, it has less than 1 photon per pulse. So they were sending these pulses, you see, on average, it had less than 1 photon per pulse. And that's how, and they received it on the ground. So that's how they showed that it's feasible to do quantum communication using satellites. And this was the basic setup. You have transmitter, ALICE at the ground, and receiver. You send, you need telescope, like to send direct your signal and receive the signal. This is CUDE path. The same telescope can be used for directing your signal, quantum signal, and receiving the quantum signal. And this is the Bob receiver part. Okay, and here you measure the quantum state, a polarization state. You can measure phase, whatever you want. So these things, and here you prepare your quantum state, Alice. 2-bit pulses you prepare. And it's not basically China, although we listen so much about China. It is Japan, which has credit of sending this macro satellite and showing that one can have quantum communication, quantum key distribution using satellites to the ground. And they launched this macro satellite they call Socrates. You can see the full name, Space Optical Communication Research Advanced Technology Satellite. They sent in August 2016, rather, they received the signal. They sent it earlier, they received the signal in 16. And this paper was published in 17. And unfortunately, it didn't work for very long. They could collect data only for 1 day. And you can see that, and this whole macro satellite, it has weight of 50 kg and size was very small, 5 units of cube, 10 by 10 centimeter cube, you say cube that. So it's a 5 unit of cubes. And this transponder, this was which was communicating to the ground. This is whole satellite weight, and transponder was very even smaller, 6 kg and size of 17.8. And they showed that you can have a qubit less than 5. And they were doing B92 protocol for quantum key distribution. And you have to have less than 4.8% qubit to establish the quantum key. And they could do that. So as I am telling again and again, you need to have telescopes with good aperture, 1 meter telescope around, and to receive the signal. So that's what they receive the signal, and then they measure the state, quantum state. Okay, two polarization states, B92 they were doing. Okay, these are the 2 states they sent from SOTA, and they measured in different bases, 2 bases, and established the key. Then second experiment, this 17, and it was done by Germany. Okay. They had laser communication terminal in the GeoSat, okay, AlphaSat. So they were trying to do, they had plans for laser communication, this classical thing, coherent communication. Coherent communication has a lot of advantage. You can annul the effect of atmospheric disturbance and all those things. So they were trying to set up this coherent communication using GeoSat, using laser communication terminal. It was there, and they thought that let's check the visibility of quantum communication using same laser communication terminal. And this is the transportable adaptive optics ground station. Okay, this one. So again, you have telescope here. So they prepared their state superposition of biphase, the shift, like superposition alpha and minus alpha state, coherent state they prepared, and then they sent it to the ground, and they could measure this quadrature components, X quadrature. As you know, you will have 2 quadratures when you do the measurement of coherent states. So they could measure X quadrature and variance, the mean and variance is within one certain wise unit. So that is basically the quantum uncertainty of the vacuum. So they could measure the quantum features of coherent states, which they transmitted from GeoSat, more than 36,000 kilometers. So it shows the feasibility of communicating quantum communication using with geostationary satellites. That's a great achievement. And Germany could show that normal DVQKD, BB84 and B92, they could do this with aircraft. So this is the optical terminal in the aircraft. This is the ground station, again using telescope. And 20 kilometers height, you see here, this is the 19.8 to 20.8 kilometer. And they could prepare the quantum states using this terminal, and they could measure ground. Now comes the China basically, and they have become leaders now. They have done all sorts of experiments using satellite-based uh, uh, quantum communication. So this slide shows that you can have long-range quantum entanglement distribution. This is Delinga and 1200 and Lysium. Okay, so you have to have entangled photon source, okay, and optics to direct that entangled photon source to the ground station, and then you have to have this measurement at the ground station. So that's what you need. Intercontinental also, they could establish this key distribution in Europe, Austria, and China, and they could do the conferencing, video conferencing using that key. So they have demonstrated you can have 7,600 kilometer this quantum key distribution, and you can have secure communication along such long distance. Okay, so they have done all sorts of experiments, BB84 entanglement based ECART91, BBM92 quantum key distribution, and they have almost all sorts of experiments, possible experiments one can think of. They could do that using satellite based quantum. And Singapore's nanosatellite is Spooky. And this is very small country, but doing very well when it comes to satellite-based quantum communication. In 2015 itself, they sent a very small satellite, nanosatellite. There they had this entangled photon source, and they checked it. It was working. Again, in June 17, 2019, they launched. This is Spooky 1, and they have very good data. They have collected very good data. This from Spooky 1. They showed that this is working fine, and they have verified entanglement. Like CHSS inequality parameter S, they got around 2.6, 2.7, something like that. And this Professor Alexander Ling, he's the leader of this program. And now they have planned, I will tell you, they have planned in 2023, they want to have this quantum key distribution with the ground station from a satellite. So as you see, this is 2018, but after that, only this is Spooky 2019 has come up, this mission. Others are still in the pipeline. So you can have, as you see this figure, very nicely made, you can have uplink or the downlink. Both you can have, or you can have retroreflector, as it told, this Matera thing Italy, you can send and receive at the same station. So all the possibilities are there, and so many, you can see so many countries are involved, along with China, Canada, Germany, already discussed, Italy, Austria, Japan, Singapore. So many countries are involved. So, and you can have uplink and downlink. Uplink, certainly you will see that most of the missions, they are planning for this downlink. Okay, so downlink, you get more signal. Of course, you can have uplink, and there are certain advantages, but it's feasibility. If you say feasibility of quantum key distribution using downlink, that is much higher, much better. So Canada is planning, like headed by this group is being headed by Thomas Genevian, and they are planning to have uplinking. So ground station, they will send the quantum states, and this will receive that. So receiving station will be in the satellite. And this is the 2023 plan. They are planning to work with Space Agency of UK, and they will be connecting to ground station in UK as well as Singapore, and that's their plan. Okay, they are planning for 2023. They want to have BB84, along with that ECART91 and BBM92 and quantum key distribution protocol. So what is task ahead for India? Verifying existing free space quantum communication protocols, okay, and developing new, more efficient, secure, and less resource intensive protocols. Ground station, as I'm emphasizing again and again, ground stations are very important. Till now, we don't have a single ground station in India. Although they are working, ISRO is working on that, but it's still it's not functional. So, and development and demonstration of free space quantum communication cryptography using satellite. That's the last stage, and this is again emphasizing the point for optical ground station. So that will be the outline of the talk. I will just show. Okay. So security of QKD, how you why this quantum key distribution gives better security. First thing. Um, so here you are using mutually unbiased basis. So if you prepare your photon in like one basis, like diagonal and diagonal, you can't say if you measure in another basis, mutually unbiased basis, you will get random result. You can't find out what is the polarization of the photon. It's same way if you prepare a horizontal or vertical and want measure in mutually unbiased basis, you can't. So this is basically this is one thing that provides the security. Other thing is no cloning theorem. So this is in quantum mechanics, you can't clone an arbitrary. Impossible. Okay. So that is another point, another property of quantum mechanics that provides the security to the quantum state which you are sending for communication or for the key, creating the key. And then you can put a bound like here, this bit error rate. This is for BB84. So here, if you put 11, you will have 0 here. Okay, this is a binary entropy S2. If you put 11% here, you get 0. So you can put a bound. So you will not get any secure key. So that's the advantage, which is not possible in a classical key distribution. Okay, presently which is being used. So this is a very famous slide for BB84. You prepare your polarization state in 2 of the bases. Okay, horizontal, vertical. This is a linear basis, and then diagonal basis. Okay, and randomly you prepare these 4 states and you send it, and then you measure randomly in 2 bases. Okay, here you are using a random basis. Here 4 states randomly and 2 bases here. And if you are then after transmission, they do the classical communication, classical channel. They use Ellis and Bob. They talk about the basis, which basis Bob has used, and if Ellis and Bob have, which state Ellis has prepared, which basis Bob have used. So if their basis is right, you see, you get the key. If this is the state sending, and this is the Bob measuring, and if Bob uses the right basis, okay, you get the key. Otherwise, you don't get the key. So this is called raw key. Once you establish the raw key, you have to calculate the bit error rate, and then you have to go for this error correction and privacy amplification to get the secure key. So this is the basic protocol. And what do you need basically for doing this kind of stuff? As I told, you have transmission channel, free space, or optical fiber you can use. You can use a single photon, have a single photon source. You can use entangled photon source. Same process will give you the entangled photon source. This one, NLO crystal and a signal idler. You can find out the entanglement. And you can use coherent weak laser pulses. And this is the most popular method to do the quantum key distribution, because you get the higher key rate. When you are using entangled photon source, still we don't have very bright entangled photon source. It has limitations. Around 1 million around you get entangled photon pairs. So that limits the key generation rate. Okay. And then you have to use detectors after source and transmission. You have to do the detection. So you can have avalanche photodiode, single photon detectors. And you can have PM tube also, not a problem. Sometimes they are much better, give higher key rate. You can use superconducting nanowire detectors, very high efficiency at different wavelengths. Even at quantum communication wavelength, they give very high efficiency, more than 90% you can get. And of course, this is for DV, discrete variable quantum key distribution. One can have, as I showed this Germany geosat thing, you can have continuous variable quantum key distribution also, where you measure the quadrature components. Okay, and there you use homodynamic and heterodynamic for this detection. So you can have different kind of attacks after this quantum key. When you do this quantum key distribution, um, you can have different kind of attacks on your key or on your transmission channel. So Alice, here you see preparing different sending after preparation of production, sending to the Bob. And Eve, this is called intercept and resend it, measures that and send it again. So this is very and if you have like
2 minutes left.
only how much time is left?
You have 2 minutes.
Okay, good. Okay, fine, no problem. So you can have different kind of attacks, and to I will just go fast now. So to avoid these attacks, protect your communication from these attacks, people come up with decoy state protocol. So you send some decoy pulses along with your correlation state which you are sending, and this decoy pulses, and then they did the analysis and provides the better security, and then because it's a better security, you can go for longer distances. So then we thought that instead of and this here in decoy state, you reject this multi-photon pulses where you have more than one photon. So we propose that coincidence detection protocol where we are going to use multi-photons also, and that increases the key because you are not rejecting those multi-photons, and this adds up to the key, and we have shown that you get the higher key when you are using this multi-photon pulses. And we have done the experiment, and this is the theoretical and experimentally observed very good match we get these coincidences. So we showed that you can go for higher distances using this protocol, a coincidence detection protocol. These are the results. Basically, you can go for a higher mean photon number, you see, and two, more than two, and you can get a very high secure key along with longer distance. So this is the B92 result we have done in the lab. We have BB84 result also. I will not go for that. And the beauty of this quantum communication, you see, as I was emphasizing, the moment you go above the bound here, as I told, for B92, you have bound of 4.8% error rate. And here you see qubit going above 4.8, you can reject that, and other keys which you are getting you can accept. So that's the beauty. Same way you can do for BB84. Then what we have done, we have entangled photon source we have prepared in the lab, very compact. This is 10 by 10 centimeter, and you can have 10 power 6 million photons, million photon pairs, entangled pairs. We have verified the entanglement, a very good CHS parameter. Yes, you see Bell parameter 2.63, it's working fine. And then we have generated hybrid entangled photon source. They are very good for communication, because if you lose 1 degree of freedom, you can have in other degree of freedom your information. Okay, you can always get. So we have generated hybrid entangled photon source that uses this polarization along with orbital momentum of light. And this along with ISRO team, we are working on this satellite payload and ground station. Okay. And this free space link also we have developed in PRL. This is the two stations, transmission and reception, these two cabins. And here we have putting mirror to increase the distance. From here we will transmit, and this reflected and this will be received. So that we planned in summer, but because of this pandemic, we could not do. And in fact, after March, we could not do anything substantial. All the time there is some problem. Somebody is having some fever or something. Everybody is getting isolated. So it's really bad. We don't have resources, also money. We can't buy even 1,000 things. Okay, we have to wait. We have to write notes. So it's really bad. Don't know when it become normal. So this is basically at around 150 meters. This mirror you put, you transmit, reflect, and receive. Okay, so that's what this channel we are working on. So maybe in this winter we will have, and this is the implementation plan phase. These are 4 phases as I discussed earlier also. So these are the 4 phases to go for this satellite-based quantum communication. Hope we will get sometime in 2023-24. So this is the conclusion. Okay, and thank you for your attention.
Thank you very much, RP. So maybe we can take only one question. I don't see any question.
So there are 2 questions.
Good.
So let me read out from YouTube.
Okay.
Share.
For YouTube.
Yeah.
Okay.
So Kotagiri Ganga Prasad, he is asking, can you please share your opinion why India is still behind in all research areas like quantum communication satellites?
That they should ask policymakers, not me. We have been asking. I'm not a policymaker. I'm just simple researcher. Okay, sitting in my lab and office. Okay, this is I don't know. Basically,
Okay.
it's basically
So another question by Mr. Binit Kumar. He is asking, is the information encoding at the source side, for instance, hello with help of 0110 ... ASCII codes, done with the manipulation of polarizer selection at the source side or by other way?
you prepare source side and then you send it and then you detect at the other end. That's all. It's a very simple scheme, not very complicated. You are using quantum mechanics properties, and that ensures that your communication is secure.
Okay,
That's
so
the
there is
only thing.
another follow-up question by the same person. Kindly explain the message encoding with the help of BB84 protocol.
Once you get, as I explained, BB84, once you generate the key, secure key, then you can encode your message using this key, which is secure. Okay, which nobody else knows, only sender and receiver know, and then you encode the message and send, because your key is secure. Securely you have distributed. You have distributed. Your distribution was very secure. So key nobody knows except a sender and receiver. Then you encode the message and send. So that's how you ensure the security of your message.
Dr. Dev.
Okay. Thank you very much. So this brings to the end of this session. So I once again thank you, RP, for the exciting talk and
Thank you, Bimlendu.
telling us
I could see you
about the
at
development
least online.
in space. So over to Vijay and other co-hosts.
Yeah, sure. So I'll take this opportunity on behalf of all the organizers to thank Professor Bimalendu Deb for chairing this session. So thank you, and I'll see you all. We'll see you all after the lunch break at 2:30 Indian time.
Thank you very much.
Thank you.
Okay. See you.
See you.
Oh.
Hello, Professor Srivastava.
Oh, I don't know. My name is not coming.
The user.
Yeah, I can rename you. That's not a problem. I'll just do it.
Okay.
Yeah.
What name should I give you?
Just Rajesh Srivastava. You want to change my name?
I
I
can't.
thought maybe some fancy name
cannot.
you wanted to use or something. Okay, so how are you? Yeah,
Yeah, fine. I think you all are very busy. Can you see me and hear me?
Yes. I see the first speaker is also here.
Okay.
Front. Yeah.
So what about other participants? Yeah, 11 participants are there. So
But lot of participants are in YouTube with us.
YouTube. Okay. Yeah. So should I begin now? Or wait?
Yeah. Sure. Yes. Okay. Okay. So hello, everyone. I welcome you all to the afternoon session. And I take great pleasure in introducing the chair for the coming sessions, Professor Rajesh Srivastava. He's an emeritus professor from Indian Institute of Technology, Roorkee, India. He works on a host of topics that include but are not limited to plasma diagnostics, plasma modeling and simulation, electron impact ionization, alignment and orientation of atoms and ions, autoionization, atomic and molecular calculations, relativistic and non-relativistic, including atomic ions and so on. And his honors and awards include, but again, obviously not limited to UGC Career Award in Physics 1994, Senior JSPS Fellowship Award 2002, and co-opted member PAC DST Physical Sciences from 2018. So it's an honor to have you here, and I request you to take over. Thank you.
Thank you, Prasanna, for kind introduction. So, and I thank Professor Sahu, Bindia, and organizing committee to ask me to chair this session. It's my pleasure. So I begin this session. Is it okay now?
Yes.
Okay.
Yes.
Okay. So good afternoon to all the audience. And we have in this session the first speaker, Tron Soya, Laboratory of Chemistry and Quantum Physics, CNRS, University of Toulouse from France. As introduction, Trond wrote a book, Principle and Practice Molecular Properties, Theory, Modeling and Simulation from Wiley 2018. He is co-author of the Dirac Code, and also there are many achievements he had. So this would be enough to the audience to identify him. His title of talk is Semi-Classical Light Matter Interaction in a Relativistic Perspective. So I request Professor Soya, am I pronouncing correctly, Professor? Your name? Hello?
Yes, it's Trond Soya.
Yeah, Trond Soya, right?
Yes.
Okay, so please take you can begin your talk now.
Okay, so how do I start my video?
You can video and
Ron, you have to share your screen.
I have given you, I've requested you.
Okay, now it's fine.
Yeah, okay, great. Great to see you.
So now you can see my screen, I hope.
Yes, we do.
Yes, okay. So first of all, I would like to thank for the invitation. I'm very honored to speak on this occasion and send my warmest greetings and regards to Professor Bhanu Das. I would also like to thank my co-workers. So Nonna List, who's a postdoc at Stanford. Then I had two master students, Timothy Melin and Martin van Horn. And on this occasion, I've chosen to talk about the light-matter interaction based on work that was published earlier this year. So I'm in the
Ron, sorry to disturb you. May I request you to put your camera a little down because your face is not seen. Yeah, it's now fine.
Thank you. I hadn't checked. So I'm a relativistic quantum chemist. And when we want to sell relativity in chemistry, we often point out that without relativity, gold would have the same color as silver, that mercury would not be liquid at room temperature, and that your car would not start, at least if it has a lead battery. But today focus is on light-matter interaction. For here, relativity is also crucial, as you will see. So I will start by considering linearly polarized light, where you have electric and magnetic fields given by these formulas. And that are typically represented by potentials, the scalar potential 0 and a non-zero vector potential. And important in the following is that we have a wave vector k of length omega over c. C is the speed of light, omega's radial frequency. It can also be written as 2 pi over lambda, the wavelength. And we also have a polarization vector epsilon, indicating the length of the electric, the orientation of the electric field. And so the wave vector forms the right-handed axis system with the electric and magnetic fields. So now I want to couple this field to my molecule, my particles more generally. And for this, we use the so-called principle of minimal electromagnetic coupling to introduce the potentials into the Hamiltonian. This gives an interaction Hamiltonian of the following form, where we see the charge density coupling to the scalar potential, and then the current density coupling to the vector potential. And this can be written on manifestly relativistic form in terms of the 4 current and the 4 potential. So this is a manifestly relativistic coupling. But yet it is used also in a non-relativistic setting. Interestingly, this coupling was introduced in 1903 by Schwarzschild, so 2 years before the annus mirabilis of Einstein, where special relativity was introduced. So this principle of a minimal electric coupling, sometimes also denoted minimal substitution, you find in many papers and textbooks, but usually without any reference. In 2001, I was writing a book chapter, and I started wondering where this term came from. And it turned out to be a long quest. So finally, Chirumachandrian, a colleague, suggested that I should look up this paper by Murray Gell-Mann in some conference proceedings from 1956. And here, indeed, you find this term. The quest had been long, so I wanted to be sure that this was actually the first reference. So I found the mail address of Murray Gell-Mann, and I wrote him. Dear sir, allow me to ask you, are you the originator of the principle of minimal electromagnetic coupling, a term found in a multitude of textbooks and papers, but never with any reference? And surprisingly, I got an answer rather quickly. So it says, Dear Trond Save. Yes, Murray Gell-Mann. So it's a minimal answer. So as I said, this coupling is used both in a non-relativistic and relativistic setting. So if you start from the free particle non-relativistic Hamiltonian, this is the usual form with the p squared, but we can also express it equivalently in terms of the Pauli spin matrices. Sigma dot p squared is p squared. And if we now plug in fields through the minimal substitution, we get these additional terms, and the blue term, so the spin Zeeman term, you only get if you have this second form of the Hamiltonian. Usually in spectroscopy, we will ignore the diamagnetic part, and at least starting from a closure system, we will also typically ignore also this spin Zeeman term. In the relativistic Hamiltonian, if we perform this minimal substitution, we get only linear terms in the potentials. So we don't get something that apparently looks like a diamagnetic terms. If you wonder about this, you can check out this reference. So let us go to the heart of the matter and look at some experiment. So we have a sample cell here. And let's have a look inside. So we'll start with the interaction of red light with a benzene molecule. So here we see our axis system, the wave vector. We see in red the electric field, and in blue the magnetic field. But where is the molecule? Well, in fact, we have to zoom quite a lot. We have to magnitude 200 times in order to see the benzene molecule. And this is the basis of the electric dipole approximation, because this benzene molecule effectively sees only a uniform electric field. General formula for the absorption cross-section is given here, where this T is an effective interaction operator. Here I show the relativistic form. We see that we have an exponential with the wave vector and the radius vector. And if their product is very much smaller than 1, we can ignore this exponential, replacing it simply by unity. And this leads to this form of this effective interaction operator. So we saw that K was related to inverse wavelengths. So this electric dipole approximation is evidently something that is valid when the molecular dimensions are much smaller than the wavelength. From this operator, it's not evident where the word electric dipole comes from. But if we use the Heisenberg equation of motion, it shows that the commutator of the position vector with the Hamiltonian is equal to the velocity vector. And in the relativistic domain, the velocity vector has this curious form, C alpha. And so by using this formula, we can make an equivalence between transition moments, so not the operators, but transition moments, in the so-called velocity and length representation, where the length representation has a dielectric dipole operator. So this velocity and length representation are sometimes termed gauges, so velocity gauge, length gauge. I would rather prefer to use the word representation. This is because when we talk about a gauge, we typically impose a gauge condition. So for instance, in Coulomb gauge, that the longitudinal part of the vector potential should be 0. So the divergence of the vector potential is 0. There is no specific gauge condition associated with this velocity and length so-called gauges. So I prefer the word representation. And this relation that we see here can be traced back at least to the first edition of Dirac's book on quantum mechanics. Now let us turn to the X-ray domain. So we're still going to have a benzene molecule, but now the wavelength is significantly shorter. So now we can actually see the benzene molecule in our experiment. And now we could question the validity of the electric dipole approximation. If we want to go beyond the electric dipole approximation, the usual procedure is to retain the first order term in the expansion of this exponential. However, if we just plug this into our formula for the absorption cross-section, we will discover that we have origin dependence. So the intensities will vary according to where you place your molecule in the coordinate system. Now, of course, this is not physical. There was a seminal paper by Bernadotte, Atkins, and Jacob that showed that this expansion in wave vector should not be done on the interaction operator, but on the observables. So either the absorption cross-section or oscillator strength, which is proportional. And with this, you get origin independence. However, it was then pointed out by the group of Xiaoshong Li that you could get negative oscillator strengths, and this is not physical. So this was observed in this molecule, titanium tetrachlor, in a ligand K-edge simulation. Then the group of Roland Lind also looked into this. In one paper, they suggest that this could be a basis set problem. In another one, they are pointing out that here we're just at the second order in the wave vector, and maybe higher order contributions are missing and could make the oscillator strengths positive. I shall show that we can now answer this question. So we have seen that this paper from the group of Christoph Jakob in principle gave a way to have origin independence, but there are some problems. So we propose an alternative approach that I call the full Monty, which is simply that we include everything. So we have the full molecular light interaction. So this was first done in a non-twisting setting in the paper I show here. In the second paper, we introduced a mixed numerical analytic approach for rotational averages, since experiment is typically isotropic. And there has been done similar work along these lines using full molecular light interaction by the group of Roland Lind. Today, I want to talk about the relativistic extension of this. And very importantly is that everything becomes very, very much simpler. So the relativity is the right setting for this. So this is published in this paper. And we have, in fact, three schemes. We use the full semi-classical light matter interaction operator. Here we have this same mixed analytic numerical approach. So we have to average over three angles, two angles that indicate the position orientation of the wave vector. And then we have to next indicate the position of the polarization vector in the plane perpendicular to the wave vector. So that introduces a third angle. We can find an analytic formula for the average over this third angle. But for the wave vector average, we use a numerical approach using the Lebedev angular integration. We also have schemes where we have a truncated interaction. And in fact, we can do this to arbitrary order, technically using recursive loops. So here we see a long formula for the absorption cross-section to the order 2n in the wave vector. Only even terms are non-zero. I'm using Einstein summation convention. So we have summations over PQ. So these are components of the polarization vector. And then we have indices J1 all the way to J2n, where we have here components of the wave vector. And here we see we take the real part of this product of transition moments. We have some operator to the order n plus m, and an operator to the order n minus m, and we have also the line profile. So this operator have two forms. So either we have taken the full interaction operator, and we take out the here the term which is of order n in the wave vector, as you can see here. So this is what I call the velocity or generalized velocity representation. We also have so-called multipolar gauge, what I would call the generalized length representation, where Q is an electric multipole operator of order n plus 1, and M is a magnetic multipole operator of order n. And here, in fact, we are fully analytic rotational averages. So this is our closed analytic forms. So let me say a little bit about multipolar gauge because it may not be familiar to everyone. I previously showed this form of the interaction operator, where we see that when we want to include fields into a Hamiltonian, we do so through the potentials. Can we do it directly in terms of electromagnetic fields? And the answer is, in fact, yes. And this is the so-called multipolar gauge. So what we do is that we choose some expansion point, I will call it A, and we simply do a Taylor expansion of these potentials. So this is what I showed here. And so we evaluate this at the expansion points, these derivatives. Then we know that we have these formulas for the electromagnetic fields in terms of potentials. And we see that we have a gradient of the scalar potential. And we also are taking derivatives of the scalar potential here. So we can now replace these derivatives using this formula. This will lead to this form where we have the value of the scalar potential at the expansion point. Then we have these terms, this expansion in terms of the electric field and its derivative at the expansion points. And then a second term, which is a time derivative of essentially the vector potential and its derivative at the expansion point. And we want to get rid of this term, the second term, because we want to get rid of the potentials. And we can do so because we can recognize that this is in fact has the form of a gauge transformation. So we can simply delete this second term. Of course, then we have to carry out the equivalent or corresponding transformation on the vector potential. If we do so, we get an expression for the vector potential in terms of the magnetic field and its derivative at our chosen expansion points. So here we are, we have now eliminated the potentials from our expression. This one can always be shifted to 0. So having eliminated potentials, we could then think that we have now eliminated gauge freedom. This is not true because, in fact, the gauge freedom is now essentially the choice of the expansion point. Of course, in atomic physics, there is a very natural expansion point, the origin of our atom. Not so in the molecular domain where I work. And in fact, you can show that potentials associated with different expansion points are indeed connected by gauge transformations, but only if this expansion is not truncated. And in fact, in this multipolar gauge, this origin independence is not assured, as we can see from numerical calculations. Now, the very nice thing about the multipolar gauge is that if we plug these potentials into our Hamiltonian, we get immediately a multipole expansion. So we see multipolar operators. So this is the electric multipole times the derivatives of the electric field, the magnetic multipole operators times derivatives of the magnetic field at the expansion point. In the relativistic domain, these are the formulas or expressions for the operators. This is basically the same as we have in the non-relativistic domain, whereas in the for the magnetic multipole operator, we are very much helped by the fact that the current density operator has a very simple form in the relativistic domain. So we have, in fact, implemented these operator forms to arbitrary order. So if we were to do the same or try the same in a non-relativistic domain, it would be much more complicated. You can see that the expression for the non-relativistic current density is very much more complicated. Let me just compare now these generalized velocity and length representations. So this is the form of the interaction operator in the velocity representation. And for this one, we have origin independence, even if the interaction is truncated. So this we can show analytically, but also we see it numerically. In this multipolar form, we don't have origin independence, but we have the nice feature of having a separation between electric multipole parts and magnetic multipole parts, so we can see how these contribute. Is it possible to go between these two forms? In fact, it is. You can use this formula, which will transform this velocity representation into this form. So here we have, in fact, in red, what would be the equivalence of an electric multipole operator in the velocity operation representation. And this is the magnetic form, magnetic part. And this form is very interesting because now we have both origin independence and we have this separation of electric and magnetic multipoles. If we want to go all the way from this form to the full length representation with the normal electric multipole operator here, we have to use another formula that involves a commutator with Hamiltonian. And in fact, this indicates that we're doing a gauge transformation. So you will then get this form. And now, in order to get equivalence between the length and velocity representation, we have to form transition moments. So this is what we see here at the end. So I think in the interest of time, I will skip this part. I just want to show you some results. So here we're looking at the valence spectrum of the radium atom. So we essentially have an excitation 7s to 7p. And what I have traced here is the oscillator strength within the electric dipole approximation. Now I go beyond the electric dipole approximation. And in fact, you basically see no difference. So this simply shows that electric dipole approximation is perfectly valid in this UV domain. However, if I go now to the X-ray domain, so now I do the K edge, so I'm exciting from 1s to essentially 7p. Now we will see a difference between electric dipole approximation and the full interaction. We can see that these peaks are changing a bit, and we also see some new features here. So these peaks are associated with transitions to P1/2 and P3/2. And these new features are electric dipole forbidden transitions to 6D. Now let us look at this molecule for which the group of Xiaosong Li found negative oscillator strengths. So this is the spectrum for this ligand K edge transition. So we're exciting from chlorine 1s to the vacant titanium 3D orbitals. And again, if we go beyond the electric dipole approximation, we get this picture. And so basically, we don't see any difference. But in fact, in this case, we don't see the change because it's hidden by the finite line width that we have imposed on our spectra. I should point out that the spectrum has two parts. So I mean, the ligands span in TD symmetry, the T2 and A1 irreps, whereas the 3D orbitals span the E and T2 irreps. And I will focus now on this part because this was the part that was studied by the group of Xiaosong Li. So let us now look at transitions in this part of the spectrum. Here I'm using the full light matter interaction. So here we have the oscillator strength, but you should multiply this number by, you should multiply these numbers by 10 to the minus 3. So we can see that we have oscillator strengths to all these three final states. If you go back down to the electric dipole approximation, now in the velocity representation, then we can see that it's only this transition to the singlet T2 that is allowed. So in fact, we don't see it on this spectrum. but there is a redistribution of intensity, although they basically sum up to the same number. Let us now see what happens if you go to higher orders in the wave vector. So here we were at 0th order. If you go to second order, so we're accumulating to second order, you can see that now we indeed get this negative oscillator strength observed by Xiaosong Li and co-workers. So this is not good. This is not physical. However, we can now, as I think the only code I know, go to arbitrary orders. So let us just crank up orders. We go to 4th order in the wave vector. And you can see that it now fixes the negative oscillator strength we had here. But now we suddenly have negative oscillator strengths in these two other, for these two other final states. We crank up again, so we are now to 6th order in the wave vector. We are accumulating. And now we can see that now things are fine here, but now we suddenly have a negative oscillator strength for the singlet T2. We go to 8th order. Now we have positive oscillator strength as we would like, and we can continue. And you can see that slowly these oscillator strengths are converging, and they are converging to positive numbers. But it is really problematic that the convergence is so very slow. And it's going to get worse. Let us now look at excitations of the radium atom. So I will first look at excitations from the 7s1/2 to 7p12. So now we're in the UV region where we were expecting the electric dipole approximation to be valid. And here we are at 0th order. So here we have the contribution to this particular order when I have these square brackets. Here I'm accumulating. And you can see that the contributions very quickly become very small. So essentially we have the same oscillator strengths to any order. So this simply shows that the electric dipole approximation is fully valid for this transition. Now I turn to the K edge, so I'm exciting from the 1s. And to 0th order, we have this oscillator strength. And now when I crank up orders in the wave vector, we can see that we have significant or reasonably significant contributions to 2nd order. Now we suddenly get a bigger contribution. And you can see that here things apparently go really wrong. We get some negative, very large oscillator strength. And you can see it simply explodes. So this looks really bad. So what is going on here? Do we have some numerical instability, or is there some fundamental flaw with this multipolar expansion? So let's peel the onion. Let's try to get to the bottom of this. So the oscillator strengths are in practice calculated from a solution vector to an excitation energy equation times a so-called property gradient, which is contains the interaction operator. So this, if we sum up to give an order these property gradients associated with this truncated interaction and compare this to the full interaction, we see that we have still the same problem, that this appears to blow up. And here we're going down one step deeper to the underlying AO integrals. We're using Gaussian basis functions. So these are, in this case, Cartesian Gaussian functions of the py type of some exponent alpha 1. And we're looking at how this sum over truncated interactions converge towards the full interaction. Here we can devise analytic expression. So this is what we get. It's equivalent to this. And we see that this is the number we want to find. This is the full interaction. And here is the sum over orders. And to make a longer story short, we find extremely slow convergence. So in fact, for this k edge, this sum, you have to go to m equals larger than 10,000 to get convergence. So it means that you're at order 20,000 in the wave vector. So we find that all these integrals and everything is completely robust. It's just that for highly energetic excitations, this multipolar expansion simply has it converges, but at an extremely slow rate. For the 2s to 7p excitation, we converge at m equals to 240. So this means that we're basically at order 500 in the wave vector. So of course, this is not practical. So I will just very quickly show you that we can also do circularly polarized light with full interaction. And this will allow us to simulate electric circular dichroism. So in the absorption cross-section, we have this formula where we have epsilon times some transition moments involving the effective interaction operator. The differential absorption cross-section, so the difference between left and right-handed polarized, circularly polarized light, can be given this form, where EK is the unit vector describing the wave vector. And interestingly, we don't see any polarization vector here because we have axial symmetry, whereas here, the polarization vector indicates the orientation of the electric field. So this, of course, will simplify the rotational averaging. And this has now also been programmed up. So I will just terminate by showing very quickly some spectra. So this is the H2S2 molecule at the dihedral angle of 87. So the molecule is now chiral at this dihedral angle. And we are looking at different frequency regions. So here we are in the valence region, and we're going down all the way to K edge. And K edge, or electric circular dichroism, in the X-ray region has been proposed for the determination of absolute configuration. That can be particularly interesting when you have multiple chiral centers, because then you get complicated signals, but with K edge, or in the X-ray domain, you can go in and excite only selected core orbitals, so selected centers. So to sum up, we have developed 3 approaches for going beyond the electric dipole approximation in relativistic framework. So we have the full interaction, and then we have truncated interaction. So either in this velocity representation or using multipolar gauge, and also show that you can have some intermediate form where you have sort of the best of both worlds. You have the separation into electric and magnetic parts, but you also have origin independence. And we have general expression to all orders, including rotational average. And I don't think this can be done in a non-relativistic setting. And we have seen that you can get extremely slow convergence for highly energetic excitation energies. We can also use circularly polarized light. And we are now ready to explore the validity of the electric dipole approximation in a relativistic domain. So with that, I would like to thank you for your attention.
Thank you, Professor Transa. May I request Professor Rajesh Srivastava to...
Yes. Okay. So finish the talk. Thank you, Professor Soe, for an interesting talk. Are there any questions for this talk?
Yeah, there are. Prasanna, can you read
there
it?
are questions.
Yeah, sure. So there's a question from Jobin Jos. He asks, how do you include many electron correlation effects? Will not the correlation effects be more important than the effects due to the higher order interaction terms in the photon energy range?
So in these calculations I showed you right now, we have done time-dependent DFT. So I mean, we have electron correlation included. We're also at the moment preparing implementation of this at the equation of motion couple cluster level. So when going to higher interactions, to higher orders in the wave vector, remember that some transitions are simply electric dipole forbidden. So you don't see anything unless you go to these higher orders. What is sort of a reasonable order for a truncated interaction remains to be explored. What is nice about using the full interaction is that it's not particularly complicated, but we are sure to get the full interaction, everything, so the full signal.
Okay. It looks there are no other comments. So let's thank once again to Professor Soya for very interesting talk.
Thank you.
Thank you very much, sir. Okay. So next speaker is Professor Rahul Maitra from Department of Chemistry, Indian Institute of Technology, Bombay. His research interests are many-body quantum chemistry, development and application of novel molecular methods. The title of his talk is Coupled via Nonlinear Dynamics. And Professor Maitra, can you
hear me?
take up your, yeah.
Can you hear me? Oh, okay,
yes, I can hear you. So, okay. Is it, you can hear me also? Okay, so I invite you to deliver your talk. The talk time will be 25 minutes and then 5 minutes for the questions.
Yes.
That's okay to you? Okay.
Thank you. So the title of my talk, as the chair has already said, that it's a coupled cluster theory. I'm trying to solve a coupled cluster theory in reduced dimension using the features of nonlinear dynamics and some features of the machine learning. So this is a very recent work that we have been doing for some last, say, 6 months or so. So most of the parts of this work are pretty much at its infancy. So let me see how it unfolds. To start with, let me have a full screen mode. 1 second, please. Okay, yeah. So first I give the coupled cluster theory in a nutshell. And as most of you know, that it's an electronic structure methodology which helps us solving the electrons correlation problem for particularly the multi-electronic system. And this usually the conventional coupled cluster theory, you need to define a reference function, which is most of the cases in the quantum chemistry community that is often done through the Hartree-Fock function. And we employ what we call the wave operator to bring in the effects of the virtual orbitals. And by this means, we take care of the dynamical correlation present in the system. So we start from the Hartree-Fock reference function and we employ a wave operator. The wave operator, particularly in the coupled cluster theory, it comes out to be an exponential of an excitation operator. So if you see my middle box, so we have an exponential of my excitation operator, which is denoted by T, acting on the Hartree-Fock function, and that gives rise to the coupled cluster exact wave function up to the singles and doubles approximation scheme, where T1 and T2 are the singles and double excitation operators. So this is the typical coupled cluster CCSD answers. And these equations, it's pretty well known. These equations are solved by taking a similarity transformed Hamiltonian e to the power minus TH e to the power T and projecting this effective Hamiltonian against the singles and doubles excited functions. So basically in coupled cluster theory, we bring in the effects of the higher line virtual functions by folding it into a effective Hamiltonian. And this is how we take care of the dynamic correlation. This is pretty well known. But the point that I would like to emphasize here, that due to this exponential structure of this wave operator, it turns out that the coupled cluster equations are highly nonlinear equations. So we need to solve the nonlinear equations for each T1 and T2 amplitudes in a coupled manner And this nonlinearity actually appears due to this term e to the power minus t h e to the power t, which can be further expanded through a Becker-Campbell-Hausdorff multi-commutator expansion. Well, so we have the total number of unknowns is basically dimension of my T1 and dimension of T2. And what we do is that we have these many equations, they are nonlinearly coupled. And due to this nonlinear coupling, it is often, in most of the cases or in almost all the cases, that this is solved in an iterative fashion. So basically, we iteratively solve all the T amplitudes, T1 and T2. So there are a tremendous number of amplitudes, and I would like to employ or exploit some of the features of nonlinear dynamics to reduce this number of variables and see whether we can gain more in accuracy or at least more in computational time. So my approach is that we will eventually solve the full equation for the dimension of T1 plus T2, but I will do it in a tremendously reduced space. This is achieved, I'm just giving the summary first. So this is achieved by, we have observed that there are only few variables which actually dictate this iteration process. We will actually do a nonlinear dynamics analysis, but we will see that there are only few variables which dictate the entire iteration process, whereas all other variables, they are sort of enslaved under these major variables. And this is called a master-slave dynamics. And this master-slave dynamics, we will exploit this master-slave dynamics to achieve the same level of accuracy as it is done through the conventional coupled cluster theory. And we will show that we will get at least up to micro-Hartree level of accuracy and with a about 50 to 60% reduction in my computational time. So here we go. This is the more or less the flow or the outline of my talk. First, I will do a linear stability analysis of the coupled cluster equation, and this will validate the robustness of the iterative scheme. By iterative scheme, I mean the Jacobi iterative scheme. We'll do the stability analysis, which we call the Lyapunov analysis, and we will show that this dynamics actually follows the dynamics of an universal, one parameter family. Although this is a highly multidimensional coupled nonlinear equations. And of course, this very high dimensional dynamics, they follow the usual features of the period transition or the chaos period transition, period chaos transitions, as we often see for the logistic map. Then we will do with this one a quick phase space analysis, which leads to the replicate that the full T variables, and we will thus endorse that the fact that from the full phase space analysis that the total this dynamics is dictated by only a few valence electrons, and we will do the same thing by doing some of the recurrence quantification analysis. And with this one, once these are done, so once we establish the master-slave dynamics, we will show that how this iteration process can actually be done in a much reduced dimension. And there we use some of the features of machine learning that I will come in the course of my talk. Okay, so this is the first I'm going into the fixed point analysis of my presentation. So in the fixed point analysis of my presentation, this is the usual Jacobi iterative scheme, as you see from the left-hand side of my screen, that we get the n+1th iteration of my T amplitudes through some of the terms that nth iteration and updating with a factor which is given by the second term, g of n mu, and g of n mu is nothing but this e to the power minus th e to the power t done in a full T1 and T2 space and the corresponding amplitude part of it. So this is, you can see, as I already had mentioned, this e to the power minus th e to the power t is a highly nonlinear equation. So basically this term g of n mu, this is the highly nonlinear term. Okay, but in this nonlinear term, we have n-dimensional equation because that is the total number, total dimension of my T1 plus T2 variables. Often, if we don't use DIIS or any this kind of an accelerating convergence accelerator, what we usually do, we usually put a regularization parameter, which we have denoted by eta here, and we will show that this eta can suitably be exploited to prove the nonlinearity which is associated with the nonlinear dynamic scheme. Okay, so let's call this entire function as R. So now, this set of solutions, when we say eta is 0, so eta is basically an input perturbation. If we put eta equals to 0, this set of equations goes to a fixed set of a set of fixed points. So these are the convergence, the solution points. Now we would like to give a small perturbation around this fixed point, and let's call this perturbation as epsilon. So T1 bar and T2 bar, they are basically nothing but the fixed point of the solutions. They are the exact T amplitudes we obtain after convergence. Now, an input perturbation, they actually reveal the robustness of the dynamics and about the equilibrium points of this nonlinear dynamics process. Now, just by expanding this term in a order by order in a multivariable Taylor expansion, what we get is that a matrix, we can construct a stability matrix, as we call it here. The stability matrix is nothing but a Jacobian matrix. So the stability matrix gives us the stability of the Lyapunov, the stability of this iterative scheme, and we have done it in the orbital basis. So suppose we have constructed this stability matrix, and we solve this the eigenvalue of this stability matrix by diagonalizing this matrix, and what we get is the eigenvalue sigma, and it is said in the linear stability analysis that this theory is going to be exponentially stable if all the values of sigma are less than 1. Or in other words, these lambda, which are the logarithm of the sigma, they are negative. So these lambdas are called the Lyapunov exponent, which comes from the linear stability analysis. Now, as a side comment, I would like to make a point that a part of this stability matrix is nothing but the UMCC matrix, which gives us the excitation amplitudes of the different excitations on top of the ground state. So that's a different story, but I'm going to solve the stability of the system. So if we see this exponent, this Lyapunov exponent as a function of eta, we see that with increase in eta, the Lyapunov exponent actually rise, and at a value about 0.29, it crosses the value 0 along the root of A1 symmetry, and that's the point where the linear stability analysis entirely breaks down. So once the linear stability analysis breaks down, then of course we cannot use this linear stability matrix, and below this 0.29, the solution always, whatever be the amount of the perturbation, the solution always returns to the fixed points, which are the equilibrium points of this dynamics. Now, what happens once you cross 0.29 or little around the 0.29, depending on the nonlinearity of the system? We see that the solution first starts oscillating between 2 points, two values. Then it starts oscillating between 4 values. Then it starts oscillating between 8, 16, 32, so on and so forth, until the dynamics becomes completely chaotic. So here we have shown this bifurcation diagram that we have. It's bifurcated into 4 periods, then 8 periods, and of course we have developed a very novel algorithm based on the bisection method to show that we have actually got the features of very, very high degrees of periods, for example, 256 periods, so on and so forth. You can just recall in this context the dynamics of the logistic map, as we have seen, r times x into x1 minus x. And we see that the different values of r, the solution actually starts oscillating between fixed points, and then it goes to a chaotic solution. Now, which is a universal feature of any map of one parameter family, is the fact that the length of the successive periods, they actually keep on shrinking, and at a very large value, where it's at the point of onset of chaos, the ratio of 2 successive ranges, it follows an universal value of 4.669, which is called the Feigenbaum constant. So we have actually analyzed this using this bisection method, and we have seen that this Feigenbaum constant comes within a 0.003% with the exact value. Of course, this is the numerical inaccuracy that we have to bear with us. So this is basically the kind of the accuracy that we have obtained for this one parameter family map. But remember that map is no longer a one-dimensional map, but it's a very, very high dimensional map. And for a water molecule in CCP-PDZ basis, the dimension of this map is basically 4938, almost 5,000 variables. Okay, so we have proved the universality is observed through the coupled cluster iteration time series under a single parameter perturbation. Now we need to look into the features of these dynamics in a more detail. So we have analyzed a phase space. So with phase space analysis, what we have done is that we have constructed the vector at each time step I. So remember that we can map this nonlinear equations as a time discrete propagation under an infinite under an input perturbation of theta. So once we have put an input perturbation and we have trying to make this this vector at each time step and try to put the distance matrix by taking the difference between the two time steps, the values of these vectors, taking the norm between these vectors in two different time steps, and this is a measure that how close these vectors actually recur in this time series. As you can see that at a given value, I have taken an arbitrary value, say 0.03, 0.375, and it's a very ordered pattern, signifying that it is actually a recurring pattern. It's actually a 32 period cycle. But once we cross this pattern, once we cross this value of 0.375 at a slightly higher value, probably sorry, the previous one was 0.366. This one is 0.375. There is no given pattern, and it becomes completely chaotic. It comes over to this region, which is basically the C, the chaotic C. Fine. Now comes the interesting part. That can we reproduce these dynamics by taking only a few variables and just leaving out all the remaining variables? So what we have done, we have, instead of taking all these 5,000 variables to construct these vectors, we have taken only a handful of variables, and we have denoted it by TIL, T1IL and T2IL, one body and two body, large amplitudes, and they are usually very large in magnitude. So we will call it as largest subset. So these large magnitudes, what we see that if we construct the same distance matrix using just the large amplitudes, we can reproduce the phase space almost exactly. So basically the phase space trajectory constructed by the reduced set of amplitudes, by reduced set I mean just by the largest subset of the amplitudes, they replicate the phase space trajectory constructed by the full T amplitudes quantitatively and qualitatively. All right, so basically these large amplitudes, this TIL, they are nothing but the ordered parameter of the dynamics. And you can remember, for example, the Ginzburg-Landau theory of superconductivity, that you have an ordered parameter which actually governs the macroscopic pattern of the dynamics. The question is, what does all the rest of the things do? The rest of the things are simply their variations are suppressed. Okay, so I am not going into details of how these large variables are chosen, because there are some intrinsic, intricate sort of mathematical relationship. For example, the maximization of the mutual information and so on and so forth. I'm not going to these ones, but these large amplitudes, you can take it as those excitations which involve the valence electrons. Of course, it comes also perturbatively that the valence excitations have larger in magnitude corresponding to the core excitation. So we see that the valence excitations more or less quantitatively and qualitatively replicate the dynamics. Now, let us have a more systematic analysis of the phase space, or systematic analysis of the dynamics, and that is done by what is known as the recurrence quantification analysis. And in this recurrence quantification analysis, we measure some of the quantities associated with the dynamics, for example, the recurrence rate, the divergence of the dynamics, the determinism, the Shannon entropy of the dynamics. And you have seen these are the plots. I'm not going into the exact mathematical relationship again, or what I mean for these different quantities, but you see that this interesting dynamics of this chaotic dynamics, as it's called, it shows all the features of the period transitions as well as the chaos period transitions, where you see the sort of sporadic islands of stability in between here around, so just before 0.370, the islands of stability, where you get from a chaotic phase to a more ordered phase. And you see that the dynamics, it shows in the entropy, it shows the certain jump because your system is getting more and more chaotic. It becomes completely chaotic here, but when there encounters the islands of stability, it goes through a dip, signifying that there is a sudden drop of entropy. The opposite trend happens from the recurrence rate. The recurrence rate actually drops as you go to more and more number of periods. And then once you get to these islands of stability, it shoots up again, saying that the recurrence rate is getting higher and higher. So basically, this recurrence rate, divergence, determinism, entropy, these are the measures of my dynamics, of my chaotic dynamics. And as we have said before, that this largest subset almost qualitatively and quantitatively replicated the entire dynamics. So you'd like to see that whether these dynamics or these recurrence quantification measures, they can also be faithfully reproduced by these only few variables. And we plot it again, and you see the red one is the one which is done by this largest subset, and the blue one is done by the full set of amplitudes 5000, and red one is the largest subset. And you see that these various quantitative measures associated with the dynamics, that they support the presence of this order parameter because of the fact that these red curves, red lines, they more or less exactly reproduce the ones, at least qualitatively and quantitatively in many cases, which we have obtained from the many variable, from this 5000 variable dynamics. So this gives us an idea about the fact that only these valence excitations, which are the order parameters of the system, they very faithfully reproduce the dynamics entirely. Now, the question comes that how many are these valence excitations? You see that we have a total excitation space of about 5000 non-zero variables. And this dimension, if we take this dimension of, say, these TL amplitudes, they have about 10 or 12 depending on the size of the system. So basically these 10 or 12 variables, they exactly dictate the dynamics, and the remaining 4990 variables, they are completely enslaved. Their variation is completely suppressed. So the question now comes that can we express these so many small variables as a function of this order parameter? And this is the basics of synergetics. The way the Haken introduced synergetics is that there is an order parameter of the system, and in this order parameter, all the enslaved variables are unique functions of this order parameter. So the variation of the small amplitudes is suppressed, and the large amplitudes alone determine the dynamics. All right? Fine. So remember that this F mu, in principle, it can be done, say, for example, an adiabatic decoupling scheme, or say, or many other exact scheme, but it will involve the construction of the Jacobian matrix, which takes time. So we did it through a machine learning. Okay. So now the question that often comes is that if we put these enslaved variables to be zero, would these dynamics continue? Or would these dynamics will still be the same? The answer is no. Because these enslaved variables, they have so many in number, they provide a feedback coupling to determine these order parameters. So you have a loop where the order parameters alone single-handedly determine the enslaved variables, but on the other hand, the enslaved variables give a feedback coupling to determine the order parameters. And this is called, in synergetics, this is called the circular causality loop. Remember that we did this mapping from order parameter to the enslaved variables to determine this F through a machine learning. And this mapping we can do through a regular coupled cluster kind of application. So now we focus, I'm not going into again the details, and may I know how much time I have? Maybe 5 minutes?
Yes, I think you have 5 minutes.
Okay. Okay. So now we have done this mapping, as I said, by this shallow machine learning, and this is done by the polynomial kernel ridge regression. I am not going into the details of this polynomial kernel ridge regression of the shallow machine learning, because that's another fully, full talk. It demands a full talk. But what we did is the following: that we first iterated in the full coupled cluster in the full 5000 variable space, say for 4, 5, 6 iterations, and tried a machine learning, a supervised machine learning, to map all these so many small variables as a function of these large variables uniquely. Once this mapping is done, then what we can do, we can restrict the subsequent iterations only to determine the large amplitudes, and the enslaved variables can be determined from this predefined functional map, which we have done for the first 5 or 6 iterations. So basically, for the first 5 or 6 iterations, we use it to train our data set. We train the data set, we make a mapping of these large variables to these small variables. And in the subsequent iterations, we determine through the coupled cluster theory, we determine the large variables only, and all the small iterations of the most small variables, they are done through this predefined functional mapping, which we have done through this machine learning. I'm not going into all the details of this regularization parameter alpha. So basically, this is the noise, the noise tolerance of our model. But let's go to the results. So this is, we have plotted the formaldehyde in CCP-DZ basis, and this is the energy. And this training data set is the number of iterations taken at the initial iterations to train our data to accurately represent this function. You see that initially with this 2 or 3 training data, it's of course not very accurate. Remember, this black dotted line is our exact energy line. And within first 5 training data set, it comes within some tens of micro-Hartree level of accuracy. And then with 6 training data set, it becomes sub micro-Hartree accuracy. Now let's look at the timing. The exact timing, if you see the right-hand side in this scale, the exact timing is about 25 seconds at a 10 to the power minus 6 level of convergence. That means sub micro-Hartree convergence. And with 5 training data set or 6 training data set, we are achieving almost the same micro-Hartree or the sub micro-Hartree level of convergence at 13 seconds in the place of 25 seconds. Or with 5 data sets, it's about 12.5 seconds in the place of 25 seconds. So we have about 50% reduction of computational scaling without losing the accuracy much. It's still sub micro-Hartree accuracy. Now look at the T amplitudes, how the T amplitudes are actually accurate. So if you see the T amplitudes, if you follow any one of these rows, because these 3 rows are for 3 different noise tolerance parameters, you see with 3, so in the y-axis, in the vertical axis, what we have plotted is basically the difference between the exact T amplitudes, what we have obtained by solving the exact method, and the T amplitudes upon convergence that we have obtained through this machine learning. See, with 3 data sets, it's pretty much scattered. The ideal case, once we increase the training data set, it becomes more and more on the 0th line. And with 5 data set, it's almost on top of the 0 line. With 6 data set, it's completely on top of the 0 line. And you can see the R2 score, which is exactly 1. So that means we have quantitatively have reproduced the exact T amplitudes by doing this machine learning. And that is also replicated by the energy. But remember that this has been achieved at a 50% reduction in computational scaling. The same thing happened with any molecule. We have tried quite a few, but same thing, we have shown it for, say, water in CCP-DZ basis. You see that within 5 data set, and of course within 6 data set, it goes below a sub micro-Hartree accuracy. And you see the timing, which takes about 32 to 33 seconds in the place of, say, 68 to 69 seconds. So it's more than 50 to 55% reduction in computational scaling, getting the same accuracy of sub micro-Hartree. All right, so this concludes. I have the same thing with my T amplitudes. I'm not going to repeat the same thing. And this is my conclusion, that we have done a stability analysis of the coupled cluster iterative scheme. We have shown that this iterative scheme follows the universal dynamics of any one parameter family. The dynamics is governed by the valence excitations, which are most chemically important. And of course, they are supported by the perturbation theory. And these chemically important excitations, which are the large excitations, they are the order parameters and the unstable modes of the dynamics. The stable modes are the so many small amplitudes, which have been corroborated by the distance matrix and the recurrence quantification analysis. And with this machine learning, the shallow supervised machine learning, we have expressed these inactive excitations as a function of these large order parameters. And finally, we have developed a new iterative scheme to propose a new iterative scheme for the coupled cluster theory to attain a sub micro-Hartree accuracy with tremendous saving in computational time by exploiting the sub-Fourier causality. With this one, I acknowledge my students, Polai, who is an undergrad student, and Onish, who is a PhD student in our group, who have done all these works. And this machine learning is done by another undergrad student. And I wish Professor Dash a belated very happy birthday, and thank you all for your attention.
Thank you. Thank you, Dr. Maitra, for a very nice talk. So let's take some questions here. Dr. Prasanna, you have question or?
Yes. I've typed a couple of questions actually. Okay.
Oh, you have a lot of questions. Yeah, go ahead. We have time.
Okay. So this is probably a naive question, but I wanted to know why damping parameter is associated with regularization. In the sense that if you look at the expression with d plus eta in the denominator, then yeah, sure.
Yes, yeah.
Yeah, so I'm assuming that d is some sort of an energy difference, and till it goes to 0, giving a singularity, you don't really need to regularize it, right?
But you see, as in couple cluster theory, once your d goes small, your iterative scheme becomes, of course, chaotic. I mean, chaotic in the sense that it's not very stable.
Okay.
So basically, eta is sort of an arbitrarily provided from outside to regularize the iterative process. Okay, so it's just a regularization parameter. So of course, you can use DIIS, but you can also use DIIS to the iterative scheme that we are proposing.
I see. Okay, thanks. If it's okay, I can also ask the second question.
Yeah, you go ahead, and we have time. Yes.
Okay,
yes.
sure. Okay, thanks. So this I wanted to more know whether I'm missing something here. So because we do not know a priori if any deviation from fixed point is small or not, this method need not hold for cases where successive iterations the amplitudes update a lot, right? So in that case,
can you repeat your questions once more? I'm sorry.
Yes, sure. So there is this equation where T1 in the nth iteration and T2 in the nth iteration is replaced by T1 bar T2 bar plus zeta n.
You mean this one? These two?
Very much before this actually, where you basically try to introduce the fixed points. Yeah.
Okay.
Yeah, this equation above on the right hand side. So so if the fixed points, the deviation from fixed point is not small, then this method will probably not hold, right? Because this would assume a Taylor expansion, I believe, from this point.
Okay. So it's a very good question. Actually, you see that the stability analysis theory, linear stability analysis theory says that once this linear stability analysis breaks down, then actually you encounter the slaving principle. But what we observed under a quasi-equilibrium approximation, that even in a sort of a equilibrium or a stable iterative scheme where you are having a fixed point iteration that you are converging to a fixed points, you still hold this kind of a master-slave dynamics. You still hold this master-slave dynamics. If that was your question.
Yeah. Yes.
But you have to assume it's under a quasi-equilibrium approximation or quasi-steady-state approximation.
Okay. So it's all under that assumption. Okay.
Yes, because under the I skipped that one because under the linear stability analysis or the Lyapunov stability analysis, it says that once this linear stability is lost, then only you are supposed to see the master-slave dynamics.
Okay, thank you.
Okay, there is another question from Jovin Jose. Yes. How can one visualize this chaotic dynamics in an experiment?
I don't know. Maybe Briggs-Reuschel reaction kind of thing. I don't know. Where there is this.
Professor Maitra, this is Jobin here. So, if I understood correctly, the dynamics or the chaos that you described is in the electronic structure calculation, right?
Yes. So this is basically a probably the first one we are showing for the in quantum chemistry that this nonlinear dynamics or the chaotic dynamics still holds.
But does it again, if that calculation is so chaotic, I mean, the end result would also so much dependent on the initial conditions and all, right?
No. So basically, the question is that once you go to the chaotic regions, you are much away from your fixed points. So that means your trajectory has shifted from your fixed point trajectory to completely different trajectory.
So we are not talking about the like equilibrium.
No. So equilibrium comes later. So I'm first showing that this is the chaotic dynamics. In the chaotic dynamics, it follows the universality of the Feigenbaum dynamics. And under the quasi-steady state approximation, it still holds for the equilibrium points, equilibrium fixed points, and you still have the master-slave dynamics.
I see. So coming to an experiment, so how can we visualize any thought about, like, I mean, you said it's not concerning the equilibrium or the stable points, but can we visualize any experiment to, to see this chaos?
No, I will think of it. I'm really not very sure about it. I'm really not very sure about it. Yeah.
Okay, then. So, thank you very much, Dr. Mehta, for very interesting talk. Okay, so now, India, hello. Yeah, what is to be done now?
Professor Srivastav, I am going to take over the next session for the poster presentations. All the participants are here and even the judges are here. But I request you to please rejoin, or maybe you can stay here and enjoy these poster presentations.
Okay, no problem. That's very good. Yes. So I take up at 5:15, right? 5:15 p.m.
Yes.
Okay. Okay. So
thank you so
good
much.
luck. So thank you very much. Okay.
Thank you.
Okay, so I think without any further delays, I should start. We are taking a break here from all the invited, contributed and keynote talks. And this session is exclusively meant for the 6 shortlisted poster participants. We still have 1 minute, but I would like to go through the guidelines quickly so that we can start in time. We have shortlisted 6 poster presentations from the received 25 or 30 total. Those were the pre-recorded videos which were put on our website with an explanation, and out of those 25-30 posters, we selected 6 best, and we requested them to be here and present their work, whatever they presented on the poster, again here for a live Zoom session, you can say. We have judges here who are going to judge these posters and then help us select the best 3 out of these 6. So the guidelines for the participants is that they should stick to their time, 8 minutes, and if they want, I can remind them after 6 minutes. So please try to limit yourself, otherwise there can be negative marking if you exceed 8 minutes. After your 8-minute presentation, you will be asked question and answers by the judges or maybe the audiences, and you have to answer them. Judges for today are Professor Dilip. He is from Department of Physics, Manipur University. He recently joined PRL, I think last month. Professor Manas Mukherjee, Center for Quantum Technologies, National University of Singapore. Professor Rahul Maitra, Department of Chemistry, IIT Bombay. Professor Minori Abe, Theoretical Chemistry Lab, Department of Chemistry, Metropolitan University, Tokyo. And Professor Bodha Ditya Santra, Department of Physics, IIT Delhi. So I welcome you all judges, and I really thank you for your time and efforts in shortlisting these participants. So I would like to go in the order of ascending as the poster numbers. So our first shortlisted poster participant is Arpita Das. Arpita, I request you to kindly share your screen, switch on your videos.
Okay.
And audio. Her title is Coherent Control of the Optical Faraday Rotation, and she is from the Saha Institute of Nuclear Physics. Arpita, kindly stick to the time.
Okay. So, may I start?
Yes, please.
So I'm going to present coherent control of the optical Faraday rotation. So for that purpose, so in optical Faraday rotation, the direction of the linear polarization of the probe beam is rotated when it simultaneously interacted with the circularly polarized strong palm beam in the atomic medium. So here the strong circularly polarized palm beam creates an
I request you to...
Sorry?
I think you can switch off your videos because the voice is cracking.
Okay. So it's fine now? Hello? Hello?
You can maybe switch off your videos because your voice is cracking.
Yeah. I'm switching.
Great, please go ahead. You can
so this is a optical Faraday rotation. Now, to control this optical Faraday rotation coherently, we introduced another phenomenon which is known as electromagnetically induced transparency, or EIT. So this is a quantum interference process in which the optical properties of the medium changes drastically. So here the strong pump creates the medium to be transparent to the probe beam by generating coherences between the relevant atomic states. So this is a probe signal where this is the dispersion signal, this blue ones, where we got a transparency window at the resonance position, and this is the dispersion signal, and corresponding dispersion is normal. So thus in case of EIT, the absorptive and dispersive properties of the mediums are modified to the weak probe field, and the medium becomes very dispersive at the vicinity of the EIT resonance. So the polarization rotation in the EIT medium gives us the coherent control of the optical Faraday rotation. Again, this angle of rotation depends highly on the various system parameters. So our aim is to study how we can control the polarization rotation with electromagnetically induced transparency by controlling the system parameters. And this will also help us to enhance the rotation phenomenon, as well as it can also improve the rotation applications of the polarization rotation. So for that purpose, we choose 87 rubidium to study in a V-type configuration combining D1 and D2 transition of the rubidium. So our pump beam is locked at the D1 transition and our probe beam is scanned through the D2 transition. And this is an experimental setup in our laboratory. So now let me explain this setup schematically. So this is our probe beam, which is linearly polarized, and our pump beam is circularly polarized. Both are propagatingly passing through the cell, and we detect the probe beam as the balanced polarimetric detection technique, and which gives us this rotational signal as in dispersion in nature. So this peak is corresponding to the EIT resonance, and we got normal dispersion. And in this experiment, we changes the pump intensity, and so from the spectrum, we can calculate the angle of rotation at the vicinity of the EIT following this equation. And this angle of rotation basically carries the information between the mismatches between the of the refractive index between the left and right circular components of the probe beam. So as we changes the pump intensity, we observe that angle of rotation increases as the anisotropy in the medium increases up to a certain value. After that, as the power burdening phenomena dominated over the anisotropic behavior of the medium, the angle of rotation decreases. So from this study, we can comment that we need to optimize the pump intensity to get an enhanced rotation. Now we choose an optimum value of pump intensity, and in this case we changes the angle between the pump and the probe beam inside the atomic medium. So while doing this experiment, the number of atoms interacting in the interaction cross section will also change. So the optical depth of the medium as well as the pump beam spot size becomes important parameters. So we took these two parameters separately in our study. So while we changes the angular mismatches, we observe that the angle of rotation decreases as in this case the residual Doppler burdening phenomena dominated over the anisotropic behavior of the medium, and it also masks the two-photon coherence contribution of the medium, so that the angle of rotation decreases. And for a particular angular mismatches, as we increase the optical depth, it also increases the number density in the medium, and that also increases the number of interacting atoms in the medium. So we got enhanced rotation. Similarly, in case of increasing the pump beam spot size, we also got increasing in angle of rotation, because here as we increase the spot size of the pump beam, the interaction cross section is changed. So the number of interacting atoms which exhibits the two-photon coherence contribution is also increases. So we got angle of rotation increasing. So from this study, we can also comment that one should take care about the angular mismatches between the pump and the probe, and the optical depth, and as well as the spot size of the beam. So now keeping all the previous parameters at a fixed or at a optimum value, we now varied the ellipticity of the probe beam. For that purpose, we placed a quarter wave plate in the path of the linear polarized probe beam, and we got a periodical variation in the characteristics of the angle of polarization rotation with the probe ellipticity, and we got a periodicity of pi/2 in this variation, and we got the maximum for linear polarization of the probe beam. And
2 minutes are left. Kindly wind up.
So I will complete. So for circular polarization, we got minimum rotation. So from this curve can also be used as a calibration graph to know unknown polarization of the beam. And in the previous cases, there is no external magnetic field. Here we applied. Now we fixed all the previous parameter to our optimum value, and we introduced a longitudinal magnetic field in the atomic media. And as we introduce the magnetic field, additional birefringence effect is created in the medium, and as a result we got enhanced in angle of rotation up to a certain value, because after that the increase in magnetic field worsen the coherence effect in the medium, and this affect the angle of rotation. So we got a decrease in angle of rotation. And from this study, we can also observe that while we applying a very small field initially, we got that angle of rotation increases 1 order of the magnitude to 1 order of magnitude than the angle of rotation without magnetic field. So we can comment that the angle of rotation or the polarization rotation is sensitive to the magnetic field. Now, to explain this theoretically, we considered that the rotation arises due to difference between the contribution to the left and right circular components of the probe beam, and for that purpose we solve the Liouville's equation. So for the when there is no magnetic field, our system is degenerate. So this is the Hamiltonian for our system. These omegas are the pump and probe Rabi frequencies, where we consider all the parametric contribution, that is the spot size effect, the ellipticity, and the intensity effects. And then to consider the angular mismatches, we consider that our pump beam lies in the XZ plane, and so that these angular mismatches can affect in the 2-photon detuning term. And then we calculate the susceptibilities for corresponding to the left and right circular components, considering atoms of
Yeah, kindly come to the
okay. So then we get the theoretical spectrum which matches well, and so finally I can conclude that we need to optimize the system parameters to get enhanced rotation, and this angle variation can be used as a calibration graph to get an idea about an unknown polarization state of the beam, and the experimental technique can also be used to detect the presence of an unknown magnetic field. And also this polarization rotation technique can be used in optical locking purposes, and from the angle of rotation we can also calculate the slow light group velocity of the probe beam, so it can be used in slow light phenomenon. So these are my references, and thank you.
Thank you so much, Arpita. Do we have questions from the judges?
Maybe I have one quick one. So the magnetic field, the small magnetic field that you applied by the coil, did you study the noise from that magnetic field?
No, not the noise.
The reason I'm asking is that there is something like a micro Tesla given here, right? But how did you apply this electric field to the coil?
So we threw a power supply from to the solenoid.
So did you see any 50 Hertz noise in there?
Okay, so that is no, there is okay. So now I understand. So no, there is no such kind of noise there. So that power supply is stable.
Okay. My question was more related to the graph on the right side. So is it the slope we see, is it because of the noise? Because I would imagine if I put any DC supply from the, linear supply, I guess, I would expect to see some noise behavior.
No,
One
actually,
micro.
this is from the actually what we so first we applied magnetic field and we got that rotational spectrum, and from that rotational spectrum we got that we from the slope of the rotational spectrum we calculate the angle of rotation. Now these I mean that fluctuations can be come into play from that fitting error, and also there is some fluctuations in the I mean that while we calibrating that magnetic field, there is some kind of fluctuations, this order of this kind of fluctuations. So these are all taken care in our calculations. But as you mentioned that the noise from the power supply, that we did not take care in that calculation.
Okay, thank you.
Thank you so much.
I had one question. May I ask?
Yes, sure. We have 1 minute. Yeah.
So actually, I had a couple of questions, but I would probably ask one. So you are showing this equation. So basically, in this Liouville operator, right? So the first term of this is basically a non-Hermitian term, right? So basically, this is something which represents some system which is not part of your system of measurement, and it actually couples to the outside and then induces some decoherence or some kind of loss mechanism. So can you please kind of explain how this part is connected to your experiment?
Okay. So here this rho is basically the density matrix. So the so for our cases, the since it is a 4-level atomic system, so this density matrix is a 4x4 density matrix. The diagonal terms of this density matrix gives us the information about the population of the individual levels, and the off diagonal terms gives us the coherence information of the corresponding coupling beams. So as we need the coherence term for the probe beam, so we calculate here the rho 3.1 and rho 4.1 terms analytically.
Okay. So did you measure these coherence properties?
So basically, what we observe this spectra is basically related to the because the real part of the coherence term gives you the information about the dispersion of the media, and the imaginary part gives us the information about the absorption. So here, as we measure the dispersion signal, so we calculate the real part of the coherence term.
Okay, thank you.
Thank you, Arpita. Can you stop sharing your screen now so that
okay.
So the next poster presentee is Jyoti. She is from Guru Nanak Dev University. Jyoti, I request you to kindly share your screen. Title of her poster is Magic Wavelengths for Excited States Transition in Rubidium and Cesium for Optical Lattice-Based Active Clocks.
Ma'am, is my slide visible?
Yes. Can you put it in slide?
Slideshow, yeah. Is it fine? Can you hear me?
Yeah, please try to limit yourself in 8 minutes. Don't exceed time, and your time starts now.
Hello everyone, I am presenting on magic wavelengths for excited state transitions in rubidium and cesium for optical lattice-based active clocks. Here is the outline. Firstly, we will have motivation, then methodology, where we have two parts: how to calculate dipole polarizabilities and how to evaluate magic wavelengths. Then we will have results, conclusions, applications, and our work, and finally we will have references. First of all, as we all know, currently we are working on, we have passive clocks. Cesium atom clock is very well renowned. Then why do we need active clocks? First of all, passive clocks are very bulky and they do have some short-term stabilities. That is why we need active clocks. Moreover, active clocks, atomic ensemble itself can produce a highly stable and accurate standard frequency signal. Therefore, in these active clocks, there is no need of local oscillator, and therefore they are really very concise. Why do we consider excited state transitions in our work? As we all know, active clocks work on Maser mechanism, which basically follows the stimulated emission of radiation principle. So we have considered excited state transition so that we can have stimulated emission of radiation. So far, a lot of work has been done on 2-level and 3-level schemes. So we have considered 4-level schemes here. As in case of rubidium and cesium, they are really apt to laser cooling and trapping, and they barely get affected by the light shift of pumping laser, which was the major limitation of 2-level and 3-level previously opted scheme. So first of all, what are active optical clocks? The active optical clocks are the clocks in which atomic system itself is the oscillator, which generates radiation with the clock frequency, and that clock frequency is simply received and converted to an output signal. As I already mentioned, it is based on Maser mechanism. So we have ammonia Maser clock, hydrogen Maser clock, and so on and so forth. So why have we used active mode? It is more stable. It shows more stable frequency standard, and it has highly reproducible atomic standard. To overcome the short-term stability of passive clocks, we have used active mode as it gives us long-term stability and shows very low energy losses. So here is the methodology. We have first evaluated dipole polarizability for a hyperfine level Fn for any state n by using this following formula. Here this alpha and Fn omega is the total dynamic dipole polarizability, which is basically dependent on delta Enk, which is the difference of unperturbed energies of level n and level k. This alpha and Fn omega, the dynamic dipole polarizability, can be expressed in terms of scalar of that is the tensor of rank 0 and the tensor of rank 2. Here mf is the magnetic projection of total angular momentum f. So how do we evaluate magic wavelength? First of all, what is magic wavelength? Magic wavelength is the wavelength at which differential AC Stark shifts reads 0. Here this delta E omega is the differential AC Stark shift, which is actually equal to the difference between the energy shifts of two involved states during the transition, which is basically dependent on dipole polarizability. So this follows this equation, and if we see graphically, we can say that where these dipole polarizability curves intersect each other for the considered states, that point of intersection basically is the value where magic wavelength occurs. So here are our results. We have first evaluated the static dipole polarizability for cesium 7s half, 6p half, and 6p 3 half states. These are the values that we have obtained: 6257 for 7s half, 1339 for 6p half, and this is the scalar term, and this is the tensor term for 6p 3 half. They all are in good agreement with the experimental value and the already published literature. This is the J-dependent graph for J-dependent dynamic polarizability graph for 7s half to 6p 3 half transition, and similarly this is the F-dependent graph for the same transition. In both the cases, we can see that we have the points of intersection at this 980 and around 1100 and this around 1400 nanometer. In both the cases, the points of intersections are nearly the same. Therefore, they for both the dependencies, we got the nearly same results. Similarly, we have results for rubidium. Here is the static dipole polarizability table for 6s half, 5p half, 5p 3 half states of rubidium. These are the results that we have got. Unfortunately, we don't have an experimental value for 6s half state dipole polarizability, static dipole polarizability for rubidium, but this obtained value is in good approximation with already published theoretical literature. Similarly, we have J-dependent polarizability graph for rubidium 6s to 5p 3 half transition, and here is the F-dependent graph. In both of them, the results are for the magic wavelength values for both the dependencies matches very well. In both the cases, we have points of intersection around 1331, around 1460 nanometer here as well. So to conclude, I can say that we have recommended the reliable magic wavelengths for experimental use for trapping of rubidium and cesium for the considered transitions. In case of cesium, we have found that magic wavelength at 1413 nanometer is recommended for experimental use, and there is a possibility of red detune trap at 2771 nanometer for 6s to 5p half, 3 half, both the transitions in rubidium. As far as applications are concerned, it opens the doorway to precision laser spectroscopy and long-time coherence physics. It will also provide the more stable optical clock than any current atomic clock, and it will provide the subnatural laser line width laser spectroscopy and long coherence time laser with line width at millihertz level. This is our work. This above paper just got accepted yesterday in physical review a rapid communications, and the below one is already submitted and is under review in atoms. These are the references. Thank you.
Thank you so much. You were perfectly within time. You stopped before time actually. Any questions from the judges?
I have one question. So, like what you were showing, this magic wavelength for cesium is something around 1400, yeah, 13, right? But like this is connecting which transition? So the singlet is, so the S1/2 to P3/2 or
No,
P1?
7.5 to 6p half. That was for 7.5 to 6p half transition. I haven't attached the graph here as I had some limitations.
Okay, so how is it different from this transition, the magic wavelength in cesium, which is at around 936 nanometer?
936. You mean like this one here?
I guess this is connecting S1/2 to P3/2.
Yes, this is for 7.5 to 6p3/2. Actually, we have got too many resonances around this 900 domain. About this 900, 950 domain. So we have omitted that part. We have only considered the domain from 900 to 1500 nanometer.
Okay.
Yeah.
But this is just another magic wavelength, right?
Yeah, that is another magic wavelength.
So in principle, one could also build such active clocks using 936 nanometer, or is anything special about 1413 nanometer?
Actually, we will have to see what kind of trap that is forming. We have considered, if we see 1,413 nanometer for 7s to 6p/2, it forms red detuned trap. If the dipole polarizability that we have got at 936 around nanometer is high, and the trap that is formed is far detuned, then it is good to go for experimental use.
Okay, thank you very much.
I see Professor Mukherjee has a question. Please go ahead, Professor Mukherjee. We still have time for one.
Yeah, if I may. Thanks for the talk. Can you go a few slides after this?
Just repeating. Before or after?
One more.
Yeah, right. This.
Yeah, so if I understand, you are recommending 2.7 micron for trap, right?
Yeah.
Now, for a clock, I mean, I'm not an expert on this, but just when I look at 2.7 micron, that's very much in the IR, right? So would you consider also the problem of blackbody radiation? Would that be a problem for clock?
Yes, that will be the problem, and there are many papers there are many groups that are working on that problem for now. But since I am in the study phase, I haven't go so far. I have just recommended the values that are good to go. But if we work further, we have to consider the problem of blackbody radiation shift as well.
So my question may be, if I phrase it, do you expect these clocks to be accurate enough to see blackbody radiation, or precise enough?
Yes, I do expect this. Basically, as far as I think, it generally depends on the laser that we are using and how do we do the optimization, but we cannot say anything until we do the experimental work. But if I go for my opinion, I think it will be precise and accurate.
Okay, thank you.
Thank you.
Thank you so much, Jyoti. So maybe we can have the third participant here, Sangeeta Sen. Jyoti, if you can stop sharing your screen so that Sangeeta can share.
Okay.
She is from IISER Kolkata, and she is going to talk about correlated computations of magnetic anapole susceptibilities of molecules and their classifications on the basis of response to generally non-uniform magnetic fields. So Sangeeta, I'm going to start your timer now. Please go ahead.
Hello, everybody. So first, I am happy to present, but I would like to not compete if it is okay with the organizers. So after my talk, we can see if it is a problem. Okay? I don't want to compete. Okay. So the title of my talk, as Professor Arora pointed out, is Correlated Computations of Magnetic Anapole Susceptibilities of Molecules and Their Classification on the Basis of Response to Generally Non-Uniform Magnetic Fields. So the focus here is on studying properties which arise from non-uniform magnetic fields. So in particular, what I am going to talk about are induced electronic anapole susceptibilities. So these arise from interactions with the curl of a non-uniform magnetic field. So in particular, the field that we study is a linearly changing one, which I can zoom on here. And the linear gradients are collected in this small matrix B. And H is the reference point for the expansion. And this small matrix B is connected to the curl of the total field. And all my plots are with respect to this curl C. The symmetric part of B is set to 0 since we're not interested in responses to it in this study. Okay. So now what are anapole moments? Simply speaking, the moments which couple to the curl of the magnetic field C in a multipole expansion are anapole moments. And classically, you can think of them as the moments which arise along the axis of a toroid. So this is a toroidal charge distribution, and this moment arises from the meridional currents in this distribution. In our case, what we are doing is we're inducing such currents by an external field and measuring the electronic anapole moment. Okay, so these are the definitions. I don't think I need to go through the details of this, but the quantities of interest here are the normal magnetic susceptibility, which is the second derivative with respect to the uniform part of the field B, and the two types of anapole susceptibility, one which is a second derivative with respect to C, and the other which is a mixed derivative with B and C. Okay, now what are the three main studies that we have undertaken? So the first one that we want to do is we want to generalize the classification of molecules into para and dia so that it encompasses not only the direction of the field, but also the non-uniformity of the field. So as a first proposal, we propose that we construct a matrix zeta, which contains not only the magnetizability, but also the susceptibilities. So normally the sign of the trace of chi is what determines our classification into para and dia. So as per the conventions adopted in this poster, positive trace for chi is paramagnetic and negative trace for chi is diamagnetic. However, there are molecules which show directional behavior such as BH and C4H4. So for BH, you have paramagnetic behavior in perpendicular to the bond axis and diamagnetic along the bond axis. So the sign of the various diagonal elements in chi are not all the same. In this case, the sign of the trace is a very delicate balance, because even for cyclobutadiene C4H4, the same situation arises, but the sum turns out to be negative. So overall diamagnetic as against positive for BH, overall paramagnetic. However, the behavior of BH and C4H4 in a magnetic field are very similar, and also the difficulties in describing electronic structure or magnetic properties of these systems are very similar. So it would make sense to distinguish the directions. Also, to incorporate non-uniformity, we have these quantities. The bars indicate that we have taken care to have them all in the same unit. That is necessary. Our proposal is as follows, that if one or more eigenvalues are positive, that is, energy decreases with increase in the magnitude of either B or C, we classify the molecule broadly as paramagnetic. So when we do this for a set of 36 small molecules here, we have the eigenvalues here, all 6 eigenvalues, and the first column is the average. We see that all the usually paramagnetic molecules the ones which we know, like ALH, BH, BH minus, or C4H4, which is at least paramagnetic in one direction, they all show at least one positive eigenvalue. On the other hand, there is a surprise entry, which is HOF, which is this dot over here. And this is known to be diamagnetic in a uniform field, as you see in the table on the side. However, it shows paramagnetic behavior with respect to the curl. And this shows up when we look at the eigenvalues of zeta. And the behavior of HOF in a with C, or the change in its energy with C, is similar to that of BH and C4H4 with B. So this is something that comes out of generalizing this classification. And if you want more details, you can always diagonalize the submatrices and find out directionality. And if you want to blur out the details, you can look at the average eigenvalue. Now, to study this further, I want to demonstrate this is BH with respect to B and HOF, energy with respect to C. And you clearly see the initial paramagnetic behavior in both cases, one with respect to B and the other with C. This is BH and this is HOF. And then again, you also have the quadratic Zeeman effect. Okay, this is the one aspect of the study. The second aspect of our study is we want to find out how different correlated theories perform in computing magnetic properties. In this case, our main focus is on DFT because that is the one which is used for large molecules nowadays and quite indiscriminately even for magnetic properties. So studies have earlier shown that for properties like magnetizability and NMR shielding constants, meta GGAs like TPSS functional and the KT3 functional, which is specialized for magnetic properties, they do well in computing magnetizabilities and NMR shielding constants. But we needed to see if this held for anapole susceptibilities as well. And luckily, we find that this is true. TPSS has some magic and it performs very well. For these two plots are for the two most difficult cases in our set, BH and HOF, the paramagnetic behavior. It is also seen in the other molecules. We have studied all the molecules here. And
Sangeeta, your time is almost up. Can you please wind up in another 1 minute? I'm sorry.
Yeah, sure. I can wind up, sure.
Thank you so much.
So since we have studied all the molecules, you see the error plots here. This is for magnetizability. And then here we have the susceptibilities. The plots are very similar. It is more difficult to estimate the values of the susceptibilities than for paramagnetic molecules rather than diamagnetic. And the third aspect, which I could not speak about, is when we consider spin effects as well, then we find that up to second order, the effects are almost additive in computing the induced anapole moments. So that is actually helpful if you want to do large molecules. And the last point is that the mixed anapole susceptibility correlates with chirality in some way. And this has been exploited by some other groups in order to compute energy differences between chiral molecules. Okay, so I will conclude here and thank you for this opportunity.
Thank you so much, Dr. Sangeeta. Are there any questions from the audiences?
I have a question.
Yes.
Yeah, Sangeeta, how much does it depend on the choice of the functional?
It depends quite a lot on the choice of the functionals, actually. So if you look at the error plots, there are two things. So I didn't have a chance to mention that. Here we have brought all the plots to the same zero. So the zero field correlation energy, the differences in that have been suppressed to show the changes with respect to magnetic field. So in an absolute sense, they differ a lot. And if you look closely here, M06, which is often used for transition metal properties, that is really, really bad for magnetic properties. TPSS is magically very good. It is even better than MP2.
Is this fictitious?
Yes, yeah. So there is some magic in TPSS, and we have also done a theoretical study on this. which shows that the meta GGA level is the most natural level for incorporating magnetic field. So anything below that is actually arbitrary. You cannot incorporate magnetic field.
Okay.
Just for one clarification, Sangeeta doesn't want to compete in that in this poster award presentations.
Yeah, I don't want to compete. Yeah.
Okay, so then okay, so that should have been conveyed to us. Okay.
Yeah, I'm sorry. I just thought that
anything personal or it's just.
No, it's not personal. It's just that it's fine. Yeah.
May I ask one question?
Yeah, sure.
We do have time.
Okay. So, I mean, this is quite impressive that you have done so many calculations and looks also very nice. I'm just wondering, because I'm doing this experiment, so what would be the application of all this knowledge, what you are creating? Can you please show some, say some about kind of type of motivation or application of this work?
Okay, so for this particular thing, what I have spoken about now, it is difficult to have a direct experimental study because the strength of fields here, that is quite, that is about 10 to the power 3, 10 to the power 4 Tesla. So that is not quite achievable yet. So the main effect is in astrophysics. So for white dwarf stars, magnetized white dwarf stars, when they want to calculate temperature and other properties, when they collect spectra, then they need the electronic structure of molecules in those fields, and that can only be achieved with theory. So that is one aspect of this study.
Okay, thank you.
Yeah.
Thank you.
And there's another relation to chirality, but that is not clear to me. There is another group in Italy who studies this, like how they can use this energy differences of chiral molecules due to anapole moments, and if that can be detected experimentally. But it is not very clear to me how easy that is.
Okay, thanks a lot.
Okay, thank you, Dr. Sangeeta. If you may please stop sharing the screen now, so that thank you so much. The next participant is Yatin Batra. He is also from Guru Nanak Dev University, and he is going to talk about probing the chemical applications of light and matter interactions. So Yatin, you may start now.
Am I audible, ma'am?
Yes, you're audible. Can you please put your slideshow?
Okay, thank you, ma'am. Can you please remind one after 6 minutes here?
Yes, so your timing is starting now.
Good afternoon, everyone. Today, myself, Yatin Batra, will be talking about the probing the chemical applications of light and matter interactions. So at first, I have discussed about the different characteristics and parts of electromagnetic radiations. I have discussed the wavelength, frequency, and amplitude, where wavelength is stated as the horizontal distance between the two consecutive crest or troughs. Frequency is the number of waves passing through a point per second, or we can say amplitude also, we can say how high the wave is. So why we need to understand all these parameters? We are probing the chemical applications, and the major chemical application is to probe their chemical structure. So all these need to be studied to finally calculate, or we can say finally elucidate the structure of a molecule. Here I have shown an electromagnetic spectrum arranged from a longer wavelength to shorter wavelength, or we can say from higher frequency to the lower frequency. And it is shown from radio waves to gamma waves. And the various parts of the electromagnetic spectrum interacts in different ways with a molecule. Just we can see that microwave is interacting with molecule. Is interacting with the molecule. Excuse me, there is some disturbance.
Yes, I'm checking that. Yeah, please go ahead.
Okay, so talking about the light and matter interaction and how these different parts interact with the various radiations. Microwaves causes the molecular rotation, infrared causing the molecular vibration, visible and UV lights causes the electron level changes in the molecule. So next, at the first, I will discuss the microwave interaction, which helps us in calculating the rotation in molecules, which are further used to calculate the bond length and isotopic substitution. So here I have considered an HCl molecule, which is in a dipole molecule, and have calculated calculated its 3 moments of inertia along its 3 axes, which comes out to be mu dot R naught square, where mu is the reduced mass, we can say the effective mass, and R naught is the effective distance between H and Cl, or we can say the bond length. From Schrodinger equation, we can easily calculate the possible rotational energy transitions that are that can be seen in a rigid diatomic molecule which is having a dipole. So here we see that 0 to 2p, 6p, 12p are the various possible rotational energy transitions. Here we can see if this molecule is made to absorb the microwave radiations, it will undergo the rotational energy transition, and this typical spectra is of this molecule, how this will look, and these lines will look in rotational spectra. So talking about its application in bond length and isotopic substitution, here I have considered an HCl spectra. Its first transitions observed, it is observed at 21.2 centimeter inverse. And from this, the value of B can be calculated. That comes out to be at 10.6 centimeter inverse. By successfully, we can put this value in this equation and calculate the value of IB, which can be further used to calculate R naught if the mass of H and mass of Cl is known. And R naught can be calculated easily. R naught here is the bond length of HCl. Talking about the isotopic substitution, I have considered a spectra of carbon monoxide, which consists of carbon 13 and carbon 12. Carbon 13 isotope is present as a natural abundance. Here 2 peaks are seen. We can say that the shorter peak is of carbon 13 spectra, this carbon 13, and this both the transitions are equated to each other, and M prime, which refer to the mass of the isotope, is calculated, which comes out to be 13.007. So this is the way how we can calculate the isotopic substitution. Now talking about the infrared interaction, we have to analyze the dancing molecule, or we can say the vibration in a molecule. Here we can see a covalent bond is vibrating, and the presence of dipole is also necessary in this. There are majorly 2 types of vibration, that is stretching vibrations and bending vibrations. Stretching are further of symmetric and asymmetric vibrations, and bending are of in-plane and out-plane bending, which can be easily visualized by this animation below. And these all the vibration interacts differently with IR vibrations. So here this covalent bond that is vibrating produces an electromagnetic wave which have its own vibrational frequency, and this is the IR beam of frequency coming from the IR spectrometer. So when these both this natural vibrational frequency and this IR frequency matches, a coupled wave is formed with a higher amplitude, which is which the peak is observed. When there is no peak, when no absorption is there, the transmittance is 100% and no peak is observed. When there is some absorption of the vibration, there is some transmittance, and we can say there is a peak. So why this peak is broad, this can be explained on the basis of the transitional levels. We can see that rotational transitions are superimposed on vibrational transitions. Hence, this the broadening of the spectra is occurring. So the functional group and the fingerprint region is shown here. The functional group region lies from 4,000 centimeter inverse to 1450 centimeter inverse, where major functional groups absorbs radiations, and fingerprint region is the one where major skeletal structure of the molecule is shown. The fingerprint region is of much value to us, as the functional group region can be show the same peaks. Here I have considered an example of propane 1-ol and another example of propane 2-ol. We can see the functional group region is showing the almost same peak, but due to the structural difference, this fingerprint region is showing the different peaks. So how this IR spectra is, how is this IR spectra is helping us in elucidating the structure of a molecule? Here I have shown a structure of nitrile containing molecule and its vibrations and its absorption at different frequency of IR spectrum. Here I have shown that H bonding and H conjugation plays a very major role in deciding the absorption frequencies.
Yatin, you have 2 minutes left.
Okay, ma'am. UV visible interactions. So this is a type of an absorption spectroscopy where transitions take from highest occupied molecular orbital to lowest unoccupied molecular orbital. There are various types of transitions. They are shown here. And this law, the Beer-Lambert's law, helps us in calculating, getting us the qualitative data or quantitative data we can get, because this is directly, the absorption is directly related to the path length and the concentration of the sample. So we are much interested in N to pi transition and pi to pi transitions. Here I have shown a pi to pi transition in isoprene molecule which occurs at 222 nm. So this is the terminology that is much used in UV spectroscopy, the red shift or the blue shift, etc. And in non-polar solvent, there is not much, the lambda max value doesn't shift much. But when discussed with a polar solvent, or when we record it in polar solvent, the value of the lambda max shifts to red shift or blue shift. As the transition states, as the excited and the ground state, it interacts differently with the molecules. So we can say now here a spectra of phenol is shown in ethanol and isooctane, where we can see the ethanol spectra is much higher than this isooctane due to the formation of H bond with ethanol, because ethanol is a polar molecule, polar solvent. So now what is the effect of electron withdrawing and electron donating group on lambda max? In both the cases, the lambda max value will be increasing. This is an chromophore and this is an oxochrome attached. We can see the lambda max value is increasing. Effect of conjugation is also pronounced here. As we increase the conjugation, the energy level gap is decreasing, which leads to the increase in the wavelength. So here a polyene molecule is shown whose value is n is equal to 3, 4, 5. As the conjugation is increasing, it is causing the red shift, because the energy gap is decreasing between them, so they absorb at larger wavelength.
The conclusion, Clyde.
Okay, so now talking about this visible spectrum, then when the conjugation is increased to higher extent, it lies in the visible spectrum of the electromagnetic spectrum, and we observe the color of the molecule shows the color opposite to the wavelength it absorbed. Like see, we can here is lysopene molecule is absorbing at 474 nm, and the color we see is red color because it is the opposite to the color we are which the lysopene molecule absorbing. So conclusion is that by understanding all these basic mechanism of various transition, we can easily understand various applications of the spectroscopy. Thank you.
Okay, thank you so much, Yatin. Are there any questions for Yatin from the judges?
Sorry, I'm asking too many, but just a quick question. So you mentioned about the red and blue shift. Can you please explain why is it happening?
Sir, we can. I said we can see that we have discussed the two transitions here. I can share the screen once again to discuss it in detail. Yeah. So can you see my screen, sir?
Yeah, I do.
Yeah. So here we can see the N to pi transition when taken in polar solvent. We can see that the polar, this N state, that is the ground state, is very much polar, and it stabilizes more when it interacts with the polar solvent due to the formation of H bond. Okay, and this the excited state is not stabilized more. So the energy gap between N to pi transition is increasing here. Due to the increase in energy gap, the wavelength shifts to the we can say it shifts to the blue shift, because we can see the relation between the energy and wavelength is inverse. So in the case of pi to pi transition, the phenomena is same. It is forming the H bond only. But here the pi star transition state, that is the excited state, is more polar, so it stabilizes more, and the energy gap is decreased, and it absorbs at larger wavelength, causing the red shift. Thank you, sir.
Oh, okay, thanks.
We do have time for one quick question, if there are any. All right, thank you, Yatin. Thank you for your presentation. So may I have the next speaker, who is Sahil Parvez. He's from Aligarh Muslim University, and he's going to talk about comparison of time complexity in factorization large by prime numbers using Grover's and Shor's algorithm. So Sahil,
am I audible?
Yes, you're audible. Can you put the presentation in the, yeah, thank you so much. So I'll start your timer. Please go ahead.
Thank you very much. Very good afternoon to one and all present here at FSQT 2020. I am Sahil Parvez, and I will be presenting on the topic comparison of time complexity and factorizing large biprime number using Grover's and Shor's algorithm. This was a project done under the guidance of Professor Prashanto K. Panigrahi and Bikash K. Behra. Here is the abstract for the poster. We all know that the quantum computers are developing, and with the increase of each qubit, the problem-solving capacity doubles. Hence, the quantum computers are good at complex problem-solving and period finding. It finds quantum supremacy over the classical computers. The RSA type cryptography uses the property of factorization for large biprime number into its constituent factors. This is because the classical computer take exponential time to factorize the number. Hence, it would not be able to factorize such large numbers. However, quantum computers can factorize in linear time progression. Hence, the quantum algorithm can use the quantum advantage to do it in very less time. For factorization, the algorithms used are Grover's algorithm and Shor's algorithm. Okay. Now, at first, using Grover's exact search algorithm, we have factorized the biprime number 1,27,94,893 into its factor 3,571 and 3,583. The circuit has been optimized by processing the prerequisites. The process that has been followed is taking the factor of the biprime number n. For this, for example, let us take it as p and q. So n equals to p into q. Now converting the p into q into their binary form using the formula p equals to 2 to the power m plus 1 plus summation 1 to m pi plus 1, and doing the same for q, we would get it as seen beside. Then using the phase matching property, that is comparing pi and qi, we find pi is equals to qi is equals to 0 for I belongs to 9, and pi is equals to qi for equals to 1 for I equals to 1, 4, 5, 6, 7, 8, and 10. So the system can be written into a set of equations as P2 plus Q2 is equals to 1, P3 plus Q3 equals to 1, and P2Q3 plus P3Q2 equals to 0. Now solving these three equations and substituting Q equals to 1 minus P, we get Q2 plus Q3 minus 2 Q2 Q3 equals to 0. It can be written in the Hamiltonian form, which when solved can be reduced into a 2-qubit Hamiltonian as seen in the last equation. And the 2-qubit Hamiltonian can form the corresponding circuit as we can see beside. The state vectors and measurement probabilities of the states are given below. Now the theoretical density matrix is represented by rho t. The formula is given beside, and the experimental density matrix is represented by rho e as seen in the equation, where the S stands for the Stokes parameters. Now the theoretical density matrix as calculated can be seen beside. The state tomography for the theoretical density matrix is found below. Now on running the circuit on different IBM-Q devices, we get the following state tomography for experimental density matrix. The IBM-Q devices used on which the circuit has been run are IBM-Q X2, IBM-Q London, and IBM-Q Melbourne for 1024, 4096, and 8192 shots as shown in different rows respectively. We can compare that the experimental results goes well with the theoretical result. The slight errors can be seen is due to the qubit errors and the gate errors present in the IBM-Q devices. Now, the running time taken by the different IBM-Q devices for different number of shots are given along with the number of qubits available in each device. Now, in case of Shor's algorithm, using 2n plus n qubit, as we can see in the circuit diagram below, for the factorizing a number so large would require 48 qubits and 24 entangled qubits, summing up to 72 qubits, which is still not available for common use. Hence, it is a drawback of Shor's algorithm. Now then, these are the references, and with this I would like to humbly conclude my presentation here and hope everybody enjoyed it. Thank you.
Thank you so much, Sahil. You were absolutely, you did very well with the timing. So we have a lot of questions. I hope coming up from the judges. We have time for at least 2-3 questions. So judges, if you have anything to ask.
I had a question. So,
yes, sir.
Yeah. So, what are the 0, 0, and 1, 1 states? Can you just go back to one slide, probably?
Okay. No, this one.
The next one, sorry.
Okay, this.
Yes.
Okay.
So this psi, what are the superposition states?
Okay, when we are using a 2-qubit circuit, there the superposition state formed are 0, 0, 0, 1, 1, 0, and 1, 1. And now when we are for this circuit, the result which we have got is we are getting the vectors, state vectors at 0, 0, and 1, 1. Okay, so it is having equal probability of states of 0, 0, and 1, 1. So these two states are constituting the density matrix. So the state vectors shows that only. So when we are forming the density matrix, that the psi is the wavelength.
Why the other two states do not contribute?
Okay, these do not contribute because this is theoretical. For the theoretical purpose, we have taken it as such. For when we are considering the experimental state tomography, these do come. So we can see here the Stokes parameters. We will be getting 0, 0, 0, 1, 1, 0, and 1, 1 for for the experiments, because there are some errors in it. But in theoretical ones, we don't get so we are applying it on RZ, means when we are using that circuit, we are using that RZ on which is equals to pi by minus pi by 2. We are using on 1 and 2, and when we are getting the results, we are taking the measurements. We are getting it for 0, 0, and 1, 1 for this circuit.
Hi, can I ask a question?
Yes,
Yes, sir.
Hi, hi, Sahil. So if you look at this density matrix plots that you have given,
yes, sir.
The IBM-Q device at Melbourne seems to have a larger errors, right?
Yes, sir.
What is the reason for that?
So there are 15 qubits in IBM-Q Melbourne, and whereas the IBM-Q X2 and IBM-Q London uses 5 qubits. So the errors are dependent on the number of qubits used and the gates, how many number of gates used. So when we are doing it for IBM-Q Melbourne, so the number of qubits here is much more than it's triple than that of IBM-Q X2 and IBM-Q London. So the error rates also adds up for that.
You mean the gate depth increases?
Yes, sir.
You mean the gate circuit depth increases?
Yes, but
IBM-Q Melbourne?
So actually only 2 qubits are used. Okay, but the whole system, in the whole system only 2 qubits have been used, but still the errors are dependent on the number of qubits as a whole. Means it is a fabrication error that is there. And if we consider the frequency, running frequency of IBM-Q Melbourne, it is also very lesser than in comparison to IBM-Q X2 and IBM-Q London. So these are the main factors depending for the error rates.
I have may I?
Yes, sir.
So I have a very general question. So you showed that the Grover's algorithm in this case would be better, right?
Yes, sir.
Can you give an intuitive idea why should it be?
Why should it be? So because when we are using Grover's algorithm, we are using the phase matching property. Means in this we are using the phase matching property, which can reduce the number of qubits into just 2 qubit structure. However, when we are using the Shor's algorithm, the maximum means the 2n plus n qubit using this there's the 2n plus n qubit structure, means circuit diagram, we would still be requiring 72 qubits, and the maximum number that could have been divisible by Shor's algorithm is I think 27 21, no sorry, it's 21. So yes, sir. So it is because we have availability of till 15 qubits and not over that. So it is actually dependent on the number of qubits. Means in Shor's algorithm, there is no option for reducing the number of qubits, which is possible by using the phase matching property in the Grover's algorithm.
So can you explain a little bit what you mean by phase matching property?
Okay, sir. When we are using, in this equation, 1 P10 P9 dot 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 P2 P1 1. This is in the binary form of 3571, and 1 P Q10 Q9 to Q1 Q2 Q1 1. It is the binary form of Q. Okay, now for 3583. So when we are comparing this P1 and Q1, so then we would be finding that both are 1, having binary number 1. And when we are doing for 2, when P2 is 0, Q2 has to be 1. And when P3 is 0, Q3 has to be 1, and vice versa. And similarly Q10 is equals to, we'll be finding that P10 and Q10 will be equals to 1, P9 and Q9 will be equals to 0, and P8 Q8 will be equals to 1, and similarly. So when we are finding that the P and the Q are matching, so that would reduce the set of equations. The variables decreases, so the set of equations decrease, and the size of the circuit can be made smaller.
I see. Okay, thank you.
Thank you, sir.
Maybe can I ask one short question?
Yes, sir.
Yes.
So so how the implementation of this algorithm were done onto this quantum computers you talked about?
Okay. When we are using that Hamiltonian equation at the last, so means we are after solving these equations, means the three equations which we can see, P2 plus Q2 equals to 1, P3 Q3 equals to 1, and this P2 Q3 plus P3 Q2 equals to 0. After solving these, we get this equation Q2 plus Q3 minus 2 Q2 Q3 equals to 0. So
no, actually, sorry,
yes,
actually I'm talking about, so this is something what you have already told. This is something you send to the library of the control system of this quantum computer. So I'm talking about the step which takes place from the library to the real qubits. Can you say something about it?
I didn't get you, sir. Can you please repeat?
Like what kind of qubits and what kind of property it has to be, because what you did not really work with the hardware part. So I want to know if you can enlighten something about the hardware part.
Okay. I really couldn't get actually.
Okay, it's fine. It's no problem.
Yes. So this. Sorry, sir.
It's no problem.
I think we should move on to the last talk. So thank you, Sahil. And if you can please stop sharing the screen.
One.
Request the next speaker to share his screen. Next speaker is Bhanu Pratap from the National Institute of Science, Education and Research, Bhubaneswar. And he's going to talk about a simulation model for witnessing quantum effects of gravity using IBM quantum computer. So Bhanu, I am going to start your timing now. Please go ahead.
Yeah. Ma'am, please remind me at 6 minutes.
Sure, Andy.
Yeah. So the title of my poster is a simulational model for witnessing quantum effects of gravity using IBM quantum computer. And the paper has now been published in Springer. So as you know that there are not many schemes to actually experimentally test gravity in a tabletop experiment. All the tests that has been proposed to experimentally determine whether quantum gravity exists or not, they are very large scale experiments, and they are currently not possible using our current technologies. So in 2017, Professor Bose from UCL London and the team of Shira Marletto and Vedral, they came up with two similar schemes that shows a tabletop experiment that can be done to, to see the quantum effects of gravity. And what my task was is to simulate that scheme using the IBM QX4 quantum chip. So this is the scheme proposed by Professor Bose. So the idea is, if we have we need two test masses. So two mesoscopic test masses. And if, let's say, we consider that gravity is indeed a quantum entity. So if gravity is a quantum entity, then there has to be some eigen quantum numbers associated with gravity. Let's call those orbital quantum numbers, or maybe mass eigenstates. So here that it has been considered as Gaussian wave packets. So let's say I have two test masses, 1 and 2, and I create this mass eigenstates, so to speak, in those test masses. So for the first test mass, those two eigenstates become L1 and R1, and for the other test mass, it becomes L2 and R2. And I have those test masses specially separated by a distance d, and the due to the Gaussian splitting of the test masses, the gap between them is delta x1 and delta x2. Now the idea is to start with these two test masses and use a quantum mechanical phase to introduce in the whole system, and in the process entangle these two test masses. And if you are able to entangle, and we use gravitational phase to entangle the test masses, and we don't know whether the test masses will be entangled or not, but the idea is we use this gravitational phase to try entangling the test masses, and then we use this mesoscopic test masses that has embedded spin. So now we can transfer, using Stern-Gerlach interferometry, we can transfer this entanglement from the mass eigenstates to the spin eigenstates, and we know how to measure spin in an experiment. So we can measure the spin and see the entanglement. And if such an entanglement exists at the end of the experiment, then we can say that yes, the only interaction that happened was gravitational interaction that created an entanglement between the masses, and that entanglement has been transferred from masses to the spin. And if we measure the spin, we see that there is a entanglement. So that means the initial gravitational interaction was indeed quantum in nature, because we know only quantum can make entanglement. No other classical correlation or interaction can make entanglement. So that is the idea behind the scheme. So as you can see, we start with two separate states for both the particles, and we introduce this gravitational phase in different stages. And by introducing this gravitational phase, if you see this state has now become entangled. So, and we consider particles that has embedded spin. Now there has been some proposals on how to embed spins on mesoscopic particles, but that's not really the point of this talk. But there have been schemes, and that has been cited in both Bose and Marletto's paper. And so if we consider these two separate test masses, and this 0 tilde corresponds to the spins of those two particles. So 1 for the first particle, 2 for the second particle, and we start with such a mass, and we use the quantum mechanical phase to introduce entanglement, and then we can see that the entanglement is now being transferred using Stern-Gerlach. The entanglement is now being transferred to the spin qubits, the tilde qubits, and the mass states are now separable. So we have created entanglement and then transferred it to the spin qubit, and now we use this entanglement witness to measure the entanglement. And if the entanglement witness value is greater than 1, we can see that the spin qubits are entangled. So this is the circuit that I used in IBM QX4. So for our case, we didn't have an embedded system. So we took 4 of the transmon qubits from IBM setup. So let's say this one is the mass of the first particle, mass of the second particle, spin of the first particle, spin of the second particle. And here we are creating superposition, so of the mass and the spins. And then we are entangling a mass of one particle with spin of the same particle. So this is how we are embedding the spin actually in our case. And then we are using a unitary operation to introduce the gravitational phases, and this unitary operator to be exact. And then we are disentangling the masses from the spins. So now there is no connection with the mass qubits and the spin qubits, and they are only measuring the spin qubits and getting entanglement. Whatever the gravitational phases we have introduced is only in the spin mass qubit part, not in the spin qubits. So, and we also need to decompose the 4x4 unitary matrix in unitary matrices that can be easily implemented in IBM. So using this simple mathematics, we can decompose that unitary matrices into 4 such unitary matrices. And those 4 matrices can now be implemented using simply Hadamard C0 X gate and this R rotation matrix gate in IBM. And this will be introduced in 4 phases. So the half of that phase phi would be introduced first, then phi LR would be introduced, then phi RL would be introduced, then the other half of the phi phase would again be introduced in the circuit. And this is the experimental setup for the IBM QX4, the errors and the coherence times. And this is the circuit that was actually made in the IBM simulator. And now if we talk about the results, so what we did, we calculated the entanglement witness, and for various values of this relative phase difference phi in the quantum mechanical phase. And we find that it we expected it to be a sinusoidal curve, so that's fine. But we find that for a certain range of the this relative phase value, the entanglement witness gives up more than one value, which means the states is entangled. And for certain values, it's not. So these in turn can be calculated as, I mean, given the parameters of the distance and everything and the mass, it can be translated to the coherence time of the system. So there have been 2 proposals by one by Marletto and one by Bose. Bose's proposal said to take test masses of 10 to the minus 14 kg, but that gave, as a result of this experiment, that gave us very big coherence time that is not achievable, at least right now. But using Marletto's scheme of 10 to the minus 12 kg masses, we get a coherence time in the range of 0.46 seconds to 0.68 seconds, which I think could be achievable in today's experiments. And so this is a simulational model, but the idea is if somebody actually does this experiment in real life,
So,
and
Sahil, you have 1 more minute. Yeah.
okay. And the idea is if actually somebody does this experiment in real life, they can either find that this graph actually goes up, so it gives a more than one value, or it doesn't. If it does give a more than one value, that would be a conclusive proof of gravity being a quantum entity, because the interaction was quantum and thus it created entanglement. And if in a real life experiment, it doesn't go beyond this line, that would mean that no, the gravity has no quantum entity whatsoever. So the scheme actually proves it, gives a very conclusive proof of quantum gravity. And our work was to use a quantum computer, real life quantum computer, to simulate that scheme, because we know that this type of simulation cannot be done using a classical computer, so it has to be a quantum computer. And we have presented the work to Professor Shogato Bose, and he has also appreciated the approach based on his work. So these are the papers that we mostly referred, and the acknowledgement. I worked with Professor Paningray from ISA Kolkata, because I also talked to Professor Shogato Bose for the results. Thank you.
Thank you so much, Manav. Are there any questions from the judges?
I have one question. So I just want to know, like, how did you implement 2 different masses on a set of qubits?
Sir, we didn't implement the masses, so to speak. So this was not a real experiment. This is like a proof of principle demonstration or a simulation. So we just considered like the states of the masses, not the masses itself, but the states we considered to be a quantum state, so that we can use a transmon qubit or like just a qubit to represent the masses, so to speak. So here, as you can see, this 0 qubit is represents the mass, and the 1 qubit, and the quantum mechanical phase that we are introducing, it's not gravitational phase in our experiment, but it's rather a quantum mechanical phase that we're introducing. But the idea is to get the real life coherence time values that we get using the same parameters that one would get if he does a real life experiment.
So this is kind of another type of simulation on top of other 2 papers you mentioned, but this is not really testing on a real hardware.
So the other papers gave the theoretical idea, not any simulational work. And this one is, I mean, this is using the IBM's quantum chip. So it's a simulation, but it's based on a quantum system. It's not based on a classical system.
Okay, thank you.
Thank you, sir.
Is this done in IBM quantum experience?
Yes, sir.
Okay.
May I?
Yes, sure.
Yeah, I have similar question in line of what Bodat was asking, right? So if I understand what you have done is basically entanglement swapping. Correct me if I am wrong.
Yes.
So I don't understand then why you do it, because you can do the same experiment on a laptop, right?
Sorry, I mean the simulation.
Yeah, right. I mean, I can also do it on a laptop.
I mean, that would be a classical simulation, right? You won't use a quantum chip to do the, I mean,
Well, I don't need to. I don't need to. Whatever you got, I can also get it, right? Because you, at some point, I mean, sorry, you mentioned that these kind of simulations cannot be done in classical computer. I would say no. I mean, this can be done in a classical computer.
I mean, yeah, I mean, that would be a simulation. My idea was to give a, I mean,
also simulation.
Yeah, you're right.
So my next question would be related to the coherence. I mean, okay, the proposal from Shogoto is or others. I mean, it's straightforward, but experimentally they're very hard, and particularly because for macroscopic particles to get the coherence is not easy.
Yeah.
So now my question would be, you mentioned about coherences, right, for a certain amount of time. How do you see this in this simulation? I mean, I would not really guess what would be the coherence of a mirror, for example, from the IBM Q experiment.
I mean, the idea is to get an idea about the coherence time, because I mean, this is a real life quantum. I mean, they have their own coherence times, right? The IBM QX chip and the qubit. So what parameters we get, for example, from the coherence time? So basically we get it in terms of the entanglement width or the phi, and we use the parameters as proposed by Bose's paper. And for example, the distance d, the spatial separation x, and these things have been put by hand into the expression, and then we have calculated the tau or the coherence time from the expression. So the others parameters we have taken what would have been what they have proposed for a real life experiment.
Okay, thank you.
Thank you.
Thank you so much, Manap. And I see we were right in time. Can you please stop sharing? Yeah, thank you. So it was a very wonderful poster session, and we discussed everything from fundamental sciences to quantum computers. I would like to thank all the participants who are here, all the audiences for patiently being in the audience, and special thanks to all the judges for their valuable time. The results for the posters are going to be announced tomorrow before the felicitation program. So I request all the poster participants to be there for the announcement. Thank you so much. I think the next session is going to start in another 10 minutes. So we are going to take a 10-minute break here. I see the I see the chair for the next session is already present. And Prasanna, if you are here.
Yes, I'm here. Yeah.
Okay, so is it okay if we take like 10 minutes break and maybe 5 minutes break and be right here at 5:10?
Yeah, that's perfectly fine, maybe. So the next session begins at 5:15, right?
Yes.
Yeah, sure. Yes. So I'll be back in 5 or 6 minutes in that case.
Thank you so much.
Thank you. Hello. I think we can.
Yeah, Prasanna, I can hear you. I think Professor Deshmukh is already there. Yeah, I see him.
Yeah, Professor Deshmukh is there. Yeah.
Yes, I have joined. Greetings, everybody. Good afternoon, good evening.
Good afternoon.
Yes.
So should we begin in about a minute or two?
Yeah, yeah.
Okay.
Wait for a minute. Let people join.
Okay.
Hello, Rajesh.
Hello, Pranav. How are you? Nice to see you after
Indeed,
long.
absolutely.
Yeah,
Yes.
yeah. Okay. So you are still in.
See, this was the plan actually. This was the plan.
Yeah, Vijay. We should be thankful to Vijay.
Yes.
Okay.
COVID is making certain things possible which would not have been easy otherwise.
Yeah, of course.
Yeah, many of us are able to get to meet each other.
Yeah.
I see this is turning out to be a great meeting.
So.
I heard a couple of talks during the previous poster session. Very nice.
Yeah.
Yeah, Prasanna, you can start.
Okay, sure. So I will request Professor Srivastava to introduce the next speaker. Yeah.
Okay, thank you. So welcome you all to the resumed session. So we have a great speaker, Professor Pranav Deshmukh. Everybody knows him, but still let me see. Professor Deshmukh has been associated with IIT Madras for a long time, and then he joined IIT Tirupati there. And he has been active all the time. And the new thing he did, he has created a center for atomic molecular optical sciences and technologies, which is a joint venture of Tirupati, IIT Tirupati and IISER Tirupati. Professor Deshmukh's research interests, we all know, is the photo absorption processes in free and confined atoms, molecules, and ions. Today, he is talking on scattering time relay in quantum information processing. So I invite and welcome Professor Deshmukh to start his talk.
Yes, thank you very much, Rajesh, for your very kind and generous introduction.
Thank you.
I'm trying to share my screen. Can you all see the screen?
Yeah.
All right, good.
Yes.
So let me try to go full screen. So Rajesh is a very close friend and very generously introduces me. So thank you very much, Rajesh. But we all know the exaggerations of that.
No, it's not exaggeration. No, I don't agree on this.
So anyway, let me get on with the talk. And when I was invited to speak at this meeting, I really hesitated because I do not really work in the field of quantum technologies. But then basically we work on quantum collisions and related processes, especially dealing with photo absorption, photoionization, photoexcitation, and relativistic many-body effects, and so on. And while reading literature, I came across some work which would be of interest in quantum information processing, which I thought will be of interest to the audience this evening. So let me just share with you what very little I have read about these things. And before I proceed, I would like to wish my good friend Bhanu, in whose honor we are meeting at this conference. Bhanu has made rich contributions to the field, and it's really an honor to participate in an event in which we are celebrating the works of Bhanu Das. So wish you all the best, Bhanu, all the time. And my very special thanks to the committee, FSQT 2020 committee, for giving me an opportunity to participate in this. So as we look at the journey from classical to quantum computers, we typically go through these big names, Babbage, Turing, and Feynman. And then in a certain sense, quantum computing is often believed to begin with the remarks of Feynman, just like nanoscience and nanotechnology, to his remark that laws of nature being quantum simulation would be most effectively done if you use quantum computing, take recourse to entanglement rather than work with classical bits. This was a remark in 1982. What came around the same time in the early 80s was this very nice work of David Deutsch. And he was interested in solving a problem in some manner to demonstrate that, yes, if you do things using quantum entanglement, it can be done in a way which is different from how you would do it using classical computers, and there would be some advantage to this. So he solved a very simple problem, but a very telling problem, and the problem that he dealt with was to determine if a function box is constant or balanced. And using quantum logic gates, the control NOT gate and the Hadamard gates, Deutsch was able to establish that, yes, you can answer this question in just one step, whereas classical processing would have required 2 steps. So that was the demonstration of the quantum capability of using quantum bits. So essentially, these gates are in some sense unitary transformations on the block sphere. Of course, in multi-bit system, it becomes a little more complicated to visualize, but this is the technique which then gets extended in quantum computing, and the works of Peter Shor and Grover in the mid-90s gave a huge boost to developing very powerful algorithms for quantum computation. And these were exploiting unitary transformations, which is what the quantum gates were made of, and using these techniques were developed, and quantum computing is very intimately associated with these unitary transformations. So this was the work in the mid-90s. And this then integrates to build quantum gates, quantum circuits, quantum computers, and there have been great advances in hardware, quantum technologies, focus on solvability of a problem. What is it that you can do with a quantum computer that you cannot easily do on a classical computer, and so on. So there has been very rich contribution to literature using these quantum gates and the unitary transformations associated with this. And especially for atomic physics now, algorithms have been developed to get self-consistent fields. Only last month, this Hartree-Fock on a superconducting qubit was achieved on the Google machine using a 12-qubit quantum computing algorithm. So these are very advances, and things are happening, and there has been great work presented even at this conference. So this is intimately associated with how you manipulate the qubits using unitary transformations. Now, there are 2 early papers which I will like to draw attention to. and perhaps experts in this field know about this, but somehow the people I had talked to had not taken too much cognizance of this work. And that's part of the reason I thought that I should mention this. And look at the dates, they come from 1980 and 1982. So this is around the same time when Feynman and David Deutsch introduced the world to quantum computing. And this is the paper. So the computer as a physical system, a microscopic quantum mechanical Hamiltonian model of computer as represented by the Turing machine. So this was one paper in Journal of Statistical Physics. And the second, which came just 2 years later, was a PRL, quantum mechanical models of Turing machines that dissipate no energy. These papers are by Paul Benioff, and he talked about two designs for quantum computer. And this was in the early days of quantum computation. So what are these two designs which Benioff talks about? And what I'm talking today alludes to the implications which come out of Benioff's work, and there has been some recent work in that consideration, which also I will mention toward the end of my talk. And essentially, what Benioff points out that the equations model quantum computation at various levels of detail, and the whole of quantum computation and building the algorithms is aimed at that. But then there are simplified equations that drop spatial variables, underpin the quantum circuits and model of quantum computing. And this is what Benioff pointed out. And what he said, and I'm quoting Benioff from his 1980 paper, that quantum circuit formulation is an approximation to open system concept. And this has been referred to in a paper which came much after the work of Peter Shor and Grover and so on. This is a paper in 2007 by Myers and Tai. This is the paper which has come much later, Tai Wu. And what this work points out is the relationship of scattering theory in the context of quantum computing. And maybe those of you who work in this field are very aware of it, but for those who are not, I thought I will introduce this particular work. So scattering theory becomes directly involved in the consideration of quantum computing, and this comes out of Benioff's work, and it has been highlighted in the work of Myers and Wu. And what is pointed out over here, that when you're actually doing flip-flops to design counters or registers to store data and multi-bit numbers and so on, you at some level deal with a pulse which must trigger the flip-flop. So a quantum gate at some level is not just a unitary transformation. It is not just matrix multiplication. There is a lot more to it. And what is happening at a physical level is that a pulse triggers the flip-flop. And what Benioff points out is that quantum circuit formulation is an approximation to the open system concept. So I will mention what he means by this. He considers a register as an open system, and it interacts with the trigger, which he considers as a particle. And the register plus particle together constitute a closed system, which you can represent by a Hamiltonian. And the Hamiltonian, you can think of this Hamiltonian as made up of various pieces. You can think of it, you can think of a Hamiltonian for the register, HR, plus a Hamiltonian for the particle. And then there is an interaction term, which is V. So this is the model that you can use And then you can use scattering theory, because as t tends to minus infinity, you have got a combined in state, which is a tensor product of the register state and a particle state belonging to the in state. And then as t tends to plus infinity, you have got an out state. You have a similar direct product of these two state vectors. And then essentially you can describe this phenomenology using the usual scattering theory and the scattering operator, which we know is a unitary operator. It conserves the overall flux. And Benioff considers two designs, one in which the quantum register is considered to be closed and the evolution is described by this time evolution operator. There is no external influence. Everything is contained within, it is closed. And then the initial state must code initial data and also the entire program, the entire evolution of the system, inclusive of the reaction to the particle, must be coded inside this. The second design is what describes this as an open system. The initial state then does not code the entire program, so that is an advantage. And then successive scatterings drive the register. So this successive scattering you cannot describe by a single Hamiltonian, because the target is changing as the trigger pulse is interacting with it. And it is this interaction part of the Hamiltonian, which we have labeled as phi. It has got certain space variables, and these are typically not dealt with when you use unitary transformations such as the control NOT gate or the Hadamard gate and so on. You're not explicitly taking that into account. And it is in this sense that Benioff says that these are certain approximations. So there is successive scattering, which you cannot describe by a fixed Hamiltonian. And it is the register plus the particles combined system, which evolves unitarily. And this unitarity is very beautiful because it is also very nicely incorporated in the quantum gates, which make up the quantum circuits and the quantum computers. So these unitary transformations, so the earliest ones that were used were perhaps by David Deutsch, the control NOT gate, the Hadamard gate, and so on. And then the works of Peter Shor, Grover, and then everything that comes together to constitute the quantum computers. So now the question that one can ask is, how would you physically implement unitary transformations? You have to do something to the register. There has to be some physical interaction, and that means that you have to exert a certain external influence on the register. The register has to be disturbed. So you can think of this as a scattering process. In terms of quantum mechanics, this really means that you have to arrange for something which will scatter from the register. And this was the main idea discussed in this paper by Mayers and Wu, which I would like to draw attention to. Which is essentially on the relationship of scattering theory to quantum computing, because the register has to be disturbed, and you can represent this process by a scattering mechanism. And then you are confronted with a question that if there is a scattering mechanism, and this is where the kind of physics that we do, the kind of atomic physics that me and my collaborators do, perhaps overlaps with this, because when you're dealing with atomic processes with quantum collisions and so on, there are certain delays that you cannot escape from. And these are considered to be ultra-fast processes. When Einstein explained the photoelectric effect, nobody thought that the photoelectron takes any time to come out of the atom. It was considered to be an instantaneous process. And for almost 100 years, photoionization physics was done using this type of an approximation. But now, in the last 15 years, many experiments have been done, and you actually measure these delays, and this delay will then automatically become an integral part of the time that is required for quantum information processing, because that is the fundamental process which is involved at some level. It is either scattering of a particle or maybe of a photon, and one can treat it at a fundamental level. And there have been experiments which have been carried out rather recently, which are of importance, which I will cite on. So the essential delays are coming from intrinsic phenomena, which are well known after Eugene Wigner, someone who has contributed so much to quantum science and every aspect of quantum science. And the time delay is measurable, comes as a very interesting idea, although it is very well understood now, but it is certainly an interesting idea because time itself is not measurable. Time is not an observable. There is no quantum operator for time. You cannot represent it by a self-adjoint operator, and you do not therefore observe it. But time delay certainly is observable, and this comes out of the works of Wigner and Eisenbud, and we do use an uncertainty involving energy and time, which looks so similar to the position and momentum uncertainty, but intrinsically at a fundamental level, there is a difference in the two uncertainty relationships, because you have these operators for position and momentum, but you do not have an operator for time. But time delay is representable by an operator. And this is the work which I do with some of my students and collaborators. I would like to thank all of them for whatever little I know about it. I've learned a lot from each one of them. And essentially the idea over here is you can represent the collision process using any coordinate system, doesn't matter. So we can think of an r theta phi and just look as to what is happening on the r radial line. So there is a wave packet, a plane wave, which comes and hits the target, and then it gets scattered out. And there is a certain delay which is involved in this. The result is that when this wave packet moves away from the reaction zone, from the target zone, it might appear that it originated behind the original position, corresponding to a delay if it was engaged in the reaction zone for some time, or if the interaction turns out to be such that it pushes the wave packet out, the delay could actually be negative. In other words, it would be an advancement, or sometimes it is referred to as negative time delay. And this analysis is done in terms of a wave packet journey. This was first done in Eisenbud's work. Eisenbud was Wigner's student. So Eisenbud's work precedes Wigner's paper, but Wigner was, of course, associated with this. And essentially, it is in terms of how wave packets propagate. And if you consider the group velocity of the wave packet, and then you come up with the idea that the Eisenbud-Wigner time delay is nothing but this spatial shift, because it appears as if it has if it has originated farther away or closer, depending on whether you have a positive time delay or a negative time delay. That is, whether you have delay or you have time advancement. And then from the wave packet analysis, and I will not go into the mathematical formulation, this is available in various sources on scattering theory. And what it turns out that this delay is given by the energy derivative of the scattering phase shift. So d delta by dE comes as a major factor. And then of course, there are some appropriate factors and also signs. So this is a matter of details. And subsequently, it is important to see how this idea was developed from a different perspective. This was soon after Wigner's paper in 1955. This was the work of Smith, in which he considered the lifetime matrix and collision theory. And he arrived at an expression for time delay using a completely different idea, which is fundamentally different from the idea which was employed by Eisenbud and Wigner. Smith attributed time delay, he sort of developed a measure for the time delay in terms of excess number of particles near scattering center divided by the flux. And he built this idea. But then if you carry out this idea further, it turns out that it gives you a completely identical measure of the time delay as you go out from Eisenbud-Wigner. So some of us refer to this as the Wigner-Eisenbud-Smith time delay. It is also interesting to see that there is actually an operator for time delay, because as I mentioned earlier, there is no operator for time. It is an observable, and then one would expect that you can represent it by a self-adjoint operator. And this comes from the works of Jauch in 1972, and more recently it is described in Amrain's book a little more than 10 years ago. And he describes the scattering process using these Euler operators and the scattering operators, which are the usual things that people who do collision physics are familiar with. And again, I will not go through the detailed mathematical formalism, but it is available in Amrain's book. One can see, using properties of the scattering operator, that when you quantize the Wigner-Eisenbud-Smith time delay, it is given by an operator which is a self-adjoint operator, and one can establish this, which is really heartening, because otherwise there is a lingering question at the back of one's mind as to how is time delay measured, and if it is, then is there an operator for it? So the answer is yes, there is. And our experience with time delay is from the perspective of photoionization process, which is related to the collision process. So in the collision process, you have got an incoming plane wave. If you have a monoenergetic beam of projectiles which are scattered in various directions, there may of course be some anisotropy. That's a matter of, that's a different matter. But then you have got a radial outgoing flux in the final state. Whereas in a photoionization, you do not have an electron in the initial state at all. I mean, the ingredients of this is a projectile and a target. But in photoionization, there is no incoming projectile. What comes in is a photon. What goes out is a completely different particle. What goes out is a fermion, a photoelectron. What comes in is a boson, which is a photon. So it's a completely different process. But then there is a relationship between these two processes, which makes it possible for you to use the same quantum mechanical formalism to connect the solutions, because these two processes are related by this operator, which is the operator for time reversal symmetry. And the time reversal symmetry connects the solutions for scattering with outgoing boundary conditions with those of photoionizations, which are described in terms of the ingoing wave boundary conditions, and this is related by the time reversal symmetry operator. So using this, you can carry forward this idea of the Wigner-Eisenbud-Smith time delay into the domain of photoionization. And now it is important to recognize that the work of Wigner, this 1955 paper in which Wigner built his formalism, so it was a completely purely a Gedanken experiment. It was only a thought experiment, and it has been realized only recently, in much less than 10 years. It was in 2013 that this experiment was actually realized, and there is this paper in Optics Letters 2013 in which resonant scattering of a weak coherent laser pulse on a single two-level system was investigated. And similar experiments have now been done with quantum dots. And essentially what was measured is the time delay between the incoming and scattering light. And this is the minimal level of interaction that you can think of. There is a single atom and a single photon. And you can reduce the overall interaction between a pulse trigger and a register when you're working with you know how you move these registers in a quantum computer. But then there is some minimal interaction, and this experiment, which was done only about 7 years ago, was one of the first ones of this kind in which time delay was measured using this time resolved spectroscopy. There is another paper which is of interest, which came out in Nature in 2016, which is also of similar nature. And then Wigner time delay induced by a single quantum dot was studied just last year. And these are two-level systems which are great qubit candidates for building quantum computation. And the time delays which are involved in this will, in some sense, impact the total time which is required for quantum information processing. Means this whole idea of building quantum computers is to do certain things rapidly, as fast as you can. But then there are going to be some limits, and these limits are going to be understood in terms of fundamental physical interactions. And some of the most fundamental interactions that one can think of is two-level atom reacting to a photon or an electron atom collision at a similar level. So people, of course, have studied Rabi flopping in two-level atoms. And in such a system, in this 2013 paper, the Wigner time delay was directly measured by Morgan and collaborators. And the Gedanken experiment of 1955 was actually realized, and the Wigner time delay was measured as a function of frequency of light. So we are, of course, interested in other two-level systems. You can also have a quantum dot, which works as an artificial atom, or artificial molecules. You can have coupled quantum dots, and so on. And the Wigner time delay induced by a single quantum dot was reported last year in the PRL by Strauss and collaborators. And this is another paper which would be of interest, which would connect quantum scattering with quantum computation and the limits that quantum scattering would put on quantum information processing. So here, if you're going through a bright Wigner resonance, then you have the overall phase shift, which you can express in terms of the background and that which is coming from the resonant process. So here is a autoionization type of resonance in which you have a bound-to-bound transition, which is degenerate with a bound to continuum. And we consider here a pure bright Wigner resonance, so that you have got a Lorentzian profile, a Lorentzian resonance. And the scattering amplitude is now given by this expression, and most of you will be familiar with this, especially those of you who are who have been through the paper by Bhanu. And so you have got this expression for the scattering amplitude, and then you can use this scattering amplitude to determine the Wigner time delay through this. So you can do a little bit of analysis, which is quite straightforward from the point of view of analysis of Fano resonances, and you can find a relationship between the Wigner time delay and the lifetime of a bright Wigner resonance. So it turns out that the maximum time delay that you can have is twice the bright Wigner resonance lifetime. So there are certain upper limits which come through this analysis. They are easy to be seen, but one simply has to go through some well-known scattering theory. So this is the experiment which was done in 2013. You have got a two-level system, and then you have got an electron excitation in the two-level system, and then there is a certain time delay which was measured in this atomic rubidium. So it is a single atom, single photon interaction, and nothing gets less than this when it comes to model quantum register. Because at a physical level, as Benioff points out, that there have to be spatial variables which are otherwise dropped when you do the manipulations, quantum gates with unitary matrices. So here, this is the result which Borgen have reported, and they have measured the Wigner time delay across the resonance, and the maximum that they got was 42 nanoseconds. If you plot the curve that you get from the Fano formula, it gives you a peak which is 52 nanoseconds. So this is only slightly less than that, but this is a very beautiful result. And not a very old one. It comes from just 7 or 8 years ago. And you can compare it with what you get from the Fano formula. And I would like to point out that these time delay studies are certainly very interesting. I'd like to share the works of some of my collaborators here. This is Ankur's work, and this was found to be very important because it turns out that the confinement signature was not carried in the photoelectron angular distribution, but yes, it was carried out in time delay. So when you deal with real systems, and depending on the environment, you may be dealing with the quantum confined systems, and all of the physics that goes into the analysis of time delay in photoionization processes and electron atom collisions or electron molecule collisions will become of great importance in developing estimates of what is the time that is involved in quantum information processing when you're working with very sophisticated quantum gates and quantum computing for quantum computation. Here is another example of the signature of time delay, where it was seen that the angular distributions of the photoelectrons, which is this beta, this was in the giant resonance in manganese, 3p to 3d giant resonance in manganese. And there are weak channels which are often left out of coupling because one thinks that, okay, they will not influence the dominant channels. You always expect the dominant channels to influence the weak ones, but not the other way around. But when you study the energy dependence of the phase, then you see these kinks, and these show up in the time delay. So time delay studies are of great importance, and this brings me practically to the end of this talk. And I go back to the question, which comes out of Benioff's work as to how would you physically implement unitary quantum gate transformations. And it is over here, in terms of quantum mechanics, this means that you have to arrange for something to scatter from the register. And this is where scattering theory and the unavoidable Wigner time delays come into the picture. So thank you all very much. I will be happy to take a few questions.
Thanks, Pranav, for very interesting and extremely relevant talk. So let's take a question. I think there is one question from Bimlendu Dev.
Yes.
Bimlendu, would you like to ask yourself? Or is from YouTube? So, nice talk. Is there any difference between Wigner time delay and the inverse of scattering resonance line width?
Certainly there is. Certainly there is. And it's a very good question because Bimlendu is not the first person to ask this question. This has been asked to me earlier also. And let me go back a few slides over here. It is here. And if you can see this, screen, which I'm sharing again, I'm going back to one of my earlier slides, that the Wigner time delay comes from the energy derivative of the scattering phase shift. So this is the energy derivative. It is angular momentum h cross times energy derivative of the scattering phase shift. And you can determine the expression for the scattering phase shift from the expression for the scattering amplitude through the resonance. And when you do this analysis, it turns out that the gamma over here is the lifetime. So this is the inverse of the width that Bimlendu pointed out. So gamma in this formula is essentially the width. It is the inverse of the lifetime. And the relationship between the two is that the Wigner time delay, being the energy derivative of this, will change. It has got a spectral distribution. It will change from one frequency to another. And through the resonance, no matter how narrow it is, there is a certain spectral distribution. And through that spectral distribution, the time delay would change. That is the one which I showed in the last figure. Toward the end, I showed that there is a spectral distribution. And then the maximum time delay that you get from this is 2 times the resonance lifetime. So the width is only the inverse of the lifetime. This is twice the lifetime, which will be the maximum Wigner time delay. So this is an important relationship to be appreciated. And I hope that answers your question, Bimlendu. Thank you.
Okay. Thank you, Pranav. So there
are a few more questions. So let me read
no
that,
questions.
Yeah.
So I thank you once again.
From YouTube.
Oh, I don't see on the chat.
Yeah, okay.
Oh, you have questions?
Mr. Ravi Kumar is asking that what are the sources of uncertainty in your calculations?
Which calculations? Means I am not sure I understand the question.
Maybe you showed some scattering cross sections or photoionization cross sections.
Oh. There are several. Maybe he was referring to some of the calculations that we have shown over here. And if that is the context, then of course, these results are what you get from the approximations that you make. And they generate certain uncertainties because essentially these are many body systems. You do not have exact solutions. You're making some approximations. And depending on what kind of approximation you're making, you will certainly get different answers. So these cannot be, nobody claims that these are absolutely accurate. So the particular results which I have shown here have been obtained using the relativistic random phase approximation, which means that certain kinds of electron correlations are accounted for in this work. And whatever errors would come from the neglect of other correlations, many body correlations, to that effect, to that extent, these calculations will be wrong. So yes, this is one of the very well tested method that we have used, which is the random phase approximation. It is actually the relativistic random phase approximation. It begins not with the Hartree-Fock, but with the Dirac-Fock. So it starts a priori with relativistic quantum mechanics. So these are fairly good results, and we have also made use of some other approximations which I have not mentioned over here in today's talk, but that's a matter of detail for doing photoionization using relativistic many-body theory. For example, we also use the multi-configurational time dank-off, the relativistic multi-configurational time dank-off method. Then if you're going through a resonance, we use the quantum defect theory, the relativistic multi-channel quantum defect theory. And each of these methods have got their own limitations. They are very powerful methods. They're extremely good. We have got very good results with that. Nonetheless, they are approximations. And there is no apology for making an approximation. It is a many-body problem. Exact solutions do not exist. And physicists live with approximation methods when you're dealing with a many-body problem. Thank you.
Okay, so Vijay, any question for there?
No, that's all. That's all. That was
okay. Thank you, Pranav, once again.
Yes, Rajesh. So thanks to Rajesh, chairman, for this session, and also to everybody else in the organizing committee for a wonderful opportunity. So thank you all very much. Good evening. Goodbye.
Very nice. Good. Bye. So we have the next speaker, Dr. Dimitri Liak.
Yeah,
he's from National Center for. Hello, Dimitri, are you there?
Yeah, he's there.
Hello?
Yeah, I'm here.
Okay, good. So he's. Let me introduce you. He's from National Center for Computational Sciences, Oak Ridge National Laboratory, USA. His research interests are on the enabling large-scale quantum many-body simulations on the leadership heterogeneous HPC systems, and many more topics. The title, his title of the talk is Efficient Electronic Structure Theory via Hierarchical Scale Adaptive Coupled Cluster Formalism, Tensor Factorizations, and High Performance Computing. You are welcome, Dr. Dimitri. You can present your talk.
So I'm going to share my screen.
Yeah, please share your screen.
Can you see my presentation?
Not yet. Oh yeah, now I can see your presentation. Yeah, okay. It's fine.
Okay.
Yeah.
Okay. Great.
Yeah.
Great. Yeah. Okay. First of all, thank you for organizers for inviting me to this conference, and of course, I'm glad to join this celebration of the 65th birthday of Professor Bhanu Das, whom I saw 2 years ago in Japan. So there was a great discussion there. And so today I'm going to present some work in progress, actually, because even though I've done quite a bit of research in coupled cluster theory, but currently I'm mostly doing high performance computing research, but there is still some topics that I'm trying to move forward in the electronic structure theory field. And so this is essentially just some work in progress, no experimental results, no calculations, just some numerical theory. All right. First of all, sorry, can I ask you if you can see my pointer?
Oh, yeah.
Yeah. Okay, great, because yeah, it will be useful. So first of all, the coupled cluster theory, of course, as we all know, presents a very flexible and versatile framework for describing electron correlations, excitations, response, and essentially pretty much any property any property related to quantum mechanics that we want to calculate in a given molecule. And for each of these properties, like correlation, response, and excitation, essentially coupled cluster theory provides a specific tensor, where you can by changing the order of the tensor, you can regulate how accurate your approximation is. So, and in this sense, yeah, it's a very flexible and kind of extensible theory, very nice from theoretical point of view. So if we can group coupled cluster methods by computational complexity, so we can actually distinguish kind of three groups here. And so one group is, of course, the conventional coupled cluster methods, which include just all the regular approximations, CCSD, T, Q, and so on, which don't do any additional tricks how to reduce the computational cost, right? So then the other big group is the so-called local couple cluster methods. There is a whole plethora of couple cluster methods here, which exploit the locality of electron correlation and introduce this kind of selection of orbitals or fragments, and essentially they introduce a Hamiltonian interaction cutoff. And there is also another group of methods which reduce the computational scaling, and these couple cluster methods are so-called like factorized couple cluster methods, where some or all tensors are factorized as products of lower order tensors. And so the whole plethora of approximations here arise: canonical polyadic, matrix product state, Tucker, the tensor tree, and so on. And so in this talk, I am mainly focused on this group, and also I also will try to show that there is yet another possibility how to reduce the cost of the conventional couple clusters theory. But first, let me start, because it will be in these presentations I use a lot of graphical notation and diagrams, and so just in case, if just maybe to refresh what they mean. And then, so whenever we see a vertex is a tensor, and then the edges attached to the vertex are tensor indices. So in this way we can distinguish scalar, there is no indices, vector, one index, matrix, two indices. And then when we close the line from both sides, we introduce a summation over this line, over this index. And so we can express the inner product of two vectors here, matrix, so matrix vector multiplication, and matrix multiplication, and so on. And obviously we'll talk about tensor, so we'll probably have much more lines here. And then we can also show things like SVD in graphical notation, like we have left unitary tensor, right unitary tensor, and the singular value tensor here. And also there are, of course, in tensor algebra, there are many more different decompositions. And so these are just few of the mostly common and most used decompositions, where, for example, a tensor of order 4 can be decomposed using any of these decompositions, because we see that the number of open edges is preserved. So we essentially express the same tensor, but using different type of decomposition. And this can be either exact or approximate. And so the tensor factorization essentially, so the whole idea is, of course, that our many-body tensors, in particular in couple cluster theory, they are not reducible to just a rank 1 product, right? So otherwise everything would be solved. But at the same time, they're also not necessarily the full rank, which means that you can approximate the many-body tensors quite well using some relatively low rank tensor decompositions. And actually the choice of the form of specific ansatz for this decomposition is mostly dictated by the available software or by some consideration of the structure of entanglement in the particular many-body problem. And this is again just some examples of the tensor decompositions which can approximate a given high order tensor. And this has a very wide applications in condensed matter, of course, quantum chemistry, which is kind of moving more and more, quantum computing, especially now, and data analytics, and even deep learning. So this very kind of used now theory. But apart from this, so again, like as I mentioned, that you can apply the tensor factorizations to couple cluster tensors, and you will end up having this whole plethora of factorized couple cluster methods. And so they do reduce the computational cost, not necessarily to a linear scaling, but to some lower scaling. But I want to introduce some alternative here, which is I call hierarchical scale adaptive couple cluster theory, which is based on some papers that I published in the past. And so the first observation is that when we define, so this is just a schematic drawing, like for example, of a Hilbert space, and you see that kind of silhouette there, and this kind of our wave function that kind of we're trying to describe. So this kind of it's a major support in the Hilbert space that we're trying to capture. So, but normally we observe that, for example, the couple cluster CCSD, yeah, it can probably well describe some part of the Hilbert space here, but not necessarily here, right? Then CCSDT is again kind of moving this direction. It describes a lot of space here, but again, it doesn't really, not enough to capture the whole thing. And finally, the CCSDTQ, in most cases, yeah, provides us a pretty good answer because it can capture our wave function well. But at the same time, the cost is prohibitive because it also describes a lot of empty space, which we're not really interested in. And there are also more smart approximations that I used to also be involved in development in the past, so-called little TQ and single reference, multi-reference approaches, right? Which are kind of trying to capture the wave function in a more kind of intelligent way to avoid describing the empty space, but mostly focusing on the wave function. But of course, what we want is that we want something like this. So we want a method, like some kind of, I call this adaptive for a good reason, right? And so the adaptive couple cluster methods are trying to capture, so they're trying to be automatically adjust to the described wave function and capture only the essential part and avoid describing empty space, and this kind of save the cost. And so this is kind of the first idea. The second idea is that so we can so couple cluster theory, of course, is based on numerical tensor algebra. So we essentially just manipulate tensors and perform tensor contractions, additions, products, and we get our results. So everything is a pure tensor workload. So the next approximation, what we can do to reduce the cost further, is that to introduce this kind of adaptive structure on our tensors. And here I present just a matrix and a vector, but of course, in general, these are tensors because tensors are just harder to draw. So this is for convenience. And so what we can, I mean, we can just take the ideas from H and H2 matrix theory and just apply this to tensors and to our many-body tensors. And just to make sure that, for example, diagonal blocks are resolved in a higher resolution and then off diagonal. And some blocks are just neglected because they're small. And by introducing this kind of adaptive resolution, we again saving. So we introduce additional savings in the computational cost, and consequently reduce the cost of the final approximation, while presumably not losing much accuracy. And again, the whole idea is that we can just consider a tensor as just a collection of tensors, and introduces a recursive definition of a tensor. And then we can always, during our tensor operations, we can always either reduce a tensor to a scalar, or we can just, for example, take a tensor element and expand it as a collection of tensors. And this kind of a recursive tensor structure, that's what defines this tensor algebra here. But then we can also do one more thing. And even in the third idea is next approximation to even further reduce the cost is that is based kind of on advancing this hierarchical tensor representation further. And we again we start from for example, flat matrix representation, and this is just a matrix decomposed into tiles, right? And then we know that some tiles have large norm, some tiles have small norm, because normally we deal with connected tensors, and connected tensors in a local basis, they decay with the distance between basis functions. So we know that this structure is in place, so we need to exploit it. So what we can do again, we can just take the full tensor, and now just instead of just considering different resolutions for each tile, we can actually then group the tiles into larger tiles, and until up to the point when each tile has approximately the same norm from some some estimate. And so this is applicable to connected tensors only, and this just again follows ideas from, for example, methods like fast multipole or multi-resolution analysis, and just applied to many-body methods in couple cluster theory. So, and with this structure of the tensor now, that our tiles actually have different size, and they're also adaptively resolved, meaning that the basis within the tile is also can change, the number of basis functions. So this kind of gives the full hierarchical tensor representation that we can potentially use in coupled cluster theory to reduce its cost. So another important kind of if you're trying to elaborate this idea further, like what's was published in this paper below, so we can actually introduce additional structure to our Hilbert space, and we can equip our Hilbert space with this notion of scale. And scale just comes merely from combining our Hilbert space with actual physical domain, which is in our case is 3D, but it can be 2D or 1D. And then considering the support of local basis functions and considering this kind of new geometry to define this new scale. And so the whole point of this is that, for example, we can take here, for example, we take a 2D case. And we can just span this 2D, we can span the Hilbert space by placing this like individual basis functions like in each cell here, and just have this kind of resolution, right? But then we can also coarsen it, of course, and we have just combine these four basis functions in one, and in such a way reduce the basis dimension and coarsening the representation of the space. And then this consequently leads to coarsening in the tensor representation. So on this, each different width of the tensor lines means that now the range is shrank, and we essentially the line now each index in the tensor now describes not individual basis functions like we had originally, but some more aggregated basis functions. And this can be continued and up to collapsing all the basis functions just into a few, right, which cover the whole space. And so and again, the whole idea is to show that this kind of smooth, I mean, not really smooth process, but this is gradual process. So one can choose what is the best scale for the tensor based on some consideration of interaction strengths. And so diagrammatically, this can be represented like a space, direct sum space aggregation. And here, like again, this line, each line is a index. Index means that, so a tensor index, which corresponds to these lines at the bottom. They correspond to original basis. And consequently, so we have we can now take one line and then the second line build a direct space. For example, one line corresponds to half of the domain, and the other line to the second half of the domain. Then we can build a direct sum, so which can full domain, but then coarsen it and reduce the number of basis functions, which is this line. So in this line now have less extent than this line. And we can repeat this recursively until we collapse the full space to a few basis functions. And of course, it's approximate because we cannot. So we always lose something when we coarsen the basis set and introduce truncations in the basis set. And two important things here is that this kind of transformation is isometric, which means that if we just contract this transformation, this is essentially a matrix, right? Because two edges. So if we contract it over the fat line, we'll get identity. But otherwise, if we contract it over this thin line, we'll get a projector, and projector essentially projects to this coarse and reduce dimensional basis. And important implications here, I mean, so this is probably the most important part of all this, is that by introducing this hierarchical structure in a Hilbert space, we can now take any quantum many-body diagram based on connected tensors. For example, so this is my notation for quantum many diagrams, but it's very, very straightforward. So essentially, all the lines above the Fermi vacuum is particles, all the lines below Fermi vacuum are holes, and the lines going this way are creators, the lines going that way are annihilators. So it's very easy to interpret. And there is three tensors here. For example, Hamiltonian, T3 amplitude, and T2 amplitude of coupled cluster theory. So it's H, T3, T2 many-body diagram. So we know that, so this diagram has formal scaling is like 1, 2, 3, 1, 2, 3, plus all contracted lines, 1, 2, 1. So I don't know, like 0, 4, V3 or something. I won't be counting these lines now. So it's an expensive many-body diagram. So now the big implication of all this hierarchical structure of the Hilbert space is that we can take any many-body diagram, in particular couple cluster diagram, because it's expressed in terms of connected tensors. And then we can introduce this hierarchical structure to the Hilbert space, meaning that we change now the meaning of these lines, of these edges coming from tensors. And now, so we introduce a kind of three-way resolution. First, we choose which scale. Then we choose the local subspace on the scale. And then we choose a specific basis function in that local subspace. And by introducing this hierarchical resolution of many-body lines, particle lines and whole lines, now any quantum many-body diagram can be shown that its cost reduces to n log n flops. So essentially, we can now evaluate any many-body diagram with almost linear cost. And this is the main implication of all these hierarchical representations. And obviously also, maybe it's not obvious, but also each tensor now only needs ON bytes of storage. So essentially this enables application of arbitrary quantum many-body methods based on connected diagrams to pretty much arbitrary system. Because I mean, of course, there's some limit, but it's linear scaling, I mean, almost linear scaling. While also we don't really truncate anything locally, so we still cover the full space, but we just truncate in a different way. And so, and even one more thing we can do, even based on top of that, which is already good, but so that approximation still can have a pretty large prefactor. But to further reduce the prefactor, we can also introduce this compression techniques for higher order many-body diagrams, for example, triples, quadruples, and so on. And again, this is based on application of this compressing many-body isometries, where we take a direct product space. For example, 2 lines here is a direct product of two single particle spaces, or 3 lines, a direct product of 3 single particle spaces. And we introduce a projector from the direct product to some smaller reduced dimensional space. And with the same properties as described before. And then we can apply this isometries, these projectors to our tensors. So these are the 3 tensors from the previous diagram. And so we have Hamiltonian, for example, here, and T3 and T2. And then, so this gives us kind of a compressed representation of these tensors, compressed now in the sense that we reduce the rank, I mean, the order of the tensor, so the number of the indices. And this so this is just illustration how it works. So we have our original diagram coming from the CCSDT, which is this H2, T3, T2, 3 particles, 3 holes. And then using this technique, we can then introduce this projection isometries for the open lines first, then introduce compressing projectors inside the diagram. Then we can see that this kind of a fragment here, 1, 2, and then this guy and here. So we can just take this fragment and contract it into a single so-called like connector tensor. And then the whole thing reduces to this. So now the whole point is that we started from the 3 particle many-body diagram, but we ended up with 2 particle diagram. And of course, these are not just individual holes anymore. So these are multi-holes. These are linear combinations of direct products of holes. But formally, it looks just a doubles diagram instead of triples. And so this is one of the other important implications that what we can do with this technique. So this is what I have on kind of theoretical numerical approximations that, again, this is still work in progress, and I still need to validate, how this works in practice. It's not really easy to implement. I mean, it's really hard to implement this in software. And for this reason, so me and my people from the team, so we were developing actually software, high performance computing software for like easy manipulation of tensors. And so the latest one is called, it's open source software available on GitHub. And so it's called XZTN, which stands for Exascale Tensor Networks. And so this is software the goal of the software is to facilitate the processing, like the construction and processing of complex tensor networks and other like advanced tensor approximations, which is also work in progress here. But it already can do quite a lot. And so it can, for example, perform basic tensor operations, addition, contraction, product. It can then, now what we're finishing is that tensor factorizations and decompositions and finding the low rank of many-body tensor, for example, using very different, like actually arbitrary tensor ansatz. And also we can express the whole tensor operators and using tensor networks, which is mean connected products of lower order tensors expressing the higher order tensor. And so we can also kind of reformulate many of the many-body techniques now using the tensor network compression with arbitrary topologies of tensor networks. And so this is pretty much concludes my talk. And again, this software is oriented to be able to run on any computer, meaning that it can run on your laptop, it can run on the Summit supercomputer, and it also can just run on CPU. It also runs on GPU. So it's trying to exploit all the resources you have and give you the computing power for processing tensor networks and other tensor approximations, which can be applications can be from, of course, quantum many-body physics, condensed matter, quantum computing. So it's a broad application area here. So this pretty much concludes. And if there are any questions, I'll be happy to answer. And again, I mean, thank you for inviting me. And again, happy birthday to Professor Das.
Thank you, Dr. Liak, for presenting to us your interesting and new work. Okay, so let's see if there are questions. Vijay, is there a question?
No, I don't see any.
Okay, so thanks again. Dr. Liak, did I pronounce your surname correctly, Dimitri?
Yeah, it's actually you almost exactly how it should be.
Can you pronounce how it is?
Liak.
Liak. Okay, yeah. Good.
Exactly.
Liak.
But it was a wonderful talk. I enjoyed a lot.
Yeah, very nice talk.
Thank you.
I hope it gives very good result also. So much more accurate.
Okay, maybe if I am allowed, can I just ask here directly?
Yes, yes, please.
Is it possible to apply this, contraction technique, tensor method for atomic coupled cluster theory? Are you familiar with that little?
Right. So in principle, yes, but of course, the atomic theory is way more complicated because you have a spherical symmetry, and then you have a non-abelian symmetries potential there, right? And so the more you add symmetries in your framework, it becomes much more harder to implement this. It's possible, but it's going to be very difficult to implement.
Okay, now we have received one question. Professor Srivastav, you may read it.
Okay, okay. Let's see. Is it on the chat?
Yeah. Or should I read it for you?
Yeah, please do it because I don't see
this
it.
Is by Professor Tronsauer from France. So he says it's a simple question. Where does your graphical notation come from? Apparently you use SVD for decomposition. That requires some threshold for truncation of the inner indices. How do you assure error control?
Right. So error control is a good question here, and since like there is and NSVD also an important part of this framework, but since there are some so many places where you perform this compression, so at multiple levels in terms of just the space compression, then direct sum compression, direct product compression, it's really it's probably I'm not sure how to come up with kind of a rigorous error estimate. But what you normally do here, since it's called adaptive, is that you gradually release the threshold and observe the conversions. And that's kind of the only practical way how this can be done now. But so far, yeah, there is no rigorous error control.
I think that's all.
Okay, so let's thank once again to Dr. Liak for very interesting talk.
There is one
And
more.
this, another. Yeah, let's see who is there. I can. Do you
it's
see
by
that?
Dr. Ayaki Sunaga. He says it's a beginner's question. Why exact tensor with symmetry is so difficult?
Because again, with abelian symmetries, it's maybe not so difficult. It essentially boils down to introduce an additional tiling based on the irreducible representation, and they are one-dimensional, so they combine really easy. For non-abelian symmetries, then becomes much harder.
Okay, that's all I think.
Okay, so Vijay, should we close this session then?
You can thank all the speakers, then Prasanna will just.
Okay, sorry.
You can thank all the speakers, then Prasanna will.
Yes. So yeah, that's what I'm going to do. Okay, so we thank all the speakers once again. And I don't see Professor Das. My best regards to Professor Das, and maybe I join tomorrow.
He's there. Maybe I would like to request him to come online in video for some time.
To show,
you have
everybody.
got two senior colleagues here. If you can come on video, that will be very nice.
Okay.
Okay,
I've asked to unmute him.
Okay.
Okay.
Yeah, maybe he is not familiar with that technique. Maybe tomorrow we'll see him. Anyway, tomorrow we'll
Okay. No problem. Okay, thank you, Vijay, Vindhya, everyone. And it was nice to conduct this session. Thank you very much. Bye.
Yeah, I'm here.
Oh, okay, Professor Das. Hello,
Okay,
how are you?
Fine, so thank you so much. I mean,
Thank you. Nice to see you after.
Very nice to see you,
long
Dimitri
time.
and Pranav and Professor Srivastav. Okay.
Yes.
So I'm really grateful to all of you. I mean, so
we are delighted.
what time is it there for you now? I mean,
Where, in India?
No, I mean,
with Dimitri.
Dimitri, what time is it there now?
Oh, it's very
9?
early for me. It's 9. Yeah.
Oh, sorry, what time?
9 a.m.
Oh, 9 a.m. Okay.
9 a.m.
So,
9 a.m.
all right. So thank you so much again. I mean, it's nice to see all of you. And okay. Fine.
Very good. Thank you.
Thanks. Thank you.
Bye.
Bye.
Vijay?
Then I'll take this opportunity to thank both the chairs for the day, Professor Bimalendu Deb and also Professor Rajesh Srivastava, on behalf of all the organizers.
Okay.
And
thank you.
Thank you. And I'll hand it over to.
We are meeting at 10 o'clock. Start at 10.
10 o'clock tomorrow. Yeah.
Okay. Bye.
Okay. Thank you. Bye.
Thank you. Bye-bye.
Bye.
Okay. Hello again. Thank you very much, Vindhya, for everything.
Thank you so much. Yeah, thank you.
Right.
My pleasure.
Okay. So I somehow. Okay. So then, shall I leave then? Okay.
Yes.
Yeah.
Oh,
we are
okay.
going to close it.
Okay. Thank you. Thanks.
Vijay, has the live streaming ended?
Oh, I thought you were taking care of that. Oh, I see. You are not the host. I am host.
Yeah, you are the host. Yes. Still.